Okay, good morning, everyone, or afternoon. This is the second day of the workshop, and it's a long day, but it's going to be a good day. So let me see. First thing is, I wanted to run this video again. We're going to talk about, we have two speakers focused on Tropical Cyclone Freddy, not Tropical Cyclone Hurricane Freddy, but Tropical Cyclone Freddy. But I tried to run this yesterday.
Tropical Cyclone Freddy has become the longest-lived named tropical cyclone ever, beating out Hurricane and then Typhoon John back in the 1990s. Freddy formed between Indonesia and Australia and then headed nearly straight west. Its intensity fluctuated, but at one point became the first Category 5 tropical cyclone in 2023. Freddy was so long-lived because the ocean during its entire track was very warm, and because the steering currents over the vast expanses of the Indian Ocean took it pretty much straight east to west. After crossing the Indian Ocean, Freddy crashed into Madagascar, causing a lot of damage, and then continued and made landfall in Mozambique, where it caused additional damage due to flooding and landslides. By the time it got to Mozambique, the steering currents in the atmosphere had decreased. So Freddy sort of wandered around back over the Mozambique Channel, almost back to Madagascar. Then it re-strengthened and made another landfall in Mozambique, where it caused additional damage and fatalities. The iMerge precipitation data set lets us monitor the rainfall that Freddy and other systems produce, no matter where it happens, over land or over ocean.
Okay, so I just wanted to show everyone that because we know Hurricane Freddy and Tropical Cyclone Freddy was a devastating event, and we hope that our colleagues will give us additional insight, both for Madagascar and Mozambique. Okay, so now I just want to say we're running a few minutes late, but I just want to go over the schedule for today. So we have the morning session around tropical cyclones, both in the Indian Ocean and the Eastern Atlantic. We'll take a break, and then we'll move towards flooding in the later morning and finish with a Q&A. I might say that tomorrow I'm writing down the main points for your talks so that they will be discussion points for tomorrow when we meet. And then also this afternoon, we have a similar set of talks, but more focused on the US. And I think if you can hang around, if you're on the continent, to listen to some of those talks, it may be very interesting. But I know it'll be getting very late for some of you. So we want to get started this morning with our first speaker. And that the first speaker is Rivo. Now, Rivo, I will slaughter your name, but then you will resurrect your name. So I want to say RANDRIANARISON, but that's probably wrong. But you're gonna send you, does Rivo have the, yes. Okay. Let me just say a little bit about Rivo before he begins. So he's the head of the operational meteorological department with the Met Service in Madagascar. He's a senior forecaster with some focus on extreme weather. He has an engineering degree in meteorology, and he also has a master's in remote sensing and risk management. So Rivo, would you please share your screen and take us forward.
Okay, so by the time my presentation as introduced by the moderators, I will speak a little about how we have been dealing with Tropical Cyclone Freddy on February, March last year. So this is my outlines. I will speak briefly about genesis and evolution of the system, and then after that, early warnings system before and during the events. I will also talk about track and intensity forecast, then the observed impact, and I will conclude with some challenges we are facing here in the forecasting office. So next slide, please. Okay, so I don't want to add more information about the genesis because we had quite a good introduction as a video from the beginning of this workshop. So this is Freddy. The genesis of Freddy was really very far from Madagascar because this happened in the eastern part of the South Indian Ocean. So this area of responsibility is under the responsibility of the Bureau of Meteorology Australia. So Freddy was named as a tropical storm by the Bureau of Meteorology Australia before moving into the Southwest Indian Ocean basin. So just for information, the two basin is bounded by the 90-degree east. So in the west, we have the Southwest Indian Ocean, and in the east, the area is under the responsibility of the Bureau of Meteorology. Just for climate drivers, at the period early in February 2023, there was quite a very strong pulse of MGO in phase 3 or 4 around the maritime continent. So this contribute very, I will say, quite high in terms of pulse for the genesis of tropical cyclone Freddy. And rapidly from 3 to 5 February, Freddy intensified quite rapidly because the system reached the tropical cyclone intensity just 3 days after the genesis. In terms of motions, as we can see in the satellite pictures, we have quite a very established high pressure belt from west to east of the Indian Ocean. So this was the main steering flow for the system. So that is why we had quite a zonal movement of Freddy from east to west. Next slide, please. Next, please. Okay, so this one is every Monday we are issuing like a weekly outlook for the whole week. So this is the bulletin we issued on 13 February. At this time, the system were already over the Southwest Indian Ocean basins. Just for information, Freddy made a landfall to the southeastern coast of Madagascar on 21st. So this is really 7 days before the landfall impact of Freddy. So at these times, what we mentioned on our weekly update is that the Met Service is closely following the system, and information will be shared as soon as possible. And then at these times, we keep really close monitoring the system. And the problem was that because everyone is checking information on the internet, and it is like they are rushing to head to the Met office to ask about how about Freddy. Over center is speaking about Freddy. It's gonna be hitting Madagascar over the couple of days. So this is the information as the key messages we provided 7 days before. So Freddy may pose a threat to coastal community, but need precision within a coming day, of course, because uncertainty remain very quite high at this lead time. Next slide, please. And other thing we are doing when we are dealing with cyclogenesis, which may cause a direct hit for Madagascar. So we have quite a we have a long terms of historical database. So we tried to look at historical system which may have a similarity of a Freddy. So after checking on our records, we found that there was a tropical cyclone Elin in 2000s at the same month in February, and as you can see on the map, Elin was also from the eastern part of the basins. They moving from east to west and affected Madagascar, but quite in further north compared to the landfall point of tropical cyclone Freddy. So this is only the historical event we do have at the time before. Next slides, please. Yeah, in terms of early warning in Madagascar, this is our general flow in terms of the information sharing. So DGM is the Met Service in the middle. So in the up the B and GRC is the Disaster Management Authorities, because at the time like this one, we work very closely with the disaster management. We are sharing information from Met Office to disaster management, and in the opposite ways. So this is just to make sure that the authorities, the public, every humanitarian action involved in the emergency operation receive the, I will say, the useful information so that they can prepare for anticipatory action. So we provide directly my list to the disaster management. We also provide information to the higher level, which is the ministry, for example, the office of the prime ministers. We work also very closely with the local media, radio, TV, newspaper, and of course we have our own website, and we have also a communication department here in the Met Office and then through that they are really try to reach the maximum of public through social media. Next, please. Yeah, in terms of uncertainty, this is the GFS ensemble forecast from the GFS model 5 days before the landfall. So as you can see, there is quite a good, I will say, good hints in terms of impact of Freddy in the eastern part of the Madagascar. But if you look at the ensemble member spreads, you can see that the GFS is forecasting the system is going to be make landfall further north as compared to the observed track. And in the bottom we have CMC, which is the Canadian ensemble forecast models, which is also available publicly for us. So this is valuable information which is available to the forecaster at the time. Next, please. Yeah, we started to issue first level of tropical cyclone warning 5 days before Freddy. So this was the first track forecast we issued on 17 February at 10 local time. So and at that time, as it is said in our national contingency plan, we have to organized like a technical briefing with the disaster management committee before, during, and somehow after an emergency situation like Freddy. So this is the key point we shared with the disaster management committee. At this time, the uncertainty is quite large. The spread is the trucks was spreading up to 800 kilometers, but we say that in terms of intensity, Freddy may be a cyclone or intense tropical cyclone when it's going to reach the coast of Madagascar. And we also made issued the key point as the first arrival of first cyclonic swells, storm surge, from 20 February in the afternoon or at the night. So, of course, 5 days before is the uncertainty is remain quite large. So we will see the evolution then over the coming days. Next, please. Yes, and then this is the weather briefing on the next day on 18 February. Nothing much is changing, but we were able to reduce our uncertainty cone to 600 kilometers. But if you can see, Freddy strikes Mananjar. I don't know if you can see Mananjar is just south of the track forecast. But at this time, we expected Freddy to hit directly Manur. It is about 100 kilometers north of the landfall impact. Yes, next, please. Yes, maybe you can click on the images. This is an animation. Yes. Yes. At this time, it's quite a critical time because this is just 24 hours prior the landfall of Freddy. In terms of the system, as you can see, there is some vertical, some shear impact on the system. And if we checked the microwave data, the Freddy was under the ERC, E-wall replacement cycle at this time. So hopefully, due to this uncompleted ERC process, Freddy finally, because at this time, Freddy was like a Category 5 tropical cyclone, and then over the next few hours before landfall, Freddy finally started to weaken. In terms of average, Freddy was we say it as a classical size, around 40 kilometers. The size of the tropical cyclone we are using here in Madagascar is defined by the radius of Gulf force wind. Yes, next. Yeah, this is GFS ensemble forecast. If we check the landfall points, we can now increase confidence in terms of where the system will make a landfall. So at this time, there is still some spread in terms of forecast, but the confidence is growing up. Yes, next. Yeah, at the same times, maybe I need to mention in terms of cyclone warning in Madagascar, we rely on the risk of tropical storm force wind or greater to issue a tropical cyclone warning. So if, for example, a system is expected to hit Madagascar, but at a lower stage, we normally not issue tropical cyclone warning. Another point is the accumulated rainfall forecasted at the time. We expected more than 200 millimeters around the landfall point, but also over the eastern part of Madagascar, there is quite this is a mountainous area. So due to this, probably there were more than 200 millimeters, maybe 400 or more over certain area. We will see. Yes, next, please. Yeah, on 21st, this is the time where Freddy make a landfall. We issued the highest level of warning 12 hours before. This is really under the SOP or the standard operating procedure, because we normally issue red warning, which means cessation of all activities, economical activities. So everyone under red alert should stay safe at home. This is 12-hour prior the landfall. This is a cyclonic special bulletin we normally issued with this kind of situation. So we will see when I will close the challenges at the end of my presentation, because in Madagascar we are not operating 24 hours due to lack of staff. We only have 3 operational forecasters here in Madagascar, so we are not able to operating 24 hours in terms of shift. But when because this is a kind of an emergency situation, we normally activate permanent watch when we reach yellow or red warning. Yes, next please. Yeah, also we are running in terms of NWP, we are running WRF model here in our office, but the problem is that we are facing too much challenge in terms of IT, power failure, internet speed. So if we are running systematically WRF model, if we have failure in terms of internet, we cannot download GFS to initialize completely our WRF model. So hopefully we were able to have output from our own WRF model at the time. So this was run on 21st at night during the landfall of the tropical cyclone Freddy. And as you can see, in terms of track, it's not too bad. Yeah, it's not too bad. Yes. Next. Yes, and after that, Freddy made landfall 21st at night. Freddy then crossed Madagascar from east to west and then reached the Mozambique Channel and affected Mozambique later. And after reaching Mozambique, the remnant low of Freddy stayed inland over Eastern Africa, triggering heavy rain like for Mozambique, Malawi, and neighboring country. And after that, 5 days later, the vortex associated to Freddy came out again to reach Mozambique Channel. And at this period of time, the SST over the Mozambique Channel is quite high. So Freddy was again able to re-intensify, and this is the part 2 of tropical cyclone Freddy. This is 2 days. Do I have how many times is remaining, please? Do I have like 5 minutes?
Yes. Continue.
Audio got disconnected for some reason.
He's online, but his microphone disappears.
Sorry. Disconnected.
He may be having problems with his internet or his mic.
Yes, sorry for that. Internet is unstable in our office, so that is why kept my camera off. Okay, so for the part 2 of Tropical Cyclone Freddy, the threat was mainly associated to mariners, because as you probably know, Madagascar have a very long coast as the economic zones. So many fishermen over the western, southwestern part of the country. So we, our vigilance or warning were mainly focused on high waves and strong winds, which may affect so the coastal part of the southwest region of Madagascar at this time. Yes, next, please. Yes, for the part 2, we issued red highest level warning on 6 March. At this time, the tropical cyclone Freddy was a severe tropical storm. Hopefully, it didn't reach a higher level stage. And in addition to that, the size of Freddy was quite reduced. So the extent of goal or higher force winds were really reduced only for the coastal area of the southwest region, but to make sure that everyone is keeping safe at home, so we decided to trigger again a red warning only for 1, 2, 3, 4 districts over the coastal part of the southwest region. And then after that, Freddy stayed maybe up to 12, more than 12 hours just offshore of the coast of Madagascar, around 50 kilometers. And hopefully after that, a high pressure system is building just south of the Mozambique channel, and then steering the system to adopt a northwestward motion to head into Mozambique. Yes, next slide. Next slide. Yes. In terms of track and intensity forecast, this is our official forecast we issued in red. In the red, this is the forecast track we issued 5 days before prior the landfall. In pink, the day 4 prior landfall. Yellow, day 3, and the green one is the day 1, just 24 hours prior the landfall. I don't know if how maybe you judge our forecast at this time. I can say that Freddy, part 1 of Freddy was quite straightforward in terms of track forecast. Of course, there was a lot of uncertainty several days before, but when the system really approached the coast of Madagascar, and then the forecast was really quite good. But part 2 was quite difficult. As you can see, is the same. Blue is day 3 prior the system reached its closest point of the coast of Madagascar. And then I will say in overall the track forecast was quite good. Yeah, next slide we will have some measurement in terms of track error. Next, please. Yeah, in terms of track forecast, this is the mean absolute error. We conducted some verification of official forecast we are issued. The the black solid line is the mean error. 50 kilometers from 12 hour up to 200 kilometers for longer lead time. Yeah, in general, I think this is quite good if we compare the scores with our past performance. But in terms of intensity, we laid around 10 knots of error through all the lead times. Yes, next. Yeah, in terms of impact, this is the impact bulletin we received from the Disaster Management Office. The map in the right is the accumulation rainfall from 21st to 22. As you can see, there is quite a huge accumulation of rainfall here over the mountainous area in the eastern part of the country. And I can say, according to the report from the local authority, there was a lot of landslide over this part of eastern part of the country. Just a quick view of the impact of Freddy. They recorded 3 fatalities. 3 missing people, I'm sorry, 10 fatalities, and more than 50,000 people were affected by the system. There is distribution like for infrastructure, for schools, for health care facilities, for water, and for agriculture. So as Madagascar is part of the African risk capacity in terms of Madagascar has been subscribing to the parametric insurance for tropical cyclones. So according to the Tropical Cyclone Explorer, which is the tools they are using to try to count the impact of any tropical system affected Madagascar, and they found that at least 200,000 people were affected by the system, and the damage was estimated to around more than $400 million. Yes, next. Yeah, to conclude, this is our main challenges. Human resource, as I said, we only have 3 operational forecasters. Can you imagine Madagascar is a big island? We all 3 operational forecasters, they are working on marine forecast, public forecast, extreme weather forecast. And due to that, we are only operating for only during a day shift. Yeah, forecast is based on observation. We have a huge lack of ground observation. We do have only 3 synoptic stations, which is operating 24 hours, only 1 operating station. In totals, we got up to 23, 24 weather observations across the country. This is really insufficient. Of course, because of that, when the system is reaching land, it becomes too difficult to follow or to track the system because there is no observation. Hopefully, Freddy make landfall over Mananja, so we have weather station there. But just 2 hours prior the landfall of Freddy, our weather station was out of service, completely out of service due to the strong wind. Yeah, we do have local product, for example, WRF model, but it is not integrated to our forecasting system. And we only have 1 workstation, forecaster workstation, but the problem was that during the tropical cyclone season 22-23, this is during Freddy, our workstation were out of service. So we are not able to work properly with as a forecasting shift. Yeah. Actually, there is also several project program, but they are supporting mostly disaster responses aspect, not NMHs. Next, please. Yeah, but now the things is changing quite. Maybe you are aware about START Network. It is a world-leading humanitarian action. They are working mainly to anticipatory action. So since 2020, START Network arrived in Madagascar, and we started to work together. And we are supporting them for anticipatory action in terms of tropical cyclone forecast mainly. And then, of course, there is more ongoing initiative now to support NMHS, because you know that E for all is for everyone, and Madagascar is part of this. Hopefully, Madagascar is one of the beneficiary country as a pilot country to E for all. There is CREW project, there is Hydromet project, there is many regional projects actually, and they are there to support more NMHs. And then, of course, despite all of those challenges, we keep carrying our main mandate, which is saving life and property, especially in the context of changing climate. I think this is the end of my presentation. Of course, if you have any comment or question, so thank you very much.
Rivo, thank you so much. It was very informative. We can take, there's 2 questions in the chat. Well, let's do the first one. Do you have a supercomputer you're running your ward forecast on?
Yes, yeah.
So you have supercomputer, but it's not the supercomputer, it's the challenge of downloading the boundary layers, boundary condition, and the speed that it takes to do that in real time.
Yes, yeah. I don't have my. Maybe I should have taken some picture of the state of our server room. It is really nothing to do with a server room. We have power failure problem, we have internet speed problem, and when we are running WRF model locally, this is only initialized with GFS model. But the problem is with bandwidth. Sometimes our internet is not quite speed enough to gather the data initialization. So the model is trying 1, 2, 3 times, and if it fails 3 times, and then just let it down, and we are waiting for the next day. And our supercomputer is not really a supercomputer like, for example, in NOAA or in the global center. This is supercomputer, but it's not the same. There is a limitation also. Like, for example, we are running model up to 5 days, 5 to 7 days, and it takes roughly around 5 to 7 hours to complete the forecast cycle. Yeah, so you imagine, so that is why we are not running, we are running only one run forecast per day, which is 18 Zulu. So we cannot run two forecast cycle per day due to this supercomputer capability. I don't know if I answered the question properly.
Yeah, we have 2 quick questions, and we're running a little bit, but we also have built some time for Q&A. So the question, there's 2. First one, how effective is the early warning for alerting people?
Yeah, this is like a self-evaluation, because this is you are asking the question to us, so we try to to evaluate ourselves as humble as possible. Yeah, this is the first time we have been using for tropical cyclone alert. Let's say far away from, let's say, many times before the landfall, because usually we are issuing tropical cyclone alert in general 2 days or 3 days before impact. But at this time we did it 5 days ahead. So and now the things is changing. Many people is connected on social media, and this has been changing really the communication aspect in terms of early warning system for everyone. Because normally in normal condition, I will say maybe 5-10 people is checking our social media, our post on Facebook, for example. But when we are starting to issue like tropical cyclone information, starting from Genesis up to really the highest level warning. So our view is really increasing. So I think this is things we can use in terms of measurement of how was the communication. I think it was quite good because if we compare the impact of Freddy with our colleagues, for example, our neighbor country for Mozambique, for example, for Malawi, maybe we can say that Madagascar is used to get tropical cyclone. Maybe we are more experienced in terms of how to face, how to prepare before tropical cyclone. But if you compare the impact, I think that at least we made a good job, I think. Yeah. And we received some feedback after the impact of Freddy, and in general they said that the communication was good on times, and the forecast was in general, in overall, able to help especially authorities and the disaster responder to well prepared for evacuation, mainly over the southeastern part of the country. Yes.
Okay, I have to let you get this last question because it's from one of your countrymen who work in NOAA, and it's Rob John, and he says,
Yeah.
what is needed to improve TC forecast for Madagascar? Looks
There is a lot of thing we need. Like for I don't know if you can help us to get more tropical cyclone forecaster. This is really a big challenge for us because three is not enough. Three is not enough. Can you imagine? Freddy was almost 1 month. So if you keep watching, keep following Freddy for three people rotating as a shift, this is really difficult. So human resource, this is one thing. Infrastructure, another things. Weather observation. Actually, there is a lot of, I will say, initiative, regional initiative or global initiative from, for example, WMO, because Madagascar is also part of the SOF project, which is we are expecting to have additional weather station, but this is not enough. At least we need one weather observation per district. Districts means it's more than 120 weather station, which is transmitting observation as a GBON compliant every 1 hours. And another one, of course, we need more training because my forecaster, my team here, they are still young forecaster. Most of them, they are spending times with the Met Office, let's say in average 5 to 6 years. So of course there is there is the support from WMO through the tropical cyclone committee. The WMO is organizing training every 2 years at the RSMC La Réunion, but this is not enough because we need more, for example, more practical training, especially for severe weather event like Freddy. Yeah, but if maybe this is not all the challenges, maybe we can share, exchange by email what can be done. And of course there is also our national action plan on e-warning for all. You can have a look. It has been launched internationally this year, so you can download it and then check what is the needs, really needs for the med service to enhance the public service or early warning system for everyone. Yes, thank you.
question, but I want you to try to answer this in the chat, Rivo, so we can the next talk, and we'll come back to this during discussion Q&A period. But again, thank you. It's very informative presentation you gave us. So next we have the Met Service from Mozambique, talking about TC Freddy. Let me get the Bernardino Nhantumbo.
Good afternoon here in Mozambique, and good morning that side, Carol.
Okay, before you start, let me just tell everyone that you are a doctor, first working at the Mozambique Met Service. You're a climate researcher, and your background is meteorology, and you have master's degree from University of Cape Town and PhD from University of Cape Town. So we look forward to your presentation.
Thank you. Can you see my screen?
Yes.
Thank you so much. And thank you for having me and the invitation that was made to Mozambique National Institute of Meteorology. Yes, I'm Bernardino, climate researcher and meteorologist by background. I will be presenting what we're doing on tropical cyclones and also sharing some experience on the tropical cyclone Freddy. I'm safe. I could foresee what Madagascar will present. That's why I try to bring the information in a different shape. So we used to say that Madagascar is our shield when it comes to tropical cyclone, and it was proved now. So this is the presentation outline, and I'll give some introduction, speak about Mozambique climate, and then tropical cyclone, what we know as a historical information, then early warning system, because it also says a lot when it comes to our performance, when it comes to tropical cyclones, and then speak about tropical cyclone Freddy per se, and then some activities that we are doing on anticipatory action for tropical cyclones, and then a list of complaints and challenge, and provide some screenshot of the damage caused by Fred. So Mozambique is a country highly exposed and vulnerable to multi-hazard due to its geographical location, long latitudinal and the geography. So it's with that we tend to suffer a lot from a multitude of hazards, including heavy rainfall, strong winds, severe thunderstorm, tropical cyclones, flooding, river and coastal storm surge flooding, droughts, and the related diseases. So given to that extent, you tend to have like a dipole kind of impact when it comes to these hazards. And the vulnerability also is highlighted by the long coastline. So it's the fourth longest coastline in Africa, and the majority of the population are near the coast. With all the challenges that we're facing, and we rely a lot on rainfall agriculture, and we have like key ecosystems also along the coasts. So as for the climate, we have two distinct seasons. One is winter from April to September, and then another one is summer from October to March. So October to March during the summer, which is the rainfall period, is hectic in terms of meteorology aspects. So it's a lot is going on during summer. And our rainfall is highly associated to El Niño sudden oscillation. So drought has been shown to be associated with strong El Niño condition, but La Nina also is associated to above normal rainfall. So I was speaking about dipole situation where, because the southern part of the subcontinent is associated to El Niño through below normal rainfall. But the east part of Africa is the opposite. So Mozambique being the transition between these two regions, we have situation where, for instance, in the last rainy season, we were suffering with drought in the southern and the central part of the country, but flooding in the northern part of the country. So it's really challenging to deal with disaster in a situation of that. So the graph here is showing how the rainfall is distributed along the rain season. So we have the rain season sitting in 2 consecutive years. We are doing some analysis to understand how tropical cyclones have been changing over time and impacting the country. So the graph that we see on my left-hand side, it shows tropical cyclone that made landfall in Mozambique from 1998 to 2023. And we can see that there are changes in terms of the number of tropical cyclones that make landfall in the country per decade. So brown are the number of tropical cyclones that made landfall in Mozambique during the 80s. So we had like 3 tropical cyclones, and the number keep on increasing. But what is concerning is that the last decade that started from 2021, we have more than what we have been observing in 10 years. So it shows that we are in a decade that might be very hectic in terms of tropical cyclone reaching the country. So on my right-hand side, we have a map which shows different tracks to prove that a tropical cyclone is a national problem. So sometimes communities that are not impacted by tropical cyclone during a certain period, they tend to forget. But historically, the whole coastal line of Mozambique has been impacted. So it's something that we all need to care about. Here, I share the disaster management structure so that you understand our role. So I try to highlight where meteorology is sitting here. So during an event, we have this technical council for disaster risk management and reduction, where different sectors sit together and come up with different information and discuss what should be done. And the roles are clear. And some of our challenge comes because of that. So in Mozambique, we are responsible, for instance, for the rain when it's in the sky. But once it touches the ground, we are no longer allowed to speak about it. So this is one of the constraints that we have. So even if you want to give some recommendations, we still have to look careful about our mandate. So as the institution responsible for meteorology, the National Institute of Meteorology will provide advisory or warning related to severe weather, but we don't speak about flooding. When it comes to tropical cyclones, we have a weakness because warning system is based on wind. And we have been noticing recently that tropical cyclones that are not that intense bring a lot of rainfall. And the numbers are showing that we have a lot of people drowning. So people that are losing their life because of the rainfall amount. So not just rainfall should be the threshold that is being used. So we have a blue for when wind is approaching, and we expect those winds to reach a certain area within a day or two. And then we have yellow and then red. And we can see here the recommendations that are provided. And this warning system ceases to work as soon as the system hits the continent. So we have to shift to a different one. So that's another challenge, because we shift to a system that has to do with the rainfall amount. With the lack of observations, it's hard to estimate the rainfall amount. And most of the data that is available from different models tend to underestimate the rainfall amount. So that's another weakness that we have in terms of how to give different colors or to give emphasis when we issue our warning. There was some recommendation from WMO mission after tropical cyclone Idai in 2019 that we should adopt impact-based forecasting. So that's one of the solutions. But the challenge with the impact-based forecasting comes with the limitation in terms of mandate. So we have a lot that we are not supposed to say. So the challenge comes from that limitation in terms of mandate, but also we need to sit together and find a solution. And funding limitation is preventing us to have this discussion on how to overcome. So far, we have been using impact-based in a pilot phase, so we need to scale up. We saw a video on tropical cyclone Freddy, which is long-lived tropical cyclone that has been recorded or ever recorded. So we have this screenshot that we see here. And my colleague from Madagascar mentioned something very interesting, because when we saw the track of this cyclone, in our mind, it came Eline. Eline was a very devastating tropical cyclone in 2000 that hit the country, and especially the southern part of the country. At that time, we had a lot of support from the United States, and they have provided these Apaches helicopter to rescue people because their ability to work even during the night. So that support was very critical. So in 2000, so what comes to our mind, like, is it going to be like in 2000 what happened with Eline? But Fred shows to be a different because of the track. So it tends to go north, and in that area, we have a lot of mountains. And due to the mountain, it was forced to turn back and then go to the coast. So that was one of the main obstacles that made Fred to change its course back to the ocean. And we have seen in this area that sea surface temperature is very critical. So during this time, we have a very low vertical wind shear, which is very critical for them to survive. But additionally, what is a game changer for the cyclone to survive within the Mozambique Channel are the positive anomaly when it comes to sea surface temperature. So here we do some comparison, because recently we had tropical cyclone Idai in 2019, which costed us a lot of lives. So you can see in this table where we are comparing the numbers. So Fred was very intense, but it did not cost us a lot of lives. One thing is that these extreme events, they tend to, of course, it's not like a good thing, but they tend to teach community. So because the memory of 2019 tropical cyclone is still fresh, most of the community were keen to take action, which did not happen in 2019. Another aspect, it comes on coordination. There was a very good coordination between institutions, also thanks to 2019 tropical cyclone. NGO and humanitarian agents are now adopting anticipatory action. They were also key in terms of action prior to the event. So firstly, when we were forecasting, the track was showing that it may go to an area similar to Idai. And everyone was panicking. But that was a key to success. So we take advantage of that. Another aspect, which even my previous colleague mentioned, is to issue warning on time. So because of fake news, which is another bad thing that we're taking in a positive way. So with social media, we have a lot of fake news. So now we are forced to issue some information when a tropical disturbance is formed within the base. So we say that a disturbance is formed with a high possibility of developing up to a tropical cyclone in this area. It doesn't pose any threat to Mozambique citizens, but we are monitoring. So this comes as an official information from the Met Service. Then we keep on updating while it is upgrading its stages. So as soon as it reaches Mozambique Channel, so we provide warning because we know it will affect the coast. So Mozambique has a lot of fishermen, so we need to issue. So this information is proving to be key in terms of communicating our information. So because of this success, we have been approached by a number of NGO and humanitarian agents to adopt early warning anticipatory action information. So Mozambique or INAM, the Mozambique National Institute of Meteorology, is now engaged in developing some kind of triggers for anticipatory actions for tropical cyclone. So we are developing a standardized cyclone vulnerability index, which has two parts. One component is the semstat, which includes the amount of low-lying area, the quantity of housing infrastructure, and the amount of agricultural area. So agriculture is key because we have around 90% of the population depend on agriculture. And then we have the dynamic component, which look at food security. So this is the ingredient that we are using to develop this trigger for anticipatory action. So the work is ongoing, and we hope that will provide this information soon, which is a key for different agents to work on the ground. So when we comes to challenge, we have a number of challenge, and like when my colleague from Madagascar was speaking, I would say, okay, maybe I should not speak anymore because it's quite similar. So we have a limited number of observation a network. We have a serious challenge when it comes to automatic weather stations. Some are on the ground, but they are not communicating. And we have been trying to solve this under SOF, which is the Systematic Observation Facility, Financing Facility. So Mozambique is part of SOF, is being contemplated, and now we are moving to implementing phase. We have a number of stations that have been elected. Not all the stations will be financed, but at least we will want to learn from that experience to then scale up to others. We still have historical data in paper format. So we need some kind of data rescue, data digitalization, and then quality control. And then we use this information for operational purpose. So meteorologists that are on operational side should have access to the database. So based on the rainfall amount that is being forecast, we can look at the on the past, like when we had that amount, what happened? And it will guide us when it comes to warning, even a recommendation to take action. We need to more like a high resolution numerical model. We need to invest. Of course, we are running also WRF. We don't have supercomputer, but we have HPC. But it comes with a lot of problem. We start from skills from who is running this model. We need more capacity building. We have problems with connection. Internet connection is a problem. It has been identified like several times, but unfortunately it's not being resolved. We need to also more capacity building when it comes to analyzing or interpreting model output. So we know models, especially when it comes to global model, given that we are in a region that is being poorly sampled, they are always challenged with those outputs. So a meteorologist should not rely on one model. And we have been noticing that there's this tendency of people giving some preference, but actually we need to gather information from different models and then comes to a judgment. We need to also more capacity building or capacity building on processing grid file. So grid files are the ones that come with model output information. So that's another challenge. We need more skilled human resource when it comes to processing and analyzing radar or weather radar information. So we have now one weather radar, and the government has promised us more 2 weather radars, but the process is not being accompanied by training on how to use this information. And we know how sensitive weather radars are in terms of being contaminated. So we need to make sure that people are trained and are using for operational purpose, especially when it comes to nowcasting. So that's one of biggest challenge. Nowcasting is critical for extreme weather events. So it comes to how to use weather radar. We need automatic weather station information to be displayed live so that also support that that activity. We need also a capacity building when it comes to satellite image analysis, because also it will give us another resource to better monitor tropical cyclones. The database that we have, we believe that we'll be able to calculate return period. So return periods are very critical also. Depending on the rainfall amount, we can give an idea of it. This rainfall amount is expected over like a certain period of, and it support us or will aid us in terms of how we more vocal when it comes to warning. We need also capacity build on marine forecasting. So as I mentioned previously, we have a long coastline, is the fourth longest in Africa, but unfortunately, we don't have a marine forecasting unity, people that are dedicated. What we are doing so far is to issue warning up to 50 miles offshore, which is not enough. We need also skilled people on ICT. So this ICT for like a modern meteorology, you can't go anywhere without ICT people. And they've been showing a lot of weaknesses. They are not being capable of resolving most of the problems that we are facing. And it's linked also on how we can communicate based on our web page. So you need very good ICT to advise. We need to also training on how to manage social media platform. So we need to train like young people that they like this social media, and then we can keep on posting information. So what we need to change from like passive to active. Most of the time we are more reactive. When there's a fake news, we have to come up and deny that, no, actually it's not what it has been said, or it's not true. Another aspect is comes to even with the media in general, because they don't really understand tropical cyclone science. So it's a big challenge. We need to train them on the base of tropical cyclones so that they will better inform. We have challenges of different languages. So Mozambique has more than 20 languages, and we are using Portuguese because it's the national language. But we know that Portuguese is leaving a lot of people behind. So one thing is to train a community radio broadcasters. So we train them so that they translate our warning that are basically in Portuguese, they translate in local language. So this is being done ad hoc because we have funding limitation, but we would love to have everyone that is linked to community radio because they are key in terms of spreading the word. And we need also capacity building when it comes to effectively communicate with the public. So there are a lot of complaints because meteorology is very technical, and the people are saying we don't understand. In a country with a very high illiteracy, this is critical. So we are communicating in Portuguese. You don't have a lot of people that can read or write in Portuguese. And then we have a lot of technical terms as well. So it's like a very, we have this like kind of snowball when it comes to reaching. Another aspect that is key, I think, to everything is a limited funding capacity. So what the government allocates us annually is not enough to run, and it puts us in a situation that we are highly dependent. There's nothing we can do proactively. So it's all about, trying to find projects. There are promising projects. I mentioned SOF. We have a early warning for all that we are going to launch the national roadmap. There's another project which is called Represa, where we are looking at tropical cyclone in a warming climate. So we want to look how a tropical cyclone will change over time. So this project is also key to inform because the region is also poorly studied when it comes to tropical cyclone. Maybe due to the limitation in terms of data. So it's very challenging. There are things that we know, but we are not able to prove with the existing data set. So we depend on reanalysis data from US now with the ERA 5 data set. Those are base data that we use for studying, and sometimes either the resolution or nature of the data is not supporting to bring a more science-based information to support decision making. So here we can navigate on some of the screenshot when it comes to the impact. We can see many roads were destroyed. On my left-hand side, we have also a hospital in a rural area that was destroyed. Hospitals, schools are shelters when it comes to tropical cyclone. So when there are damage, it is not only about infrastructure, but we are losing a shelter as well. So most of the community tend to go to school, hospital to hide during tropical cyclone. We can see this community in the center that's been destroyed, power lines. We have an initiative which is called Electricity for All up to 2030. And with the tropical cyclone destroying power line, they are taking us behind because investment should be made for repressing. So we are afraid that we won't miss we won't reach the target of electricity for all by 2010. We have this rail line also that was also damaged. And most of the rail lines in Mozambique are critical for inland country. So most of the, like Zimbabwe, Malawi, South Africa, they rely on them to ship their goods offshore. And without them, it's not only Mozambique suffering, but we have neighboring countries that are not able to make this business. So I will stop here, and yeah, thank you so much.
Okay, thank you, Donato. We're behind, but we have like two quick questions. The first one says that Mozambique, TC Freddy hit Mozambique twice. Were adjustments made between the first time and the second time in terms of, let's say, warning or evacuation, or your warnings? What happened between the first and second landfall?
Yes, thank you for the question. So because it was like two distinct areas, it allowed us to do the evacuation. And as I mentioned, the coordination worked very well this time. And we had teams that have been dispatched on the ground to spread the word, both in the southern country for the first landfall and even in the second one. We had the issue with the first landfall because Fred was so rapid that did not give us, we tried to anticipate. And when you go beyond 5 days, when it comes to a tropical cyclone, there are a lot of uncertainty. So we had teams going to a certain area in 7 days, and then it changed the course. So it has some costs. But for the second track, we are very successful. If you look, is the second track, the second landfall that went to Mozambique and then to Malawi, and Malawi tend to have a lot of casualties. comparing to us. So because the warning system and the coordination was working, way better this time. So, yeah.
What were the number of fatalities in Malawi from the flooding?
Oh, yeah, I can't recall very well, but I think it was over 500 people, which is high comparing to Mozambique. It was less than 200 people, even with 2 landfalls. So we were okay. And the second rainfall was right in the middle of a seat. So we have Kilimani, but we managed to evacuate on time.
Okay. This is the last question, then we'll go to Cabo Verde. So we're gonna cut through our break. It's okay, we'll be all right. We're all hybrid. So the second question is, how often and how long ahead of time do you issue alerts or warnings as TC approach Mozambique? What is your warning time there?
Yes, so as I mentioned, due to fake news, now we are issuing an information. It's not necessarily a warning. Information, we inform the public that a tropical disturbance is formed within the base. And then when it comes to warning, we start once the tropical cyclone, it reached Mozambique Channel. It's where we start. Of course, this is the information that goes to the public. So we have a technical council where we share the information, and we warn them that beyond 3 to 5 days, there are a lot of uncertainty. So for the Fred, they insisted, and we provided that information. That's why the spread was so high. We had people that were dispatched to alert people on the ground in a very wide area, because it was done out of this 5-day lead time. So they learned as well from Fred. It was like a very good lesson that they should also leave the science to speak. Yeah. So beyond 3 to 5 days, there are a lot of uncertainties. So we don't advise speaking to the public, and we are not doing so.
Okay, so tomorrow we have a discussion period, and we're gonna come back to some very important issues that both you and Rivo came to around infrastructure, forecasters, measurements. Then there's still questions of evacuation, shelters, language. These are all a lot of issues that you guys have to deal with in real time when the tropical cyclone is approaching you. And so we have to come back to this. There's no way we can walk away from it. It's very important and very informative. Both talks are very informative.
Thank you.
If we have time for the Q&A at the end, maybe we can still get in 1 or 2 questions. But then we have to go to our other Portuguese-speaking country in the Atlantic, Cabo Verde. And this is going to be Carlos Moniz. Carlos, can you share your screen? I hope you're here. I saw you earlier. Yeah, you're here.
So hello everyone, and thanks Greg for having inviting me for this workshop, particularly for Cape Verde. So we are a special country here in the West Africa, where these events form. So I think it will be interesting for us to share our experience with this with the cyclones that form here. this rename that they given for calling them hurricanes from Cape Verde. So you can go for. So you can see here in Cape Verde, we are located in the Atlantic region that is propitious for form of tropical storms. Like in synodic terms, that we have atmospheric and ocean conditions that are favorable for the developing of depressions and hurricanes near our waters. You can go forward. Here you can see the topography map of Cape Verde. In Cape Verde, so because of the passage of the tropical waves, the islands of Salt is like the more effective ones, like Santiago and Fogo, because of the biggest ones, and because of the topography. When we have the passage of these tropical waves, we have more consequence in those particular islands. You can go for. These tropical waves, and in particular the SST, have a role in the seasonal precipitation in Cape Verde, because the precipitation in Cape Verde, it depends of two things. When the ITZ march to the north, and particularly when we have the passage of the tropical waves. And in particular, when we have the combination with warm SSTs, Cape Verde experiences some of these events, and sometimes it have consequences for the islands. You can go for. Here I have bring some examples of the last year that when we have the passage of the tropical waves, usually they are associated with a low pressure. We can see here in 4 examples that I bring here. So when they passage, when we usually have a strong rain and a strong winds that damage, then we have some damage that usually are located in the salt of the islands. Here we have examples of the islands of Foamouhoue. In 17 August last year, we have some damage when we have the passage of tropical waves. We can go for. Here another example. We have a low pressure associated with a tropical wave, and you can see we have strong winds here, and here in the set image is evident, and in the right you can see some damage that it have been provoked in the city of Praia. Then you go for another example in the same year. We have some local damage provoked by another tropical wave. So you can see when we have the passage of these tropical waves, some of them when they find warm SST, they can develop it and provoke some of this damage that is crucial for Cape Verde. Then you go forward. This is as well some of the impacts of stream rain events in terms of urban and rural impacts. So you can see we have some flooding, and in this event we have we have been two woman losses, and this is like some of the impacts of these tropical waves when they passing through to Cape Verde. You can go for. And here in our story trend, you can see this is a station for Praia. You can see we have an increase in the extreme daily rainfall events up than 80 millimeter. So we have a 50% increase in rainfall with flood risk in these last 30 years. If this is a consequence of climate change, we don't know yet, but but you can go forward. You can see because you can go forward. You can see because in Cape Verde we already experienced climate change. You can see here in the average air temperature, we see a clear increase of the temperature like 0.3 degrees per decade. And in the last four decades, we have an increase like one degree in the temperature of air in Cape Verde. You can see on our left, because the months in Cape Verde that we have where the temperature is more warm is in the summer season, and that is compatible with the passage when you have the tropical waves. You can go for, and here we can see because is the evidence where we are experiencing climate change, because in the minimum temperatures we have more increase about 0.3 degree, indicate there is an effect when you have, this is when the greenhouse have more effect in the night when we don't have solar radiation. So you can see the nights warming up faster in Cape Verde. That is consistent with what we're observing about around the world. You can go for. So in terms of precipitation, we can see because the months where you have more precipitation Cape Verde is in the summer season, and so it starts at July, ends in November. But here we don't have it's not possible to identify the trend here. But what we can see, because we have years where we have wet seasons, and other years we have dry seasons. So it'll be alternating in those. You can go for. In terms of mean sea level, we can see we have an increase in the mean sea level about 32 millimeters per decade. And particularly if we do a zoom in Cape Verde, we can see in our region we are being affected by the effects of climate change that increase the sea level, the mean sea level. Then you can go for, and this increase of sea level, it has a particular consequence on when we have like storm surge events that aggravate and we're having some episode of flooding, of coastal erosion, and damage on the properties. Okay, can you go for? And I tried to bring here a projectile to go until 100 years, that we see if you follow the high emission scenario, we see in the region of Cape Verde, we'll have an increase of the sea level in like 1 meter. So it is important to us to follow a sustainable scenario, so we don't have to experience this increase of sea level raise. Okay, you can go for. And as well for the sea level, we can see for the temperature. If you follow the high emission scenario in this region in Cape Verde, we'll have an increase of 5 degrees Celsius in the temperature and a reduction in the annual precipitation. And these conditions of increase of air temperature, you can go for. It's compatible with the warming of the tropical Atlantic sea surface temperature, that will experience an increase of temperature that is noted every year and every decade. And this condition you can go for, and this condition will be more compatible with the situation that caused Hurricane Freddy in 2015. So here we are bringing here the most impactful extreme event in Cape Verde in the last 100 decades and 100 years. That was Hurricane Fred, and it was a particular special event because in this day when where Fred formed, in that particular day, the SST anomaly was we have positive anomalies in the region of Cape Verde that we can see. These lines here was a tragedy of the Hurricane Fred that possibilitated to move across to Cape Verde. So it was a particular event with particular special situation that possibilitated to across Cape Verde Islands. And this event, we don't have evident human losses, but we have a damage like $2 million on properties. Then you can go for. In that time, we have some issue in our forecast because we don't have good instruments to do it. But now we're counting with two models, two regional models that we have. That is operating operating operational model, and we have here an example of this schema we use it with the SMWF is the forcing model, and then we have two domains. That is a 3 kilometer and other is a 1 kilometer, and then you can go for, and so this model is how I say it is an operation model, and we have here this web page that all the meteorologists can use it to help on the forecast. So it will be an advantage when we have this extreme events. So it right now it is a good way to use it. You can go for, and other model that we're counting here in the institute is a seasonal forecast model that we call ETA model. Here I bring an example of forecast of seasonal forecast of 2000, maybe 2003. Then we can have an idea how would be our seasonal our wet seasonal forecast. So it helps a lot to know how to expect in the wet season. Then you can go for other challenge for us in Cape Verde is to implement the impact based forecast, because what we have experienced with Hurricane Fred and other extreme other events is because the local population don't know how to react when they receive the forecasts of extreme events, and they don't know where will be the most impact areas. So it will be important to us to start working with impact-based forecast. You can go forward, and because we are working on a vulnerability map. So this will help a lot the local population to know when we have these extreme events where they should expect the most impact zones. Then you can go for. So other challenge we have here is in terms of human resource. We don't have. We are expecting to have more meteorologists here for helping on the institute, and as well as a marine observation station and the launching of balloons because of terms in resource and the expensive cost of these operations. I think in the future we can surpass in this these barriers. And as well, we have to promote and train session and workshop for the stakeholders so they can better interpret the information on potential impacts in forecast bulletins. Then we can go for, okay, so here we see some of the institutions that the institute has the how do you say, the some resource to help on our focus. And then we can go for, and you can go for, and one more.
Carlos, did we lose you?
No, he's not audible. His mic is on.
He's on, but I don't know why.
Okay, let's give him another minute, and then if he can't get the contact back, we can have him come back at the end of the other sessions. Okay, he's back.
Greg, I have been are you listening? I have been disconnected. I have some problem issue, and I hope you guys understand. I'm not fluent on English, and I understand you understand what I have to present.
Okay,
So
tell us about the last page on social media. What did you say?
About what?
You showing us this page on the communication, YouTube, WhatsApp. What do you want to say about this?
I want to say, because we are now experienced to try to use this new type of social media to disseminate the products like Instagram, YouTube, and WhatsApp, because we have seen it is an easy way to make sure that the information go to the population that usually people don't see the news or the news. The old now are not using the old social media, social communication. So we are seeing it is important to us to use this new era of social communication. Okay.
Yes. Okay. Carlos, is that the last time? Okay, Carlos, thank you so much. Can you join us tomorrow for discussion?
Yes, I can.
Okay, because we have many things to follow up on what you say. You you say you need more human resource. You mentioned the issue of the upper air soundings. So tomorrow we need to return back to the discussion of infrastructure, human infrastructure. You mentioned a good point about the need to communicate better with the public. So we need to come back for all the countries and discuss some ideas around this. We need solutions, right? So we need to all think together and how to build a connection. So anyway, thank you for your talk. Very good. Please tell my friends in Cabo Verde, Esther, and all the team I say hello there. And tomorrow
I think they are online.
Okay. All right. We're fortunate to have Miss Olumide Olanwen.
Olaniyo.
You know, it seems like a Yoruba name, no?
I'm
Well,
Yoruba.
okay. So I need to
Yeah.
learn Yoruba. Okay, she is the general manager for air quality unit, weather forecasting at the Nigerian Met Service. And she has many years of experience. She says over 20, but she looks more like a high school or a college student. And she's currently working on a PhD in the Department of Geography at the University of Abuja. And I have had the honor of knowing Olamide for the last few years, and we have done quite a bit of collaboration around dust forecasts. So, and she's part of a larger group that we've been meeting for several years. So, it's my pleasure to actually introduce you, and we look forward to your presentation. And if you need us to share, if you
Okay.
have, yeah.
Okay. Yeah, can you share it from there? I'm finding it difficult to share from here.
Okay, so I'll put that up now, and then we'll share your presentation.
All right.
Just tell me when to move forward, and I will move forward.
Okay.
You're on.
Good day, everyone. So I'll be presenting on flood in Nigeria, the impact, challenges, and forecasting extreme rainfall events. Can you move on? There are a lot of causes of flood in Nigeria, but the most important cause is torrential rainfall that we have been experiencing in the recent time. So you can see the effect of flood. This is the flooding of 2019, especially people that are along riverine areas. Can you go ahead? So we have different kind of flooding. We have coastal flooding, river flooding, flash floods, and urban flooding. And flooding that are... Can you move forward?
Okay, you might need to just do audio because your video. Sorry, yeah, just do audio. Your voice is breaking sometimes. Can you hear me? So we won't get to see you, but we still.
Okay.
Okay, so here we go.
All right. So we can see the network of rivers in Nigeria. We have a lot of rivers, and we have two main rivers, River Niger and River Benue. River Niger and River Benue, they have lots of tributaries that flows to the southern part of the country and enters to the Atlantic Ocean. So people that are around these rivers, and they are prone to flooding when we have high rainfall. And we can see the Lagdo Dam. It's along the River Benue, but Lagdo Dam is located in Cameroon. So whenever we have heavy rainfall, the Cameroonian authorities, they open the dams, but Nigeria does not have dams to contain the water. So this water will cause a lot of damage and devastating flood to the communities along the river. Can you go ahead? Also, people in the coast are also prone to this coastal flooding, especially in Lagos, where we have about 23 million people. Yeah, Lagos is very vulnerable to flooding because of the low-lying coastal geographical feature, and there is weak flood control on infrastructure. And then also we have problem of sea level rise and tidal surge. Can you go ahead? We can see the impact of flood in Nigeria. This is showing from 2010, the number of people that are displaced, the number of people that died. And this has become a yearly event now. Every year we record devastating flood due to intense precipitation, and lots of people are displaced every year. Can you go ahead? In 2022, apart from the one that we experienced in 2010, we had the worst flood ever. And this caused lots of deaths and the displacement of people. Also in 2023, according to Nigerian Emergency Management Agency, as at October of 2023, 157,000 people were affected nationwide and 68,000 displaced due to the flooding. About 13 states out of 36 states of Nigeria were affected by the opening of Lagdo Dam due to excessive rainfall. Can you go ahead? So these are the impact of flood. Millions of people are forced to relocate. It destroyed businesses, polluted water resources, increased risk of diseases, and destroyed farmlands. Those are the things that we are facing in Nigeria, and it's yearly occurrence. Can you go ahead? So this is one of the causes of this flooding. Highest one-day rainfall amount that is more than 100 mm. In some cities, we have precipitation more than 100 mm in a day. Like in Yenagoa, the last city on the picture, we have 203.4 mm on a particular day. The total rainfall, the annual rainfall of this city is about 4,065 mm, but on a day, that is more than 5% of the annual rainfall falling in a day. And this can continue for several days, and the result is devastating. Can you go ahead? So these are the fossil functions that are affecting rainfall variability in Nigeria. We have intertropical discontinuity, African easterly jets, African easterly waves, easterly jet, tropical easterly jets, Sahara, thermal low pressure systems, wind at different levels, sea surface temperature, dust topography, extratropical influences, monsoon depth, monsoon flux, cape. Those are the forces that are affecting variability of rainfall in Nigeria. And it's good we understand all these features so that we can predict these events accurately. Go ahead. So this is the schematic view of West African monsoon. Most of the rainfall in Nigeria are from West African monsoon. And these are the features that I've mentioned above, that I mentioned earlier, that are affecting precipitation, rainfall in Nigeria. You have TJ, I've mentioned them, but this is the schematic, a picture of how they interact with each other. Can you go ahead? So why is it important that we understand these components of West African monsoon system? Because the general circulation models and the numerical weather prediction models they have poor skill in capturing West African monsoon. And understanding the causes of rainfall variation is crucial for both local ecosystem and rainfall-fed agriculture, because most of the farmers in Nigeria, they depend on rainfall for their farming. And a more accurate operational weather forecasting is very crucial in Nigeria. because of the rainfall-fed agriculture that we practice. Can you go ahead? So this is the intertropical discontinuity. It moves latitudinally from January. This is the position in January. This is typical. This is in February, this is the position. And this is the position of the ITD in August. That is the highest position. And after August, it starts moving southward again till it reaches its least position in January. The position of the ITD is depicted by dew point temperature of 15 degrees Celsius. And the seasonal variation of ITD is responsible for duration of rainfall. Can you go ahead? Another important feature of West African monsoon is the mean sea level pressure system. The Azores high pressure system and the St. Helena pressure system. During the winter, the intensification of Azores brings in dust into the country. And during the summer, the intensification of St. Helena high pressure bring in moisture into the country. The more intensified this pressure system, the more moisture is brought into the inland parts of Nigeria. So the interaction of this pressure system is very crucial in determining the amount of precipitation that we have. Go ahead. Another feature is African easterly jet. It's always positioned around 700 to 650 hectopascal level. So the forecaster needs to be able to identify the position of the TEJ, and embedded inside the TEJ is the African easterly waves. All this modulates the amount of rainfall that we have in Nigeria. And the jet is formed by the strong south temperature gradients in the low level between Sahara and the Gulf. It's only in West Africa that you have temperature increasing latitudinally. And this has given a peculiarity to the formation of weather over West Africa. In all other parts of the world, temperature decreases latitudinally, but in West Africa, temperature increases latitudinally. So this is very important in forecasting rainfall for West Africa. Can you go ahead? So the wind at different level also is very, very important in forecasting precipitation. At the low level, wind convergence, it's condensation, it's the formation of convective system. But at 200 hectopascal level, there must be divergence for this convective system to occur. If there is no convergence, if there's no divergence at the upper level and convergence at the lower level, the MCS will be short-lived, may not even form at all. So all these features are very, very important to take note when we are forecasting weather over West Africa. Go ahead. Another important feature is the incursion of mid-latitude trough over the West Africa. There is this extratropical influences of middle latitude trough that pushes ITD even during the winter. During the winter, we can have intense precipitation. That is during the dry season of mid-latitude trough across the northern Africa. Can you go ahead? Other driver of interseasonal rainfall variability are El Nino Southern Oscillation. El Nino occur when the SST is above normal over the 3.4 in the Pacific Ocean. So the impact of El Nino over Nigeria is that we have precipitation that is below normal. But when we have La Nina situation, when there's La Nina, we have rainfall that is intense. The rainfall increased when we have La Nina situation. Like in 2012 and in 2022, where we have great flood across the country, the precipitation was more than normal due to La Nina. And then we always take this into consideration when we are doing our seasonal rainfall prediction, so that we'll take into consideration the effect of El Nino Southern Oscillation. And another major rainfall variability feature that we also use is MJO. When MJO is passing across West Africa, it's always intensify the precipitation. So we consider that one too when we are doing our forecasting. Can you go ahead? And most of the precipitation that we have, they are in form of mesoscale convective system, thunderstorms, squall lines, and all these features can be seen on the satellite imagery. And so we take note of all these and we use them to do our forecast. Can you go ahead? So these are the operational practices that we use. Please go ahead. So for our operation, we have a model called Cosmo from DWD, Germany, and it has resolution of 7 kilometers. We use that one for our forecast. And there are a lot of variables that we assess from Cosmo model: pressure, horizontal wind, vertical wind component, temperature, cape. It has lots of components that we use. And it uses adiabatic processes. And so we also see features like radiation, turbulence, cloud formation, and precipitation in a Cosmo model. Now we want to, Cosmo model now has migrated to Icon, and that is what we are going to be using very soon. But right now we are still using Cosmo model. We run it once in a day, and it gives 3 hours products that we use for our forecasting. Can you go ahead? So this is component of Cosmo model. Resolution is 7 kilometers, and it covers West Africa. So we're able to do forecast for Nigeria. We also do forecast for Liberia and Sierra Leone. This is WMO mandate for us to do to help our sister nations, Liberia and Sierra Leone, in their forecasting. So we use Cosmo model to do that. Can you go ahead? So other forecasting tools that we use is we use preliminary user of MET application, Puma. Puma is from Meteo France. So in Puma, we can access lots of features. We can access wind, satellite imageries, divergence. You can see all the components: divergence, total precipitation, total cloud cover. We can access lot of parameters that we use for our forecasting. Go ahead, please. Also, we use product from Climate Prediction Center, NOAA. We get lots of, so that we can compare the product from NOAA. We compare the product from ECMWF, we also use product from Meteo France. So all this we put together to produce our forecast. Go ahead, please. Can you go ahead? So these are the satellite imagery that we also be using ImageSat satellite imagery to detect the speed of storms, their formation, their dissipation. And when we study this, we know the speed of the storm, and we can say, okay, in the next 1 hour, this storm will get to maybe Abuja, and we can use it for nowcasting and also for long-term forecasting, maybe 24 hours forecast, 48 hours forecast, and 2 hours forecast for aviation purposes. Go ahead, please. Go ahead. So this is a case study of evaluation of Cosmo output for rainfall events of August 21 to 26, 2017. Please go ahead. So this is the track of the storm on this particular day. And we can see a sequence of mesoscale convective system that passed over West Africa. Along these trajectories, there are lots of flooding reports along this trajectory. Can you go ahead, please? And this particular case resulted in a hurricane, the 5th most devastating hurricane in US. This particular storm from August 30th and 12th September resulted in that. I cannot remember the name of that hurricane now. Can you go ahead? And about 100,000 people were displaced, over 4,000 homes destroyed in Nigeria. Go ahead. Almost 3,500 affected and 10 deaths in Guinea. And after this storm passed over the or the coastal area of Guinea, it moved into the Atlantic Ocean, gained more energy, and become a very devastating hurricane that landed in the US. Can you go ahead? Go ahead, please. So this is observation, the Cape. We use Cape to investigate whether Cosmo can really capture this storm. That was after the events. And we use ERA interim as the observation. And we can see that Cosmo can capture the events, like the Cape that was associated with that event on that day. And you can see on the other day we have the ERA interim, and you compare what Cosmo predicted, and we can see that it's able to capture the Cape that is associated with that event. Can you go ahead? Also, the rainfall that was experienced, this is the GPM observation, and this is what Cosmo predicted. And we can see that the position of the precipitation were not really captured by Cosmo. There is a lag in the location of the storm. So we can use this one, the bias, to correct the Cosmo model so that it can give us a more accurate. That is the reason why we always do investigation to see how our model is performing. Go ahead. Can you go ahead? So the result shows that the reproducibility scale of the model in predicting atmospheric dynamics does not transform into predictive scale of producing rainfall. So forecasters will estimate the likely areas of every rainfall when we determine the bias of the position. But we can also see that Cosmo can determine the position of AEJ, the Cape, and other features. But the position of the rainfall will always correct the bias and use it to correct the model. Can you go ahead? So this is another study of post-events. This one is we use moisture flux and Cape to see whether we can use those features to predict extreme rainfall events over Nigeria. This one was done using storms that occurred between 2010 and 2014. And then we use precipitation that are above 50 mm over selected meteorological stations in Nigeria. So we'll look at the moisture flux and the Cape 3 days before and 3 days after the event to see their characteristics, so that in other future events, when we see this signature, we can identify extreme weather events. Go ahead. This is the result. This is the Cape on 1st to 3rd of July. And we realized that the Cape that can encourage convective system over the southern part of the country is about 800 kilojoule, while over the northern part of the country, the Cape must be as high as 300. So the situation for precipitation over the south is really different from over the north. Go ahead. And also the moisture flux also increases 3 days before the event and decreases 3 days after the event. So when we look at the horizontal moisture flux divergence, and we'll see that it's increasing, then we'll take note that there is probability that this event is going to be an extreme event depending on the amount of the horizontal moisture flux divergence. And also we can see that it's because the unit of the horizontal moisture divergence is negative. That is why you can see how the plot looks like. But for Cape, it is positive. So you can see that it increases gradually until the day of the event and decreases after the day of the event. So when you see a Cape increasing from day 1, day 2, day 3, and you will be able to say, okay, this is an indication that, and depending on you can see that we have up to 3,000 joules per kilogram of Cape. So we see that it's possible, there's possibility of extreme rainfall. So those are the indicators that we use to predict extreme rainfall events. Can you go ahead? So the results show that moisture, convective instability, and vertical wind shear are very, very important to contribute to rainfall events over Nigeria. But the most important is moisture. Even when you have very high Cape value, when you have convergence, divergence, and we don't have enough moisture, there is probability that the event may not be as extreme as you want, as you feel. But the important thing is the movement of moisture from the Atlantic Ocean inland. And another thing is that we have some high grounds over the country. All those high grounds like Jos, Mambila, Adamawa Plateau, and we have Cameroonian Mountain too. they are very good source of moisture divergence, and they serve as lift to aid convention. So they are referred to as fertile ground for convention. All those things we take into consideration when we are predicting extreme rainfall events. Can you go ahead? So this is our forecast. We always produce impact-based weather forecast. So when you do the forecast, people that are going to be affected will be put in the forecast. The impact of the events, the amount of precipitation that we're expecting, the impact of the events on people, we're going to put it there, and we'll explain everything so that the users can understand what we are talking about. So all these forecasts, we put them on social media. We put it on Facebook. We put it on Twitter, or X as it's called now. Then we put it on YouTube. Then we'll send it to various users. We have a collection of email addresses of users that use the forecast. So we'll send it to them after the forecast. And when we have alerts of extreme weather events approaching, apart from this daily forecast that we'll do, we still send alerts to them to intimate them that we are expecting rainfall events or event that's going to cause flood, so that precautionary measures can be done prior to the event. Can you go ahead? So this is heavy rainfall forecast, and areas in green indicates very light rainfall, and areas in yellow indicates very high rainfall, and these are sent to the people that matters, the hydrological services, the National Emergency Commission Agency, and people that will need the forecast. We have a lot of email address. I will send it through email address. We'll post it on our website, and we'll post it on our YouTube channels, and so that people can really get the information. We have email addresses of radio stations, television stations that they broadcast this. On our national television, we still send it to them, and every 9 o'clock in the evening, at the end of the news, they broadcast the weather information. Can you go ahead? But with all this, we still have challenges in because of these factors. For us to effectively do the weather forecasting, we have issues with data scarcity. We don't have much land stations that will be very good for us to have. We mostly use satellite data to augment all these land stations, and then there's limited skill in data analysis. We need to build capacity for meteorologists, and then we have limited institutional support and funding. And among African scientists, there is poor collaboration. And even among the meteorological agencies, there is poor collaboration. And also we lack supercomputing facilities. And the the dissemination of researches among African scientists is also another challenge. And then supporting policies and capacities for the users to understand and apply the information that are given to them. As much as we are trying to make this information understandable to the users, but we still have challenges of users understanding the meaning of the forecast. Can you go ahead? So that's the end of the presentation. Thank you for listening. So if there's any question, I'll be glad to answer them.
Do we have any questions in the chat? I have a question. I'm going to go back to this slide of yours. It was one of your overview slides. This one.
Okay.
This looks pretty devastating.
Yeah. Yeah, that's what we'll face every year. For the past few years now, it has been annual events of intense precipitation and then opening of dams, and people along the riverine areas are mostly affected. And they are mostly vulnerable people that are poor, that build their houses along the river, and then they are mostly affected. You can see the flood water will take over the whole building. You may not even see roof of some buildings during that time. So they will be displaced. They will now be camping them in camps, displaced people camps, where they will stay until the water recedes.
Do you do river forecasts? Do you like have automated like gauges along streams that you can see in real time to know how bad those rivers are flooding or streams? Or if they're going over their banks?
Yes, there's another agency that is in charge of that. So the Nigerian Meteorological Agency is not in charge of that. But Nigeria Hydrological Agency and some river basin authorities, they do that.
Do you two collaborate on this kind of thing, where the rain fell, how heavy it was?
Yeah. Yes. Whenever we do the forecast, especially when we do the seasonal climate prediction, we invite all the agencies that are involved in dissemination of the forecast, and they come and will tell them about everything. So the Nigerian Hydrological Agency now will do the flood forecast and will share it to people so that they can prepare.
We have another question, and we also have a question online. So this is Bill Parker. He's actually one of the meteorologists in charge in Jackson, Mississippi, here in the U.S. So he has a question for you.
Okay.
And so this morning, most of the presentations have said that, you know, there's a lack of human resources. There's a lack of, I guess, people who are in the meteorology field over in Africa. And so my question is, how good is the government support for the career of meteorologists in Africa? And based on, let's say, US dollars, what does a meteorologist normally make, you know, in Africa? I mean, is there a desire for young people to become meteorologists in Africa?
That's a very nice question. The government always try as much as possible to support, but the support is not enough. And in terms of the salaries, I don't think it's something to write home about for meteorologists, especially people that are it's not much. It's not much. It's not much. So it's just the passion of people, of meteorologists, that they do. I can say of Nigeria, I cannot say of other African countries, but in Nigeria, the entry level, it's not even up to $100 per month.
Month?
$100 a month.
Let me do the calculation.
Hi, Greg.
Okay. It's not much. Maybe a little above 100, above, but it's not much.
Wow.
But as you go ahead in your career, your salary increases. So with time, you earn more.
Martala, you have a question.
Yeah, I have a comment. I think I need to commend Olumide for this exciting presentation. And just a quick response to some of the questions you earlier raised. She's absolutely right with respect to some level of synergy between NIMET, NISA, and quite a number of other agencies. I think I've participated in 2 or 3 years events where Emergency Operations Center has been activated, where all the key stakeholders related to emergency in the nation, including multinational agencies, are called upon. And I think in one of the events, we have activated the UN Charter on the UN Spider to actually look at the issues relating to flood. But to put it straightforward, is that at the moment in Nigeria, we don't have a real-time flood forecasting system, But I think what NIMET is doing, they do their bits, but NISA is responsible for forecasting flood, which I think they still have challenge with the gate stations across the country. The gate stations are on the major rivers, the Niger and the Benue rivers, and then other smaller tributary that can create the trigger for the flood to happen on the larger basin are not well gauged at the moment. And I think that might be an entry point for us to take a look at. Thank you very much.
Okay. Well, I think this is a discussion point again for tomorrow because Nigeria has what, 200 million people?
Yeah, more than that. I think right now it's 220 million.
That's a lot of people to protect.
Yeah.
In the climate change regime.
Yeah.
The last question is, how many meteorologists does the NIMET have? I mean, I would assume is a good number. Is this true?
Yeah, I think we should be up to maybe 300.
Okay, that's not a good number.
It's not, the problem is like the economic situation of the country. Many meteorologists they have left the country for a greener pasture, and then it's just few that is remaining. So, and the few that are there, they are not so motivated, It's just when you have the passion to do the work, like me, I'm so passionate about this work that I derive pleasure in doing it. Some people are not so passionate. so that's the problem. And many people have left the country.
I thought you were going to say 3,000, and you said
no.
This is very problematic in the climate change regime.
Yeah.
these numbers that you show are not, they're not minor. They, 1 million people being displaced is massive number.
Yes.
Well, we need you tomorrow for the discussion. So
Okay.
I think we have our 2 speakers back. But first we have to see. We have Andre Kamga, are you here? Or Riyadh, are you here?
Andre is here. Riyadh is not.
Yes, Andre is around.
Andre, where are you?
Here I am.
No, I haven't seen you in many years. Even on social media.
Yeah.
Okay, so what
you know,
do you need us to give your presentation here, or can you share your screen?
Let me try to share the screen.
And while you're trying to do that, I will introduce you. So this is Dr. Andre Kamga, and he is the Director General for Ahmad in Niamey, Niger. And I've known him since he was a graduate student a long time ago, and we shared a similar mentor from Cameroon. Since that time, he's become very big, Andre has, and his main area of expertise is in predictability of weather and climate, and he provides the overall leadership for all the operations there. So Andre, we're gonna have you push forward.
Good. So thank you so much for this opportunity to discuss these burning issues related to, let's say, the early warning for all on one hand, and climate action, particularly adaptation and resilience related activities. So in the work that Ahmad does, we have 2 departments, one weather watch and prediction, and the second one, the climate department. Having been involved in the past in this concept of seamless forecasting, we have tried over the past few years to get it real. That is building what we call the next generation of forecasters in Africa, who should be able to operate both as weather as well as climate forecasters. You will see in the upcoming slide, how this can be important, particularly for weather forecasting of extreme events. They need to understand the climate environment under which those extreme events operate. So this is just a short one slide on Ahmad. So it's a continental body established through a resolution 540 of the UNECA Conference of Ministers. UNECA is the United Nations Economic Commission for Africa. Following the drought of the 70s and 80s, particularly in the Sahel. Please, when I say Sahel, for us, it means from Cape Verde to Djibouti as a straight band covering many regional economic, at least 3 regional economic communities. So the center is operating in Niamey since October 1992. After a set of assessments, UNECA in 1996 refocused Ahmad's mission on 2 things. First, to operate as a continental weather and climate watch center for Africa. And this meant operating the following functions: monitoring, forecasting, and early warning for drought, floods, and other extremes. The second element of the mission is to operate as an institution of excellence for the applications of meteorology for sustainable development. So here we have programs on capacity building. The most famous one is called on-the-job training and secondment of forecasters from national meteorological and hydrological services. Then we have development of methods and tools, as well as new products, and contribution to the implementation of global weather and climate programs in Africa. We promote databases and support research and innovation. As part of the continental operational mandate, the ACMAT today is a WMO designated regional climate center for Africa. And this responsibility was given through a resolution of the WMO Congress in May 2015. The center, after demonstration, of course, and the center is now a continental multi-hazard advisory center since October 2022. And this second function is within the African multi-hazard early warning and early action system, which is the Africa flagship program for implementation of the early warning for all initiative. So this is the, let's say, a picture, two pictures. One on your left is the status of regional climate centers. So these are structures established through the implementation of WMO regulations. And it's an institutional infrastructure at the regional level to support countries deliver better climate services. As you can see, over Africa, we have in red, those are WMO designated centers, meaning that they have demonstrated their capacity on 4 key functions: climate monitoring, long-range forecasting, data services, and training, and are therefore considered as regional centers who should contribute to facilitating climate services development in the countries, and particularly the implementation of the global framework for climate services in Africa. You have other developing centers, such centers in Central Africa, Southern Africa, and the Indian Ocean. So one of the functions of ACMAT as a continental body is to promote these other centers who are not in red, so that in the near future, Africa has all these blue become red over Africa. Then we have on your right, in October, as I said, 2022, as part of the African multi-hazard early warning and early action system. So ACMAT is the continental center providing advisories up to 5 days or more ahead on these hazards: floods, heat waves, drought. And then this is used to generate continental watches and then disaster situation reports that are discussed at the Situation Room office base at African Union Commission headquarters in Addis Ababa. So these Situation Room then will call, when it is needed, international assistance, humanitarian and other disaster organizations, including UNDRR, to support response and preparation for these disasters. So one of the famous, let's say, achievements of this initiative was related to the visit of the Mozambican president in Addis, who then left quicker due to the level and the intensity of the expected cyclone, which was going to hit Mozambique in the following days. So one thing to do first is the detection of these hazards. So what you have there is the status of our synoptic network. And this is the in situ observation of precipitation that we collect every day in this network, and we can then detect here locations where we had heavy rainfall. In this case, here in red. Then we have on temperature here over, let's say, the past 10 years, we have been working with WMO to issue a state of climate report for Africa. So this is the state of temperature and the trend on temperature since 1900 until recently over Africa from that report using a series of data sets. So I put it basically to let you see the number of data sets that are used to appreciate, let's say, the trend in terms of temperature and the warming levels across Africa. We still have a challenge to have such products generated at the country level because of the limitations in terms of capacity, internet bandwidth, and computing power to access all these data sets and process them properly. So it is something that we are promoting and putting some effort for the regional centers I've just mentioned to be able to generate this and supporting countries. One other limitation of this is that it's a continental view of temperature increase. We basically need at the city level this information. And interestingly, the IPCC have put emphasis now on climate change and cities. So we are having more support now to go in those details that really matters. This is another product on extreme, looking at the number of days where we get the warmest 1% of the record in Africa. As you can see in this data set, 2016 was the year with the highest number of days with mean temperature above 99%. And you see it is 14 days in the record. And here, this indicator is particularly useful because on one hand, it is not just temperature, it is the number of days with extreme temperature that you see move from about 2 days per year in the late 70s to actually 14 days in 2016. So this is something very much important to be done at the local level. So in cities, to actually have get an idea on the need for commodities like energy, electricity in particular, during the warmest month of the year, particularly in those mega cities where we today have a lot of power brownouts. So this parameter in particular has been found very important And we need capacity building in Africa for meteorological services to generate this for use by particularly the energy sector in the countries. This one is the trend, basically the trend on temperature. I'm mentioning, let's say, temperature more than rainfall because in the past, let's say, past decades now, in addition to floods and drought, heat waves is a strong hazard that is actually having devastating impact in Africa, but most often not reported on effectively. So as you can see here, Africa is the warming trend per decade in Africa is quite high in the recent 1991-2020 period. So this is the temperature anomaly just for 1 year, highlighting actually North Africa where the rate of warming is quite significant. As you can see here, North Africa has a warming rate of about 4 degrees per century. So this is what we are expecting at the global level in 40, 50 years, which is actually already occurring in North Africa, 4 degrees per century as warming trend. Now, as you saw in the presentation by Nigeria, 2020, you see here 2020, where here we identify a parameter called the percentage of grid point in over African land masses where daily rainfall is above 90th percentile. And it shows also a clear trend, significantly positive trend, where we move in the early 80s. So this is when the satellite data became, let's say, useful. We move from about 4% of African land masses hit by heavy rain during the year to 40% in 2020. I should say that 2020 in some country like Niger, where we are, about 2% of the total population were affected by flood that year. And so this shows that for precipitation as a parameter, we may just see variability, sometimes multi-decadal variability. But when we take extremes, there is clear signal of change. This is, yeah, we have already gone through this one. Now, as you saw in the mission of ACMA, drought, floods, high temperatures, but also cyclones. The main basin of interest to us is not the Atlantic basin, but it is the Southwest Indian Ocean basin. And you see here in a couple of years ago, I think 2021 or 22, WMO adopted a resolution, a famous resolution called Open Data Resolution, which provided us an opportunity to access 6 global models, operational ones, as you can see here, from ECMWF to the Canadian model. And then we are able to actually track a cyclone up to more than 5 days ahead. So this is one cyclone that hit the basin in February 2023. as you can see, only the UK Met Office system was indicating more than 5 days ahead that the cyclone would cross the channel. And this is actually what happened. And the message there is, given these disparities at medium range on the model's outputs, it is very important to collaborate with the meteorological services, because in this case, our collaboration with Madagascar help us to understand several days ahead, before that, from their experience, when the cyclone is at this latitude, at this time of the year, the likelihood that it crosses the channel is very high. So what we did was to just process the mean sea level pressure data for the week around this period during that time, and just realize that the lowest pressure on average is in the channel. And this helps us to actually consider that this Met Office forecast is not just an outlier, that it is a real possibility that effectively happened. And we all know what value an outlook 5 days or more ahead on the track of a cyclone. So you can say 5 days ahead that this cyclone, which is here on the 17th, would cross the channel, how important this information can be to countries like Mozambique. And it is also an opportunity to mention that we have on the web today most of these products, but research and operations should really team up to actually do these studies to understand how best we can optimally use this information and provide what is really necessary to alert the population, particularly at medium range, because we are saying that having those warnings a few hours before the event, they'll have very, very little value. So this is the observed track of that cyclone, and this is the forecast made from 17, that is for 5 days ahead, with the Met Office system actually being able to at least tell us that this system may cross the Mozambican channel. So this one is just to show you as you can see here, so this is a diagnostic that we generated based on interactions in the briefings with the Madagascar Met Service. And you can see that on average, climatologically during that period, the lowest pressure in the basin is within the channel. So this is what certainly attract cyclones. And at medium range, in this case, only the Met Office system was able to capture the event. So this is just a second case. Now, in the operations of the Continental Multi-Hazard Advisory Center, you have here a case, so we issue vigilance products. In this case, this is an outlook for heavy rainfall over eastern part of Niger, which is then verified with a product called Rapid Developing Thunderstorm, which is generated by processing satellite data merged with very short-term forecast from the APEJ system, and help us locate, detect, and anticipate a few hours ahead the evolution of storms. And this map is just the observations indicating what was recorded over this area. So in this case, this flood event was anticipated also several days ahead. But in this case, given as the Nigeria presentation mentioned, given the limitations at the interface between the the hydrology, and the civil protection or disaster management at country level, we don't always benefit effectively from this information. So it is one area in the African multi-hazard early warning and early action system on which we are working with AUC and UNDRR to actually strengthen this interface. We call it user interface on weather and climate services for disaster risk reduction. Now, this is a global initiative we had with WMO, which have established a coordination mechanism to support particularly these countries with a lot of refugee camps. The Continental Multi-Hazard Advisory Center provides every week a map locating expected heavy rain areas, and it is used by UNHCR to prepare its operations over that part of Africa. Okay. Now, this is another important product that it needs improvements. So it is the start of the agricultural season. In this case, we did it for 2020 and 2021. I just want to raise your attention on the coast and the Sahel. So in 2020, if you remember, 2020 was one of the significantly heavy rain year with floods. So it was characterized in the Sahel by most often late start of the rainy season. And it is a behavior that we are seeing quite often now. So the season start late, and you have heavy downpour at the core of it, leading to significant disruptions in the agricultural sector. As you can see here, in 2020 we had this in the case of Niger, for example, and in 2021 we have now almost all the stations we monitor in Niger and northern Nigeria in 2021 had late start of the season. And this actually was interpreted at the end of the season as drought, with the growth rate projected in late 2020 for 2021, which was positive up to 4 or 5%, becoming negative. And this product it was generated following a few years of analysis after discussions at the user interface platform on climate services for agriculture, where clearly farmers indicated the difficulties of using what was then operationally provided as information on onset based on the so-called Sivakuma method. So this user method developed in the tropical regions of Australia and adjusted it to Africa. And it is today used to monitor the start of the agricultural season all across Africa. So in terms of, let's say, recommendations, things we may discuss in the days ahead, we have, in terms of institutional infrastructure, a system well structured at the global level with the World Meteorological Centers. There are almost 6 or more of them today. And we have at the regional level, the regional climate centers and regional specialized meteorological centers for severe weather. So, and this is where investment is really needed to undertake research needed to take advantage of the global forecasting products that we today have, which are both deterministic and probabilistic, and need validation in different regions across the world, including Africa. And this effort will help us generate outlook, advisories, watches, useful guidance several days ahead of extreme events, and support our briefings, ad hoc briefings when significant hazards are expected with the countries, not only with the Met offices, but also with the disaster management agencies. And today, Ahmad in his room is working with the two institutions in each country, both the Met Service and the Disaster Management Agency, to build anticipatory action plans and then support their implementation. So that is one key element that we have here in the programs ahead. And I'm thinking of the possible implementation of the US Prepare program, where we could put some resources on strengthening this ad hoc briefings several days ahead of these events, and then pushing forward to the Met offices to have their 12 6-hour ahead warnings, and then making briefings, post-event briefings, to learn, listen, and improve. Then secondly, we have the need within the Met community to further operationalize the seamless process, merging seasonal, sub-seasonal, and medium-range forecasts, and using this institutional infrastructure at the regional level, composed of regional climate centers and regional specialized meteorological centers for severe weather. Then we have at the nowcasting level, as you heard me talking about rapid developing thunderstorm product, it is a satellite application facility output developed in Europe, but until today, not very much used in the operations at the national level. So we should put effort on further developing it and making it use at the country level. And on the tech training, sometime merging the forecasters and disaster risk reduction experts to create this emulation and the idea that these two communities belong to the same home. Then supporting countries to establish and operate their national early warning information system center. So here, it's again to put together the meteorology and disaster risk reduction around an information system. So a common database or interoperable database basis between the two communities, and facilitate access and use of our vigilance watches and warnings. We have in the concept put a lot of emphasis on warnings, but vigilance and watches, outlooks also, should be put together in the same context to give the warning the value it deserves. So as I said, indicating that a heavy rainfall is coming in a few minutes or even in a few hours will, in the case of Africa, has little effect and will sometimes even not reach these communities. It is very important to support generation of outlook, vigilance, and watches also. And then the last is support measures to reduce risks or exploit opportunities through forecast-based integrated emergency planning, budgeting, financing, and implementation. We have been doing this separately. On one hand, meeting together to undertake emergency planning, doing the budgeting at the country level on the other hand, without taking into account the emergence of these hazards. And sometimes financing, providing finance without having a window to address the hazards that a country may face during the year. And all these need to be together with the basis and the basic understanding in the Met community that impact-based forecasting is the way forward today. So in a forecast that we generate, yes, we should tell the expected climate anomaly, the hazards that may occur in that climate, but most importantly, what would be the potential impact of the expected hazards and what measures can be taken or what anticipatory action plan can be prepared and implemented to reduce the impact or benefit from opportunities of that event. So these are, let's say, I think is the last slide. Thank you, and looking forward to discussing further with you on those important issues. Thank you.
Andre, will you be able to join us tomorrow at 8 or yeah? What time is our?
I think it's 8.
8. So at 1200 UTC, are you available?
At 14.
12 to 13:30, I think.
Yes.
12 to 13:30 UTC. Tomorrow, are you available?
Okay, so that will be 1 p.m. here in Niamey. Yes, I should be able to do that, yeah.
Okay, we need you for the discussion because we need to talk about how a regional center like yours is mapping to the needs of the national centers where you really have some serious issues going on. And probably the most, the one that has got me probably thinking the most is when Olumide was talking about just people leaving the Met service for greener pastures. If that's US or Europe or someplace else, you running into a capacity issue, right? And if people stay around, you need to figure that out. That seems to be pretty serious, along with many of the other infrastructural needs. I mean, Nigeria has 300 forecasters. Madagascar has 3, and this is horrible.
Yeah.
So
yes, the problem is actually most often linked to the institutional setup in the countries. In most of the cases, even in countries where the Met offices are agencies, there are still significant management reliance on the ministries and efforts to promote and develop autonomous agencies is the policy that WMO and other organizations are promoting to help address the situation. This will create a situation where Met services develop their own staff rules, salary grids that attract talented young Africans in the field, which is now often difficult because most of them are public sector organizations under ministries with very limited possibilities to actually improve the situation of staff. I even have a lot of cases where a Met Service improve and develop marine information systems that is found useful, but the resources that are generated by selling these services are then channeled to the public treasury. And those Met officers who are behind those activities are usually frustrated and usually think of leaving the country for greener pasture, as you said. So that's it's a key concern that we should address also politically.
Okay, so I hope you can join us tomorrow. There was something in the chat that Charles put about the inauguration of the African Meteorological Society, but I really, this is kind of a big problem. And the ones creeping up are the ones where you're losing capacity at a time when you need more capacity. So we really need to address that in the conversation tomorrow. Charles, I hope you can also join us tomorrow. Charles is from UMBC, because this discussion needs to happen and we need to discuss some kind of, you know, first level 1 solutions. You can make some comments and then we have our last speaker. Can you unmute her?
He can unmute.
You can unmute, Charles.
Oh, you're talking about Charles? Oh,
Yeah, he's on the screen right now.
He can unmute now.
Okay, thank you very much. Thank you, Andre. Thank you to all the speakers for this, very enlightening presentations. I really I enjoyed watching all of you. Yes, I put the information here that the International Forum of Meteorological Societies helped to inaugurate the African Meteorological Society last year. And the first conference is coming up next year, April, in Addis Ababa. They're working in partnership with the WMO RA1 office in Ethiopia to host this conference. So yes, this issue of capacity, capacity reinforcement in Africa is a challenge that all of us are aware of. And so this newly inaugurated society is trying to help with that. There is an education committee that has developed some, training modules that they are going to be giving to, young rising professionals in this field. And there are other things. There are scientific collaborations going on that they're trying to promote. So I encourage everybody to please put it on your calendar that this first conference will be happening next year. And we'll be inviting some of you as invited speakers. Thank you. That's all I wanted to say at this time. I'll try to join tomorrow. If it's in the morning, yes, I can join. In the afternoon, I have other engagements, but hopefully I can join tomorrow. Thank you very much.
Okay, let's go to the last speaker. He doesn't have a PowerPoint, so it's okay. I just wanted to put this up here because I don't think that people fully realize that the need to rebound from a disaster is tremendously difficult for many people on the continent. It's difficult for people in the United States, but it's extremely difficult for people on the continent to come back from disaster, leading to the displacement of many people. I mean, there's not like an insurance company waiting to give you a check when you lose everything. So this thing with the The hazards that we're talking about is like definitely, yeah, FEMA's not coming in is definitely devastating to lives of people on the continent. And we need to figure out how to build capacity. And so Riyad is the next speaker, and he's one of the people who has developed an informal network. I call him, if he was at Penn State, he would be one of our weather lovers, weather weenies, but he provides such an important support system to many people in Senegal. So Riyad, I would like for you to talk about what you do, your network, etc., and the value of it in terms of supporting the country of Senegal.
Hello, everybody. I am Riyad Kawa. I live in Senegal. I was born in Senegal. And since I am young, I am captivated by thunderstorms. I have been pushed by a friend 13 years ago to put my previsions on Facebook first, because everybody who know me told me that my previsions, my forecast was good forecast, and that it can help some people. So first, I was just looking for to have some people passionate like me, because in Africa it's very difficult when you have a passion like this to share it. So I accepted to put it on Facebook first, just to have some people passionate like me to exchange this passion. But after that, it is now a public group in which many people are taking focus from me to prepare themselves from their activities. So today, what I do is that I make focus, but near focus, few hours, about or 1 day maximum, just for the people to be aware of thunderstorms coming, if there is some winds or heavy rain. And today, people are using this focus to protect their activities. The group is about more than 100,000 people, official, but unofficial, many people. Unofficial, many people, most of that, an office told me that more than 60% of the population is looking my Facebook group, and it saved a lot. If you see the comments inside the group for many years, in each activity, in sailing, fishing, agriculture, safety, many people told me that this group has saved them about flooding, about losing their culture, about saving their lives also. For example, a few years ago, 5 years ago, a big thunderstorms came from the continent, and I have given an alert on the coast, and the environment police took this alert for sure, and they went to get some gas oil to put it on the boat, because some people were on an island, and they had to go there to save them before the thunderstorm come. Unfortunately, 2 people died, but 4 people were saved. More than 4 people were saved, and the environment police told me that it was if I didn't give the alert, maybe everybody would die. So this group today is a public group, and I can't now stop it, because many people are using this group, and they told that the forecast is very accurate.
We have your Facebook page on the. I'm sharing your screen.
Yes. So this group name is La Météo de Riyad. Riyad is my first name. So I can't also make the Senegalese. I don't want to use Senegalese name, because we have the Senegalese national forecast. So I let them to use the name of Senegal. This is normal for me. So I use my name and the name of Meteo. It means forecast for the people. I use the forecast to make this name for the people to know that there is forecast, and this is from me. And inside, I have used the clause of non-responsibility, like other applications, like other internet URL that I are making also weather forecast everywhere in the world and for each country.
So tell us more about let's say last year, you had some flood events in Senegal.
Yes.
And how do you spring into action? How does the network around Senegal work? Do people send you videos? Do they send you?
Yes.
How does
So what I've done to get too much people, sorry for my English, I try to do my best. What to do for the people to come in this group? I use some videos also to I give them also some hours. I can calculate some hours before the thunderstorm come. So at the beginning of this group and until now, but at the beginning to get more people inside, I was calculating the period we have to wait before the thunderstorm come. For example, I tell them at noon, the wind in Dakar will come and then rain will fall. And at noon, the wind came and the rain also. And then, people want to know and want to see, they want some proof to trust. Because in social media and in this world, many people today are changing reality and they want people to trust on something that is not true. So it's very difficult. So I'm using videos, I'm using also predictions about how many hours the storm will come and for the people to trust. And today the people are trusting my forecast. So I have created also in another network that is WhatsApp. I have created, but from Facebook, I have created in WhatsApp a group called Les Observers about observers of Senegal skies. So today in each department, you have 52 departments in Senegal. In each department, I have at least 4 observers. And each day, in morning, in the middle of the day, and at the end of the day, at the golden hour, they send a picture at the east, at the south, at the west, and at the north of their position. And also, if there is thunderstorms, they directly put it in the group. And I use all this information to put it in the central information that is in Facebook, and I share it after in the other networks. Then people directly know what is happening in one region or one department. And if they are taking their car, for example, from one department to another or one region to another, they know what will happen and if they have to wait or they have to go. This is how I manage this group.
do you collaborate with Senegal Med Services?
Yes, I was collaborating with them a few years ago. About 6-7 years ago, I have given an alert about big winds who were coming in June. So normally in June in Dakar, we don't have rain or big winds. But this time we had rain and big winds coming from Mauritania. So I have given an alert. And this alert came to our airport and to Dakar with high winds. And we have some disasters because of the winds, even at the airport. And one journalist the other day has spoken about that, and unfortunately, he told that why Mr. Riyad is okay, and why the National Meteorology has even given this alert. So inside, I have in my inbox, some people send me some message to tell me that the national forecast are angry because of what happened. It was a few days before my birthday, so I went there to meet them. I asked to meet them, and I was invited by them. So I went in my birthday to sit with them, and they told me that I don't have the right to do some forecast because it is very dangerous and everything. I told them I have a clause of non-responsibility, and today many applications inside Apple Store or everywhere or URL in internet are using some forecast. So I just give forecast. I don't. This is not an obligation for the people to follow me, and that I am passionate of that. So they gave me some tests of observations inside the meteorological agency, and in this test I was okay. So the director told the engineer to work with me. He told me, "How do you want to work with us?" I told them, "This is a passion for me. I have my work, but I cannot stop this passion. This is my passion. I don't want a salary. I don't want nothing. What I want is to save my country. I want the thunderstorms to come because we need agriculture, and climate is changing. So what I want is just maybe collaborating with you for free." They told me, okay. So we have created a group in WhatsApp in which I was inside with some engineers of National Meteorology of Senegal. I was giving some alerts inside this group, but each time I was giving an alert, they told me, "No, it will not rain. Don't put the alert on your Facebook. Wait. So I couldn't wait. So I was waiting 1 hour more, but after that I have put the alert inside, and the rain came and the wind came. So frustration maybe came. I don't know. One of them has left the group, then a second one has left the group. We were only two inside, one of the Meteorology of Senegal and me. And today this group is non-functioning, unfortunately. So collaboration, I think, has stopped. I don't know why. I don't know. I am also sad for that. So this collaboration has stopped, but I cannot stop from my side to do that, because when I read the comments of the people inside, you have thousands and thousands and thousands of comments about people who have saved their culture, their lives, and everything. I say, as I believe in God, I believe in life, and I love humanity, and I love all that is living, even animals, even trees, forests. So I cannot stop. For me, if I stop, I will die of a disease or something. I cannot stop. So I continue to share this kind of information inside. Last year, unfortunately, again, the director of the meteorology has made a video. He didn't give my name, but he told someone in Facebook is making a focus, don't follow him because he's copying on us and he's dangerous and everything. I didn't give my response of that, but I continue on that. So unfortunately, we are not collaborating, I think. But today, many of the way that I am putting my focus are taken by them also, the kind of expressions, everything. And I'm happy of that. I'm happy of that. I'm not angry of them. I love them, because when you are passionate of climate, you are passionate of all the people who are working in forecast. And when I know that climate change can end the world can end because of climate change, today I can just support everybody. So I love them. I still love them. I'm not frustrated. Maybe I'm sad, but I'm not angry. I'm not frustrated. So our collaboration, I hope it will come if it can, if it could. I hope it will come. If it come again, I will tell yes, because if you collaborate with somebody to give information to the whole population, what is the most important is that the population has benefits on that. So maybe I cross my fingers. If they come to me and want collaboration or other things, I will tell yes, because I see that today in Europe, in America, some storm chasers are in contact with meteorological centers because they are on the ground. They are chasing the storms like me. So with satellite, you have imagery every 15 minutes, sometimes every 30 minutes. And when you are on the ground, you can in seconds give some indications. And I think that this kind of indications is very important today, even in America, because we know that in this valley, from Texas to the north, you have each year some criminal tornadoes, and that sometimes if people are chasing them, the National Meteorology Center can get some information or some videos from the ground. And I know that their predictions are accurate, but maybe more accurate in some distance for the people to hide before a tornado comes, for example. So I hope that collaboration will come again with the National Meteorology of Senegal.
I guess I was asking you about some events that you have witnessed, let's say over the last 2 years, where your network, where your Facebook page has been important. Yesterday, you mentioned talking about social media, about agriculture, started rainy season, end of rainy season, but also in Dakar, you have a big, massive city, and when it floods, it's debilitating. So can you give us just some stories
Yes.
about?
Yes, 2 years ago, one big storm, one big cell, supercell was just in the east of Senegal, between Mali and Senegal. And I have given an alert of big flood coming. So people were, sorry. So people directly took their safety, and big flood came to Senegal. We had disasters. 2 people died. I think, yes, it was 2 people. 2 people died in this day. I have given some alerts, and after that also I have shared some videos, because today the group, everybody in the group is also sending me some videos from their part of the city, and also me with my car, I'm going around and taking some pictures, some videos to show the people what happens after the rain. So yes, I used to share this kind of information, and I'm doing this again. Like 2 years ago, a big flood came. It was at night. A wall also collapsed on one family, and this is why 2 people died. And it made that this group is a group that is followed today. This is an example. 4 years ago, also, I have another one. I told them that a big thunderstorm was coming to Senegal, and that it was at the east of the country, at the northeast. And I warned the people in Dakar that this storm will come around 9 p.m. In Dakar. And some fishers called me and told me they want to go to fishing, and if they can go. I told them, no, you can't. If it is me, it's better I stay on land, don't go. They told me, okay. But this supercell was at the northeast, and it has make-born little cells at his west. So unfortunately, some friends of these fishers told them, Mr. Riyad Kawa is lying. This is the storms, what he's speaking of. This is little storms. It's finished, let's go. So they went, but at 9 o'clock, a big wind came, and their boat has been returned inside the sea. Fortunately, nobody died, because the police of the sea went there and saved the people, and they came back on the land. But till now, on rainy season, when they want to go for fishing, they call me and they tell me, please, we want to go from this hour to this hour. Tell us if we go, or tell us if we don't go. And I'll tell them, okay, you can go. But if I am sure in 100%, I tell them. If I'm not sure, I tell them, don't go. We have a chance of thunderstorms, but please don't be angry if the storm don't come. It's just around. Because sometimes these people, if it is not raining, they will tell, okay, Mr. Riyad is lying. But with climate change, we know what is happening. The cells can collapse directly, or they can take a direction at the last minute. So I tell the people, don't be angry. If you trust on me, trust on me. I'm not here to fight your fishing. I'm here to save you if you want me to be in the game. So I'm in the game with you. If you trust me, trust me. This is the 2 examples I can give. There is many examples in this book.
Okay, there's a couple of questions, but I want to ask you about right now. So
yes.
So this year, the monsoon seems to be strange. It seems that Dakar has not gotten much rain. Days ago, you see some rain over the desert in Mauritania. The models, they don't seem to be, maybe it's just too early in the monsoon to see the waves to be really developed. What I just want to know from you, what's your sense of what's happening this rainy season?
For me, you know, there is a big problem of deforestation. And in Africa, we use charcoal for cooking. And I have one statistics from 8 years ago. For example, only in Dakar, the capital, they use about 70,000 of charcoal, 70 tons of charcoal per day just for cooking. And to make 70 tons of charcoal, you need at least 700 tons of wood. So imagine how many trees per day you have to use for charcoal only. So for me, there is a problem of evapotranspiration. And today the balance is negative. It was okay, but now it's negative. For me, it's not only Senegal, also in Mali. I don't know, I don't have idea of Burkina Faso or Niger, but I know that in Mali, they have deforested a lot. And in Senegal, till now, the mafia is there, and they are deforesting a lot. We have one statistic, one number, it's like 40,000 hectares per year disappearing of forest. Is the forest disappearing only in Senegal? But I know that today is more than that, because today we have also Asian people who are coming. The Asian people are coming also for some wood. They used to make some furnitures. It's not only charcoal today, it's also the wood that is exported from Senegal to go to Asia and to be manufactured there to make some furnitures and other goods. So for me, if you deforest, and we know it, I know you also, the scientists know it, and I have learned also behind you and behind the scientists, if you cut some forest, you will let the soil nude, and this soil will take energy by the sun, and this energy will give some heat on the ground, and the air will be the air will change, and the pressure will change, and some negative winds will come. So today, forest, if you have big forest, you can also manage the atmosphere. The forest can manage the atmosphere from ground zero to level 2 kilometers and more. And this is the bad winds come from zero level to more than 2,000 meters of level. So for me, the deforestation is a big impact about how the thunderstorms today are going inside the Sahel, inside West Africa. I'm regarding for now 4 years each thunderstorm who is coming from the east, and I see that they are at the beginning of the rainy season. When they come to Mali, they go down to the southwest, because in the southwest you have the Guinea forest that is very foresting. For me, there is a lack of humidity because also when you cut these trees, the tree is like I don't know how to say fontaine. It's something who is living, and then from its roots it goes down. It takes the water of the undersoil, and after that with evapotranspiration, it puts this water, the vapor, outside, and this vapor is being used by these systems who are coming from the Niger and from Burkina Faso and sometimes from Chad also, and these cells normally had to stay alive. I know that more than 10 years ago, when a supercell was born in Chad or in Niger, this storm stayed alive for 5 to 7 days to come to West Africa, stay alive at day at night. And today, at some hours of the day, maybe more at night, these systems or also at noon, because the sun is too much, this system collapse, and then another cells come after. So for me, there is a lack of evapotranspiration, and the soil is being dry. And these storms, when they let rain to go down, they have to take some humidity to stay alive. They have to continue to make rain. But if there is no humidity, they collapse, but the energy of the atmosphere of the system stay. And then a few hours after, when humidity comes from somewhere, and in majority from the southwest, we see some other cells who are burning around this system. So for me, in the algorithm of forecast, maybe the scientists should maybe see this problem of evapotranspiration and deforestation we have in West Africa. And I think that you have to reforest. Maybe we can use Google Earth for the decades, for the 2 or 3 decades before, to see how we have cutting and how the forest has disappeared from all this space, and maybe reforest this space to make maybe the monsoon of Africa, the African monsoon, come again and stay regular for the people. Because this is a big impact today. We see that inside the countries, many African people are going to the coast to get some job, and even they are also taking some boats to get to reach Europe, and today they want also to reach South America. And this is a big problem for economy of Africa, because the brain are going, the hands are going out of Africa. And today also it's an impact for Occident, because in Occident it will be too much people, and in America also, if they enter in America, they want to go to United States and other parts of the world. And we know that in every part of the world, people are looking also for job for their community. So for me, we have to save African monsoon and make it be again good for the people to stay there, to get some job there, and also to have health there. Because what we can say is that in dry season, as we don't have forest, the little water we have underground, maybe below than 0 meter and going to 30 meter, all this water, because it's too dry by the sun outside, all this water is going out and is going out of the atmosphere. That's why we have too much heat, more than 40 degrees Celsius. I don't know in Fahrenheit, but more than 40 degrees Celsius we have in Senegal and in Sahel between February and May, June, before the monsoon. And we have many health problems. Last 2 months in Mali, we had many people died there because of the heat also.
Wow. Okay, I got to combine 2 questions, and then I don't know if you can join us tomorrow. I know you are dealing with family situation, and so we appreciate even your time to be here. So this question, I'm gonna combine them. One is like, how do you explain the complex topics, meteorological topics, to your Facebook community? And tied to that is, how do you sustain your community?
I try to make it as easier as possible. In my mind, when I draw it in my mind, it's very complete. But I try to make it the more simple. I like a little cartoon not cartoon, like a little draft, a little draw, and I use some little apps to make some colors, to explain to people what is a cell and what direction it takes. And when it not happened, I make some videos like the one I have sent you now a few minutes ago to show the people how the thunderstorms are collapsing, and I explain why they are collapsing, and I push the people to go to reforest the villages and the grounds to hope that in some years the rain will come earlier, and that they can make agriculture, and that also they can have some food for the rest of the year. So this is how I do in my group. And also in Africa, many African people are very cultivated, but some of African people also have a lack of education, unfortunately, because of poverty. So also I use to speak in simple French, because we use French here in Senegal. So I speak in a simple French to make the people understand, and little draft also to make the people understand what is happening. and make them also to compare on what I'm telling and what they will see with their eyes. And today, I want to stay in the truth. And today, they trust on that, and they are speaking on that and acting on that. For example, today, from some years, but this year we can see it concretely. Today, this year in Senegal, we are speaking inside the Senegal, and also the government is speaking about reforesting inside Senegal. And also, I used some industry that wants to make their part of carbon impact. I push some industries to burn some trees from seeds, and to call some organizations to take for free the seeds, these baby trees, and go and reforest. So today also an organization inside Senegal has copied. They took example of this idea, and they have made, in the middle of Senegal, they have made a big garden about little trees to give to the people to go and reforest also. So this is how I use this is the method I use to make people to understand what is happening and make them act.
Yeah, you show. I'm putting up the video you sent of the collapsing thunderstorm. What did you want to say about this event?
This is what is happening till June, all the months of July and till now. We will go to middle of August, and many regions of the west of Senegal are crying. They are stressed. And the north also, they are waiting for rains. I assure you that 10 years ago, if this kind of supercells were at the east, like this one, it will 100% cover the country of Senegal. And today, unfortunately, when they are at the west of Mali, they collapse, and the cells go down to Guinea. And for me, this is about a lack of humidity and a lack of forest, because the winds of the ocean from 0 meter to 2,000 meter are strongest because of the lack of forest. So this is a problem of pressure depressure. And what is happening there is that in some regions in West Africa, instead of having this cell one time, they can have this cell 2 times or 3 times or 4 times. If you see this cell, it was born in the same way as the second cell who is born now at the northeast, a second time. So this region will have again this cell another time, and unfortunately, Senegal will wait again to get some cells.
Okay. Well, look, we don't know if you can join us tomorrow, but whenever and if you can.
I can.
Okay, so look, we'll have the discussion again tomorrow. I'll send you the times, and there is many people who have questions for you, but I think you have to continue, as you said, or you will die from something else. So
yes.
We don't want you to die from something else. So Riyad, thank you so much. And we're gonna now take a break for the next hour or so. And I'm just gonna put up, so if you are around this afternoon, I don't want to force people, but there's a new concept that is going to be described, the warn on forecast system to deal with local extremes from NOAA. Then Paul Murkowski is going to talk about tornadoes. He's from my department. Bill Parker, who's behind me, is going to talk about severe weather in Mississippi. This is a long day, but it doesn't matter. We have to do it, right? I feel like Riyad, right? After this, we have people from Hurricane Center. We'll shift our focus from severe weather to tropical cyclones mid-afternoon with someone from Hurricane Center, Yunji, 2 people from National Hurricane Center talking. And then finally, we talk about flooding, communication, and how to get across these messages to populations. So we'll be back in about 5 minutes, and I hope you can join us. But even if you haven't, I just want to thank all of the speakers from Africa this morning to give their talks. Is very enlightening, and we have to have discussion about this tomorrow. So it's not AGU or AMS. It's not to just give a paper. It's to enlighten the audience so we can think about future collective actions. So we'll see you soon in 50 minutes if you come back. And thanks again, everyone.
Okay, good afternoon or almost good evening for the people that are joining us from Africa. And we'll have our Tuesday afternoon in the United States session. And the first sessions will be talking about different aspects of severe weathers in the United States. And our first speaker is Mr. Patrick Berg from National Severe Lab.
Hello, can you hear me?
Yes, we can. Okay, if you can try share your screen, I'll just do a very brief introduction. And Patrick is a scientist and public servant with a passion for real-time severe weather events and safety information at the National Severe Lab. Oh man, a scientist for the Warn on Forecast program. And he has his bachelor and master from the University of Oklahoma. And he has been serving 18 years as a National Weather Service forecaster, working in both local and national offices before he moved into a research role in his home state of Oklahoma and pushed the weather warning science forward. And the floor is yours.
Okay, sorry for that. I think you can hear me now. Were you able to see the slides when I showed them?
We saw it a few seconds ago.
Okay. Let's see. Okay, is that good?
It's not in the slideshow mode, but now it is. Okay.
Yeah. Great. All right. Thanks for bearing with me. We in the government we use Google Meet, so I'm not very familiar with Zoom, but I'm very happy to be here speaking with you all. This sounds like a fantastic workshop, and I look forward to catching some more of it. But we have some exciting work in the area of severe weather prediction on the local scale to talk about here in the Warn on Forecast program. So I'm the Warn on Forecast program lead or project manager. Thank you for that introduction. Yes, I had a long career in the National Weather Service before moving over to research. So hopefully I can speak to some of these prediction challenges from the researcher and forecaster perspective. And this idea of Warn on Forecast is something that developed over the past 15 years or so here in the United States. And I have an example of why that developed here. So in the US, we have this watch to warning paradigm where we ideally see watches for severe storms and for tornadoes issued at hours in advance of a threat at the local level. And then primarily based on radar detections or spotter reports, we'll have warnings come out minutes or tens of minutes prior to the actual impact to a local community. But there's kind of a disconnect in the meteorology of these two images. So on the left-hand side, when we're talking about issuing a watch, that's highly driven by numerical weather prediction models. And then the warnings are highly driven by radar. So there's this gap in between. In this case, for a tornado that occurred in Michigan earlier this year, about 3 hours between the watch, which is regional scale, and then the warning, which is the very local scale and has that immediate call to action for people to seek safety. So what we wanted to do here at the Severe Storms Laboratory is provide forecasters with better tools, numerical prediction tools in that gap period between the watch and the warning to potentially extend the lead time for warnings such as for tornadoes. And more of the motivation for that is shown on the left-hand side here, where if we look over the last couple of decades, the average lead time for tornado warnings is somewhere around 10 to 15 minutes, depending on how you define it. But there's really no trend there. It's pretty flat. We haven't made any large advancements in tornado science enough to move the needle on lead time for tornado warnings in particular. So and it's not too hard to imagine many groups and locations that need more than 10 or 15 minutes of lead time for a strong tornado. Mobile home parks are a good example, hospitals or sporting events, concert venues, any outdoor activities. All of these people and places could benefit from having more advanced warning at the local scale. So back in 2009, our lab began a project to take advantage of the increasing capability of storm scale modeling and the increasing availability of compute power to tackle this problem of providing forecasters with numerical guidance in the watch to warning timeframe. So basically 0 to 6 hours is where we operate the warn on forecast system. And so that idea of warn on forecast is to move away from the paradigm where we issue warnings, or the National Weather Service issues warnings primarily using radar, and to instead use numerical models to inform those warnings. So that's where we developed the warn on forecast system, which makes probabilistic prediction because thunderstorms carry so much uncertainty in their character and their size, their timing, evolution. We need an ensemble approach, essentially. So we took a probabilistic approach to this problem, and because that requires a lot of compute power, we operate on a regional domain. So it's not the entire United States, but instead we target the model at wherever severe storms are expected on a given day. And in order to keep up with the evolution of those storms at the local level, we developed rapid data assimilation methods. So every 15 minutes, the model is cycling, pulling in the latest radar reflectivity and velocity information, also several satellite fields. And then every 30 minutes, we will put out an entirely new set of forecast products. In order to do this for severe weather operations, there has to be low latency. So we try to push out an entire forecast out to 6 hours within 25 to 35 minutes of the run being launched. So that's pretty low latency and can be immediately applied in the warning environment. And then our output is viewed at 5-minute resolution, which gives forecasters the opportunity to envision the detailed evolution of the storms that are being predicted and to make, hopefully, predictions at the city level. That's an example on the right there of the concept where this was an actual storm that occurred in 2022 over Chicago. WAFs had a probability swath, high probability for low-level rotation in the storm, and then you see the actual storm that occurred about 90 minutes later, right in the middle of that probability swath, and had 2 tornadoes with it. So to give you a little bit more a way to visualize what we're doing with this rapid data assimilation, we'll take this storm here in western Arkansas. So this is a developing supercell storm early in its life cycle. but it's been around for about 60 minutes. So we've been assimilating radar data. And then on the right-hand side here, I'm cycling through all of the 18 forecast members of the ensemble. So a forecaster can do this in real time and see that all of the ensemble members are pretty well initialized with that storm. And that gives you a little more confidence when you view the forecast output. And so I'm showing on the left-hand side here just an example of a couple of the different members and how they take that storm. It becomes a long-lived storm. This is about a 4-hour loop. It moves to the right, takes a right-hand turn. Those gray swaths are rotation swaths or updraft helicity being left behind by some of these cells in that area. And so very many of the members had solutions like this. Then for the various hazards, you get a probability field that shows moderate or high probability. So in the middle of the screen there is the probability of severe hail. And the green dots are where severe hail was observed in this period. And so it's a pretty good narrow focus where the one could use to say over the next few hours we expect severe hail in this zone of the state of Arkansas. And one of the unique features of the War on Forecast system is that, again, we relaunched the entire forecast a half hour later after having another couple of assimilation cycles. And if there are ongoing storms, then the forecast often gets even better. It gets a little bit sharper on the right-hand side image there. The probabilities go up. They're more narrow in scope, they're more precise, in other words. And this is a common trait of the system that we've developed. So there are a couple of other, just thinking about the challenges of predicting severe weather at the local level and various things we have to overcome. This is a new type of modeling, really, where we're targeting regional domains on areas of expected severe weather. So the model doesn't run all the time, and it doesn't run everywhere. We have domains that can migrate around the country. And that actually is pretty well suited to cloud-based computing. So we've developed WAFS as a cloud-based system running on the Microsoft Azure cloud. And over the last few years, we've really tightened that up. It's a pretty well-oiled machine. It's containerized. In other words, you can plop it onto any computer and run it without compiling anything. This gives us less dependence on the research hardware. The runs are pretty cheap. For this run that I'm showing here with the 2 domains over Texas and Florida, it's about $1,000 to run for the entire day. And then there's this interface that we've developed that National Weather Service offices have used in cooperation with us to select the domains for certain experiments, where they can add the domains, move them around the country, and very easily launch a new run of WAFs. Visualization is another thing we've really focused on over the years, so that if you imagine, this is an entire modeling system that gives you a new run every 30 minutes. That's going to be a lot of data coming at the forecasters who are already juggling phone calls and graphics and other things that they are doing. So they don't have necessarily all the time in the world to dig through the model data every half hour. So we've worked with forecasters to come up with visualizations that help them get the information they need very quickly. And also, this is a little bit of a animation that will play here, or maybe it won't be able to play. But I'll just give you a sense of the web viewer for War on Forecast. This is the main way that forecasters are using the system right now, because it's still experimental. It's not in the National Weather Service software just yet, but they can use these drop-down menus to select probability and percentile plots. This here is a paintball plot that shows all the storm objects from all the 18 members all on a single plot. And all of this is designed in the fashion of some of the operational viewers that the Storm Prediction Center uses. So forecasters are familiar with this kind of layout. There are a lot of keyboard shortcuts and customizable overlays that they can toggle on and off. And again, that has been one of the strong principles of our group, is that we try to remain engaged with the users as much as possible and use their feedback to improve the system. So you see a few of the images here of us embedded with either National Weather Service forecasters or emergency managers. And then our test bed here in Norman, Oklahoma, we have ongoing experiments throughout the year to bring some of those folks here to talk about WAF's output. And then you see the locations of our runs. We have, even though it's targeted towards severe weather, which more often occurs in the east, we have spread it out across the country quite a bit. So now that you have kind of a background of what the War on Forecast system is, I want to talk about three extremes of severe weather: heavy rainfall, tornadoes, and derechos. And this should give you a sense of some of the success that we've had with WAFs and also some of the remaining challenges. So I didn't say before, but it is a 3-kilometer grid modeling system. So it has no greater resolution than the operational convection allowing models at this time. The real value in WAFs is that rapid data assimilation and the relaunch of forecasts so frequently. But at that 3-kilometer grid spacing, we find that WAFs does really well with heavy rainfall on many different scales. So I'm showing just two examples here. On the left-hand side was a case from 2021. There weren't very many thunderstorms that day at all in the southwestern United States, but there was one small complex that produced 3 to 4 inches of rain. And this is a very dry territory, so it floods very easily. And the flood that occurred from that 3 or 4 inches of rain caused a train derailment in southwest Utah. And WAFs predicted that rainfall just in the exact right place at 4 hours in advance. And so that could be really useful. An example on the right is from St. Louis, Missouri in 2022. They had a very early morning complex of storms that persisted for several hours and produced very high-end flash flooding, some fatalities and evacuations, a lot of damage in the city. And WAFs caught onto that again several hours in advance, predicting at least a 40 to 80% chance of greater than 5 inches or about 127 millimeters of rain. So again, that lead time, or on that watch to warning time scale, could be very, very useful. In some of these cases, other models had the heavy rain 200 kilometers farther north, especially in the St. Louis case. So being able to get that location right and place it over the city is really important. I think it's also important too, as forecasters, we need tools within the model so that we can get a sense of how far to trust a given signal. So if it's showing heavy rain, well, how far do we trust that heavy rain signal? How much confidence do we have in it, in other words? And there are a lot of products and tools within the War on Forecast system to help forecasters do that. I'm showing 5-minute rainfall rate on the left-hand side. This is from the 2021 event in Western Tennessee that produced the state record for rainfall, which was about 376 millimeters. Actually, the state rainfall record was more than that. It was over 500 millimeters, but in a 6-hour period, that system produced 376 millimeters. And WAFs actually predicted in the max percentile from the ensemble 353 millimeters in that same time, which is a fantastic forecast. And again, these are 6-hour loops of 5-minute rainfall. So a forecaster looking at that could say, wow, these storms are not moving very much in 6 hours. And also we see some mesoscale vortex development that might help anchor the heavy rainfall. I see simulated satellite imagery showing a wedge signature there in the middle. And then on the right, there's some ensemble sounding and photograph tools. So lots of different ways that forecasters can pick apart the data and gain confidence. So that's for rainfall. For tornadoes, we've seen many success cases as well, especially for some of the larger storms. When we have smaller tornadic storms or storms that are embedded in lines, WAFs will struggle with that, partly because of the resolution problem. But for these larger, long-track supercell storms, WAFs tend to do really well. And this is an example from Gaylord, Michigan, which was a deadly EF3 tornado in May of 2022. And again, that I alluded to it earlier, that the forecast tends to get better each half hour as more data is assimilated. And you can see that in the middle and right-hand column here. We're looking at first of all, the probability of updraft helicity or of rotation in the storm exceeding some threshold. And then in the bottom row, you've got the maximum percentile value of that helicity. So that would be the strongest WAFs member. What is it showing during that period? And so at about 80-minute lead time, we see kind of moderate probabilities, but that the maximum percentile is fairly high. So that would be kind of a low probability, high impact event at that point. And hopefully forecasters could begin thinking about it or messaging that. But then we see the next run in the right-hand column, the probabilities increase and the intensity in the max percentile also increases very near to where the tornado occurred, which is the blue dot. So that then becomes a higher probability, high impact situation, still with 48-minute lead time at that point. Another similar case is a storm that struck Little Rock, Arkansas in March of last year. And I'm showing 3 different products here, all at very long lead time. So on the left-hand side, we kind of see the average solution for the storms within WAFs. The ensemble mean is the black contours. And we see where that overlaps with the significant tornado parameter showing values of 3 or 4 nosing up into the city of Little Rock at that time. In the right-hand side, I wanted to show you that we do have some machine learning-based products. So these take WAFs and post-process the output to produce a more reliable probability. And that was showing that within a 30-minute window, there was a 25% chance of a tornado occurring right there across the city. And then in the middle image, that's 90th percentile of low-level rotation, or actually low-level vertical velocity, or sorry, vertical vorticity. And we see those purple values, that's kind of the maxing out the scale there, which shows the proper trend of right when that storm was going to mature as it came in from the west. So this again was at 82-minute lead time. So this type of signal that we're hoping forecasters can gain confidence in as they get more experience with the system, and then potentially issue warnings earlier. For that same case, I did a deep dive. That was actually a tornado outbreak that spanned many states. So there were a lot of tornadoes. And I talked about that kind of ramp up at just the right time in the vertical vorticity product. Well, over the 39 tornadoes that WAFs correctly kind of had a storm in that area of the tornado, all of those showed an increase in that vertical vorticity in the 20 minutes prior to tornado touchdown. So there's some sense here that when WAFs is performing well, that it might actually be capturing when a storm will cycle up or become tornadic. So there's more research that's needed on this. It's just one case, but it's at least encouraging and something we need to dig into more. And you kind of pair that with some other research that we did over the past year with the University of Kansas student. And he found some statistically significant differences in the WAFs environment near tornadic supercells versus supercells that did not produce tornadoes but did produce large hail. And so you see the composite images from his cases on the left-hand side there. The one in the upper left are the tornadic supercells, and in the lower left, that's the non-tornadic ones. You're looking at the low-level storm-relative helicity in the image, and then the average shape of the storm in the black contours. And so there's some encouraging signs there, and really a lot of more work needs to be done on the environment in WAFs. We've tended to focus more on the storm cells themselves, but this is at least an early result showing that the environment may be responding to the storm in the model in ways that could help tornado prediction. Okay, so we've kind of run through the rainfall and tornado cases, and then I have a little bit of a deeper look at a derecho case, because I think this highlights a lot of the value in WAFs and some of the challenges as well. And especially because this workshop is about extremes, and this is one of the most extreme events that has occurred in the past several decades in the United States. So this is the August 2020 derecho, very severe wind, long-lived system over the Midwest, over Iowa and Illinois, that produced high-end severe winds across much of the state of Iowa and then again into western Illinois. This all occurred in the early morning to midday hours. So keep that in mind as we go forward in the next few slides. The main impacts were between about 15 and 19 UTC. And what I'm showing here is the observed radar. So that's what we would hope to match with our modeling efforts. So keep that in mind as well. The storms initially develop as elevated thunderstorms in South Dakota and then grow into that Boeing complex over Iowa around 15Z right there. And we see all those wind and tornado reports. So again, costliest thunderstorm system in US history, $7.5 billion in damage. 20% of the cropland in the state of Iowa was destroyed. And power was out for millions of people for up to 2 weeks. So really can't overstate what a big event this was. It was also a very difficult forecast. I happened to still be a forecaster at that time, working at the Weather Prediction Center, which is the National Center for Rainfall Prediction. So I remember this case, and there was a large area of high instability in place for several days over these states. But the numerical models didn't know what to do with that. Timing was very different in the models. The intensity, the location, everything was different. There was no clear signal. So in the Storm Prediction Center outlook at 9-hour lead time, the first outlook of that day, I've outlined the area that was impacted in the black dashed lines there. And you see that the first outlook on the left-hand side, this was a marginal or slight risk. There was no indication that this could be a high-end wind event. Then at 2-hour lead time, some things were changing. Forecasters were looking at the evolution on radar and seeing maybe some updated model solutions. And so they did properly adjust to a higher outlook, more impactful outlook at 2-hour lead time, but had to ratchet up even further after the event was already ongoing in Iowa. So very short lead time. It's an August event, weak forcing. It's challenging. So we had to kind of expand and run a larger WAFs domain to capture the whole system, but we wanted to see how it would do. And it turns out that it did really, really well. This is the 3Z run, or 3 UTC. So this is 12-hour lead time. And it correctly predicts a Boeing system. You're looking in the image there at the 90th percentile of the maximum surface wind gust. And we see lots of severe, anywhere that it's yellow or orange, that is a severe wind gust. And the red is significant severe above 80 knots. So this is really good. And the question becomes, so why was WAFs able to do this when most of the other models struggled? The There was one model, the HER, which I didn't mention before, but it did have a pretty good solution. It's just that it didn't have much support in real time. So why did WAFs succeed? Well, there's kind of a lot on this slide, so I'm trying to break it down for you. But first, let's focus on the instability. So I'm showing the surface-based CAPE, the ensemble mean, in the image in the upper left. And then those black splotches are the storm objects from each of the 18 WAFs members. So we see at the beginning of the night period over Nebraska and western Iowa, there's this almost white, kind of purplish white area. That's large instability of greater than about 3,700 joules per kilogram. So there's a broad area where storms could occur. And storms were attempting to initiate in Nebraska, and that's not very uncommon to have storms in the low-level jet in an unstable environment. But during summer, a lot of times those are less favored, and it's more favored to have storms farther north of a frontal boundary, which is what occurred here. Is the main storms ended up developing in South Dakota. So WAFs, because of its data assimilation, was able to kind of minimize the activity in Nebraska. And that was really important because if you look at the right-hand side, most of the other operational models had this very unstable environment. They had storms that you're on the cusp of developing. And so it kind of snowballed. And many of the storms in the other models did increase in coverage and intensity over Nebraska and began consuming all of that instability. So look at the lower right, instability was wiped out by 11 UTC in, this is the NSSL WRF model. Many of the others were very similar. And so that essentially prevented the other system from being able to develop. So we found in our study that suppressing the storms in Nebraska and just that rapid data assimilation was the key to getting this right. And then I think I'm not able to show, or maybe this will play. No, I can't play this loop, but essentially even there, so a 12-hour lead time, WAFs showed the concept of a derecho storm. But as we got closer, the location got better. So you see here that the location of the probability swath is a little bit to the north of where it actually occurred, a little bit offset. But with continued assimilation, that moved to the south and eventually was right on, was nearly a perfect forecast at about 4-hour lead time to the greatest impacts. And so that kind of brings me full circle to, I think I've mentioned a couple of times, just forecaster confidence and how we're trying to give them tools, especially probabilistic tools, to increase their confidence, to take certain actions in that watch to warning time frame. And these are quotes from National Weather Service forecasters that I have up on the screen there. Using this model guidance to forecast with greater lead time, greater confidence, and that, especially in the context of this workshop, close evaluation of the output can lead to meaningful warning decisions and anticipation of extremes. And I think we saw that for the Tennessee flood case and for the derecho case. And in my mind, this increased lead time, or the notion of that, means earlier communication of the probabilities, the uncertainty as it's increasing or decreasing, and things that are nearly certain, things that we're very confident in. Scenarios at the city and county level can be communicated more effectively. So I have just a couple of more slides to show what people are doing with this and the National Weather Service thus far. Again, it is experimental, but we're working closely with the Weather Service to move this to operations over the next few years. In terms of the communication aspect and how the public receives warning information, social science is making a little bit of progress, but it's still kind of early. in some of these studies, but this is one study from Mackenzie Krochak here at NSSL, showing that in that watch to warning window, the 4-hour to 60-minute window for either public or emergency managers, some of the top things that they want to know are the severity that could happen, the location, and the timing. And then the timing falls off and becomes less important as we get close to the event and the confidence increases that it's actually going to happen. So these are some of the things that the Weather Service forecasters are focusing on when they communicate WAFS output. And one of the most common ways that they've used WAFS is what we're kind of terming a watch to warning graphic. There's an example here of where the watch from the National Center is on a regional scale, but I've highlighted one county there, Kingfisher County in Oklahoma, where the local office, based on WAFS, put out a graphic showing a smaller area that was at risk within the watch. And they did that at about 1.5 hour lead time to when a tornado touched down, the first tornado of that day. Or they might chat the expectations to their partners. Everyone has now chat rooms where they're engaged with their local partners and emergency managers. And this was the Chicago office doing this for a storm that eventually produced some tornado warnings and a tornado in northern Illinois. And then occasionally, especially for the flash flood threat, we might see forecasters drawing a polygon or making their flash flood warning larger based on the signal from WAFS, or communicating potential river rises to an emergency manager. Sorry, my voice is starting to go out on me here, so I better wrap it up. But at WFO Lubbock, or the National Weather Service in Lubbock, they actually used this one time in the opposite sense of they had a storm that was producing a large tornado. And with WAFS, they were confident that the storm would dissipate before coming into the city of Lubbock. Just as important of a thing to be able to tell people the all clear, or to prevent the message of an extreme event going out when it's a false alarm. So this was, you can see in the right-hand loop there, the favorable environment washed past that storm and then it dissipated. So a few remaining challenges. I'm sure there are many remaining challenges, but these came to mind. Convective initiation is still a problem in our style of modeling. So the value of warn-on forecast is better seen after the storms have initiated. And when we can assimilate, radar and satellite observations of existing storms, the performance goes way up. And we'll need to resolve multiple scales going forward. We are working on a 1 kilometer version of WAFS right now, but it doesn't run fast enough to be used in real time. So, computing, as that evolves, is also a big part of the story. Trying to build on the use of artificial intelligence, either in post-processing or in replacing numerical models. We have work in both those areas. And then building operational systems that are both reliable and nimble enough to accept the new research as it comes out to get these things in operation. So with that, I will close and see if you have any questions.
I think we have a question from the chat. The first one is about the cloud-based grounds, and probably a little bit more about the configuration of the WAF system.
Okay, I think I heard cloud-based WAFs, but I'm not sure what the question was.
For which model resolution? 3 kilometers, is that right?
Yeah, the cloud-based WAFs is on a 3 kilometer grid. And the domain is 900 kilometers by 900 kilometers.
Okay. And the second one is about how does WRF simulate reflectivity and satellite? Does it require special initial data, or normally WRF has these variables?
I think so. Maybe you're asking how we assimilate the radar and satellite data.
Mm-hmm.
I'm not sure that I can answer that in a detailed way, but I know that we published several papers. If you look at papers by Nusrat Yusuf and Lou Wicker, going back from about 2010 to 2015, that's when we developed this rapid data assimilation. So there should be a number of papers out on that and how exactly we're using the work model to do that. I know that one of the more interesting aspects to me was the idea of additive noise, which our chief scientist Lou Wicker developed. And essentially, there are some cases where we'll be assimilating radar data into an area that the model thinks is too stable to have storms. And so we add some noise to the environment to make the ensemble less confident in its own prediction of stability, to allow those radar echoes to be assimilated and to grow in the model. I probably didn't answer your question, but hopefully that helped.
So do you think that this framework
I'm sorry, the audio is cutting out there. If somebody closer to the microphone could repeat the question.
I said, do you think that the Warner forecast for have multi-hazards?
Okay, yeah, I caught some of that. So you're asking about inland tropical cyclones or landfalling tropical cyclones and multiple hazards. That's a great question. Yeah, if you go to our website, and I've got it up on the screen there, CBWAFs, you can use the calendar in the upper left-hand. There's a pull down to go back to tropical cyclone cases. The most recent being Beryl here in the U.S. We had 3 days worth of WAFs runs for Beryl as it came in through Texas and exited through the Northeast. And you'll see that we actually have a special tropical cyclone menu, and there are additional products when we run for a tropical cyclone that show the probability of various hazards all on a single plot. So I'd encourage you to take a look at that. There's also a couple of papers by Thomas Jones in our group on the use of WAFs for tropical cyclone hazards.
Let's move on to our speaker. Talk will be from Solomampionona. And he's a distinguished professor and is the head of the Department of Meteorology and Atmospheric Science. And he has from the University of Oklahoma, and he has taken part in Vortex 1, Vortex 2, Vortex Southeast, Taros, and Turos field campaigns.
Thanks for the invitation and kind introduction. Can I be heard clearly enough on the audio?
I think so. Nobody complains so far.
So far, okay. So I'm going to summarize the latest thinking on how tornadoes form in supercell storms based on what's now essentially a half a century's worth of field observations, numerical simulations, and theory. I guess maybe before starting, I'll give a 30-second summary of how I got here and what I do. So I've made my whole career in the severe storms community, mostly focusing on supercell storms, not all the time though, but I've played with field observations, simulations and theory myself. And I guess there are different types of tornadoes. Some are in non-supercells, many are in supercells, but virtually all tornadoes that make headlines that are involved with high casualty events are in supercell storms. So those are the ones that I'll focus on. If I were to define a supercell storm in as few words as possible, I would probably just define it as a storm that has a rotating updraft. So, and the fancy word for this is mesocyclone, as most in the audience probably know. Takes little imagination to see the updraft scale rotation when you look at supercells in time-lapse imagery such as this. As I mentioned, virtually all high-end tornadoes are associated with supercell storms, but also the biggest hail on Earth comes from supercell storms. I would say any time you hear a hail report of exceeding 1 inch, it's virtually certain to be a supercell storm. Certainly 2-inch diameter hail and up, guaranteed it was a supercell storm that was responsible for it. When we look at radar imagery, the signature is very distinctive in reflectivity. It's the hook echo, which is an appendage on typically the right rear flank of the storm. And when we look at velocity data, the radar in this case is to the south of the storm. So the green and red couplet represents inbound velocities adjacent to outbound velocities. The radar can only see the component parallel to the beam, but that couplet is typically used to infer the presence of the mesocyclone. And in this case, notice that the mesocyclone rotation is co-located with the tip of the hook echo. So this is actually not the tornado. This is the mesocyclone. So this is a scale that's several kilometers across. The tornado, if there is one, and in fact, at this particular time, there was not a tornado present, although a tornado developed a little later. The tornado may or may not be resolved by the Weather Service radar network, depending on how close the radar is to the tornado. This is why we typically put radars on trucks and drive them to the storm, because then we have the resolution needed to see sub-mesocyclone scale details. So as far as tornadoes go, I don't have enough time to teach a whole course, of course, so you'll get the very abridged presentation. I've gone back and forth over the years on how I talk about how tornadoes form. I'm going to start with the end part, because that's the part that's the easy part, and then kind of work backwards. So the end part is just you have angular momentum that you contract to a small radius, and voila, you have an intense vortex. So this is something everybody's familiar with inside and outside of science. It's the same fundamental physics that you observe when you watch figure skaters spin faster or water go down the drain. All vortices in nature, all intense vortices get there from the result of contracting angular momentum to a small radius, period. They all do. Questions are, where's the angular momentum come from and how did it get contracted? In the figure skaters case, they're giving themselves angular momentum by the way they kick their feet and using the ice as leverage. In the case of the drain, the angular momentum maybe came from somebody getting out of the tub or into the tub. They move the water a certain way, torquing the water. And then the convergence just comes from the water collapsing toward the bottom of the drain. When we look at things more naturally, fire whirls are an example of an intense vortex. In this case, the convergence is driven by the intense heat of the fire, creates an intense updraft, and from mass continuity, air's got to come inward. Where's the angular momentum come from in this case? Not so obvious. Maybe it's wind getting, encountering obstacles on the ground in different ways and getting torqued that way. In the case on the right, it's much more straightforward where the angular momentum is coming from. It's coming from the box fans. No, this is not Greg Jenkins' backyard. But you're probably going to try this at home, right, Greg?
Yeah. It's cool.
You're not a pyromaniac, are you?
Well, that's a cool experiment right there.
But yeah, in this case, the convergence is the angular momentum's coming from the fans. The fans are also probably contributing some convergence, but the flame is also generating an updraft and convergence. And then kind of the less spectacular example than the human-made backyard fire whirl is the dust devil. But same basic idea. There's a heat plume there associated with a boundary layer thermal. So air is rising, there's associated convergence, and if there's any angular momentum present, in this case, the angular momentum is probably tied to just coherent turbulent structures that are ubiquitous to the boundary layer. And if an updraft finds itself at the right time and right place over one of these, voila, dust devil. Hurricanes, we understand the angular momentum source. It's pretty straightforward in this case. It's ultimately the Coriolis acceleration. And then the convergence of the angular momentum is brought about by the hurricane internal dynamics drawing air inward and upward into the eye wall. And then when it comes to tornadoes, the questions that people in my community have tried to answer over the decades is where's the angular momentum come from? And what's causing in the storm, what's allowing this to happen naturally beneath the supercell updraft? And why does it happen only in some supercells and not all of them? So one thing I failed to mention is that the majority, large majority even, of supercell storms don't make tornadoes, which maybe sounds contradictory to my claim that virtually all headline-making tornadoes are associated with supercell storms. It's not the same thing as saying that all supercell storms make tornadoes. In fact, most supercells actually don't make tornadoes. So what's different from one storm to the next? So if we put our storm chasing hat on and we're looking at a storm here on the high plains of the United States, this is eastern Colorado. We're looking toward the northwest. This is a supercell storm. You can see the rotation in the updraft. The striations there are reflective of the presence of a mesocyclone. At the ground, there's wind blowing toward the storm approximately. Up above, there's wind with a stronger westerly component. And that variation of wind with height is wind shear. And the presence of vertical wind shear implies that there's horizontal vorticity. And if there's a component of the airflow aligned with this horizontal vorticity, then we have what's called streamwise vorticity. In other words, the axis of rotation is closely aligned with the direction of the airflow toward the storm. And so this is like football spin, assuming you can throw a spiral. If you're a professor at Penn State, it's a requirement that you be able to throw a football properly. At least that's what I was told when I got here. Were you told the same thing?
No.
Yeah, Jerry and Greg, okay. Well, no comment. All right, we'll get rid of the footballs and we'll replace it with vorticity vectors in black, and the magenta arrows give the sense of spin, local spin associated with the vorticity. So the mothership in the sky appearance, the striated updraft, this is just a visual manifestation of lots of individual air parcels, each possessing vorticity that's reoriented from horizontal to vertical as air gets sucked into the updraft. But this actually is insufficient to make a tornado. This is one of the things we learned even as far back as the 80s. And that's because if you look at the orientation of this rotation, it's only becoming vertical some distance above the ground. In other words, the horizontal spin is only being transformed to vertically oriented spin as it rises away from the ground. But a tornado, by definition, is this intense vertical column of vertical vorticity that extends all the way to the surface. It's tempting to wonder, well, can't the horizontally spinning air just go horizontal and then abruptly upward? And the answer is it can, once you already have a tornado. In a tornado, the air just comes in horizontally and then turns straight up. In fact, that's called a corner region flow. But before the tornado gets there, the air is not doing that. So we can't really invoke that mechanism to explain how the tornado gets there in the first place. So instead, the process that gives rise to the tornado has been thought for decades to involve sinking air and downdrafts. And in this case, in the photo, you can see rain falling on the right side of the slide. And the rain, much of it evaporates. Some of it does, of course, not all of it does. A lot of it ends up on the ground, but the air that's getting pulled into the storm's front flank through that rain is chilled by evaporation. And there's also some hail melting as well, but it's predominantly evaporatively cooled air. So this air sinks as it approaches the storm. And along the interface between the evaporation region and the ambient air, there's a temperature gradient horizontally. So it's warm in the ambient, cool in the interior. And that horizontal gradient in temperature is a source of horizontal vorticity. So there's two vorticity sources here, or two ultimately angular momentum sources. One is the temperature variation on the edge of the evaporatively cooled rain region, and the other is just the ambient vertical shear in the environment. The ambient shear in the environment gives rise to the overlying mesocyclone, but this precipitation associated horizontal vorticity generation, this is involved with air sinking toward the ground, and the horizontal vorticity can be tilted upward as the air sinks to the ground. And this allows vertical vorticity to occur essentially all the way down to ground level. And if we now zoom in on the tornado or incipient tornadic region, at this point now we've got angular momentum about a vertical axis, and whether we get a tornado or not really just comes down to whether there's adequate convergence or not. So one of the things we've learned from field work and from simulations is that if the downdraft air is too cold or the suction from above is too weak, we just get broadly swirling rotation at the surface, and it never reaches tornado strength. If the air is only a little bit cold and there's also very strong suction from above, then you get tornado strength rotation through stronger convergence of angular momentum. So this is air that's come through a downdraft. It's always going to be at least a little chilly, but the tornadic storms have air that's only slightly cooler than the environment typically. So how cold is a little cold? We're talking just a couple degrees Celsius, whereas storms at a very cold outflow, it could be 5 to 10 degrees Celsius cooler than the environment. And one thing I didn't address is this suction from above. Supercells, one thing that distinguishes them from non-supercells is that supercells have a very strong dynamic pressure gradient. So their updrafts are driven not just by buoyancy, but by a vertical variation of dynamic pressure. And that causes air that's not buoyant, air that wouldn't rise on its own. It's air that's below its level of free convection to be accelerated upward very rapidly. You can have 20 meter per second updrafts a kilometer above the ground owing to these pressure gradient forces, even for air that's negatively buoyant. So here's an animation showing it. It's, you know, getting past the cartoons. Like this is, you really can see this stuff if you set up a camera. This storm came awfully close to making a tornado. You can see the rain on the right side of the slide, clouds getting sucked out of the rain and lifted. So the storm is forcibly lifting negatively air upward. And as that happens, the rotation is quite intense. And in fact, there's a brief funnel that develops there. So even though this didn't go on to make a tornado, I mentioned most supercells don't make tornadoes. This one came pretty close, but it's really nice. I still show it even though it's non-tornadic to show you that the same processes occur in supercells, whether they make tornadoes or not. One twist is that all of our theory of the last few decades is based on the assumption that environments are laminar. Theory, it's just too complicated to deal with all sorts of individual realizations of turbulent boundary layers in the environment. So now we have the computing power to actually simulate storms in large ensembles, each with its own slightly different turbulent environment. And I'll just say, this is hot off the presses stuff. One thing that's been exposed when we include a turbulent environment is that there might be another pathway to tornado making than what I just summarized in the slides leading up to this point, where basically you have coherent turbulent structures, which near the ground take the form of very small scale longitudinal rolls. They're shallow. These are surface layer phenomena, counter-rotating vortices aligned with the wind, and they can cause vortex lines to buckle upward. And if a storm moves over one of these, it's kind of like pulling on a snag in a sweater. It can yank these vorticities upward and intensify them potentially to tornado strength. So that would be a whole other talk on its own. So we're not going to talk about that now. So what are tornado researchers still trying to learn? I mean, I don't mean to convey that it sounds like we figured it all out, because obviously we're all here because understanding does not guarantee prediction necessarily. So some of the limitations are technology-wise. I mean, satellites are only seeing what's way up here. Radars are only seeing stuff where there's rain. And then unless you're right next to the storm, there's also a radar horizon issue. So you're not seeing a lot of the key business district of the storm. And then you've got a resolution issue as well. Radars are typically not resolving tornadoes. They're only resolving the mesocyclone. Some of our hamperings are due to lack of scientific understanding, though. So they're not just technological. I mentioned that some storms make tornadoes. Most supercell storms don't. Here's an example of a non-tornadic storm. This is the mother of all mesocyclones. Really intense mesocyclone rotation and really impressive hook echo. And yet this storm did not make a tornado. And if we contrast that with this storm did make a tornado, but the radar signature is relatively unremarkable. The mesocyclone is nowhere near as strong as the mesocyclone in the former case. So it's not just as simple as, oh, we have a Doppler radar network, we'll just identify the strongest mesocyclones, and then once they exceed a threshold, we'll issue a warning on them. There's much more to it than that, unfortunately. And then there are other storms that aren't even supercells, which I said I wasn't going to talk about non-supercell tornadoes, but I will say this in passing, and that is that these can have really unremarkable reflectivity signatures, sometimes velocity signatures too. In this case, the velocity signature is pretty good, but in the polarimetric radar data, we see a debris signature right here. And in fact, this is the proverbial needle in a haystack, very short-lived tornado embedded in just a whole lot of heavy rain. These are a nightmare to issue warnings for. And I would say we have almost no skill at all at issuing warnings for that sort of event. And then the last thing I want to close on is the topic of we're kind of butting up against predictability limits. I had a lot of conversations with a former colleague of mine, Fuqing Zhang. Unfortunately, he's deceased now, but when we overlapped here at Penn State, he often spent a lot of time telling me I was kind of wasting my time studying the physics of supercells. I should start doing more with predictability. So I did get my scouting merit badge in predictability a few years ago. But here's a nice example. This is a tornado outbreak. We have lots of supercells on the radar, but only a few at one time are making tornadoes. Most aren't. Even in the worst of all tornado outbreaks, not all storms typically make tornadoes. And even the ones that are making tornadoes aren't making tornadoes all of the time. So what causes tornadoes or supercells to make a tornado at one particular moment and then not at another moment, and some storms don't make them at all? This is how I got my predictability merit badge. This 25-member supercell ensemble. Each of these is in an identical environment. These white swaths are the tornado swaths. The environments are all identical. The only thing different are the random number seeds used to introduce essentially what would be undetectable temperature perturbations in real life. And you get a whole range of tornadoes from EF0 to EF3, and some storms don't make tornadoes at all. This was really disturbing to me, which suggests that there's some real limits to intrinsic predictability when it comes to predicting supercell behavior. These are all supercell storms. So the supercell itself is highly predictable, but predicting exactly when and where the tornado will form and how intense it will be it's essentially unpredictable. It's a lot like the Price is Right Plinko game. And then the last thing, this is something that we're doing here at Penn State, is getting temperature data in storms. So we stole the idea from Twister. In Twister, the first Twister film, not the second one, they launched all these little balls into the storm. And what we're doing is launching lots of small probes that are attached to small balloons. So we can launch these by the dozens, rapid fire. We can get one up every 30 seconds or so. And the storm pulls these through the forward flank. We don't have to be in the tornado to do this. So maybe it doesn't make for the most exciting television. But what we get, this is a really cool animation down here in the lower left. Look at each one of these things is one of our probes. It's kind of like the old video game, Asteroids. I'm dating myself, where you're kind of shooting at the asteroids. We're kind of firing these things off into the storm. The storm's own wind field sucks them through the storm. And as it does so, it's pulling them through these key temperature gradients and precipitation areas where we need measurements. It's where you can't get remotely sensed temperature data. So we're really good at getting radars on trucks to storms and measuring the winds and what's going on. But if we're in the business of science, which is the business of understanding why things happened, and that requires knowing the forces behind them. And the forces in this case are pressure gradient force and buoyancy forces. These all require thermodynamic observations. We have to get beyond the radar. So this is what the analyses look like when we do that sort of thing. It's pretty darn cool stuff in my opinion. So that's all. Thank you very much for your time and for the invitation. Thanks, Jared.
Thank you. Any questions?
Is there any question, Ramon?
No, not yet.
Yeah. Question. Besides the key ingredients that you mentioned, what is one finding that you kind of took away that you would say develops tornadoes?
Yeah, so to get supercell storms, you need at least some CAPE. It doesn't have to be an extreme amount of CAPE. You don't need to have 4,000 joules per kilogram. There are low CAPE supercells, but what you absolutely have to have is wind shear. If you were to force me to put some numbers on it, I'd say you need about a 40-knot differential between the surface wind and the 6-kilometer wind, so nominally 500 millibars. If you've got that, then you potentially could get supercell storms. But then to discriminate between tornadic and non-tornadic supercell storms, kind of the state of the art is looking at the strength of the low-level shear, how much the wind varies over, say, the boundary layer, or maybe even a shallower depth than that, lowest few hundred meters. On high-end tornado days, we sometimes have 50 knots differential from the bottom to the top of the boundary layer. And then another thing that we look for is low cloud bases. So low cloud bases, has nothing to do with the fact that, well, if the cloud base is low, it's easier for a funnel to connect with the ground. It has nothing to do with it, because you can get tornadoes from high cloud bases. It's just that low cloud bases imply high relative humidity in the boundary layer.
What about the
well, yeah, that's a different topic, but the high boundary layer relative humidity suppresses evaporation so that the cold pools aren't excessively cold. There's going to be some cold air wherever rain is that's unavoidable. Even if it wasn't evaporating, just the mass of the rain is a source of negative buoyancy. But having low cloud bases seems to prevent the cold pools from being excessively cold, and excessively cold pools is well known to short circuit tornado formation. They even got that right in the Twisters film. I don't know if you've seen that yet. Hopefully I didn't spoil it for you, but yeah, they were going to do this tornado modification to weaken cold pools. It would actually work if you could modify the cold pool. It's just that shooting a few rockets from the back of your pickup truck is nowhere near enough stuff to alter, it's about 1,000 cubic miles of atmosphere you'd have to modify. I mean, a storm is roughly 10 by 10 by 10 miles. It's 1,000 cubic miles. Shooting a few rockets is not going to have much of an effect.
I think Joseph raised his hand. Do you have questions?
I did not. I actually did the clap function.
So was Fuching right or wrong in your mind?
The thing is, I know you can picture Fuqing saying, Paul, you're wasting your time, for those who knew Fuqing. Yeah, I mean, well, yes and no. I actually thought he was right, which is why I wrote this the article, the 25 storms with the random perturbations, and they all behave differently. That was motivated by and inspired by Fuqing. But then one of the things I found in one of the simulations, I was like, this storm doesn't quite look like it's making a tornado for the reason I always thought it makes tornadoes. So then I analyzed the bejesus out of that storm and found that what we thought we knew about the physics of supercells might not actually be right. Mm-hmm. So in that case, Fuqing is wrong, that there actually was still a lot to be learned about the dynamics. Now, whether that additional learning improves predictability or predictions remains to be seen. It might not. Unfortunately, you know, we all like to think, oh, if we could understand this better, it'll improve our predictions. Sometimes, but not always. Sometimes, we know how cumulus clouds form, but I'm not able to say whether the next cumulus cloud is going to form over this building or over Walker Building or over the Penn State Creamery. So there's sometimes just intrinsic predictability limits, and sometimes we can predict things pretty well without understanding them that well, actually, using statistical techniques. So, but you don't know until you try, and all of us here in the business of discovery and learning and turning over every stone. So, yeah, I'm not going to tell anybody that we shouldn't keep learning for the sake of learning. Yeah.
Thank you, Paul.
Yeah.
Our next speaker will be William Parker from Jackson, Missouri National Weather Service. So Bill Parker is the meteorologist in charge in Jackson, Missouri of the National Weather Service, and he's a graduate of Jackson State University with a bachelor's degree in meteorology. And prior to becoming the meteorologist in charge at Jackson, he worked in New Orleans and Shreveport in Louisiana. And he's very passionate about severe local storms, hurricanes, and also exposing students of color to meteorology. And
you just improved the state's education health by taking them from Mississippi to Missouri.
Jackson, Mississippi.
People are so happy for what you did.
It's Jackson, Mississippi. All right. Just want to say first, thank you guys for having me here with you guys through this conference. There's so much I've learned in being here over the last day or two. We're going to talk about some of the things we utilize when it comes to forecasting, messaging severe weather in the Mississippi area. The Jackson, Mississippi office covers a 3-state area. We cover much of Mississippi, the eastern part of northern Louisiana, and then we have 2 counties in the far southeast part of the state of Arkansas that we cover as well. You could go to the next slide. So just a quick outline. We're going to talk about messaging, hazardous weather, what's more important, categories versus impacts, severe weather prediction tools, things that we use in the office to try to predict weather. Some of the things have already been covered, and then some real-time diagnosis. So impact-based messaging is one of the things that we really try to focus on at the National Weather Service in Jackson. Changing the focus from traditional jargon that meteorologists understand to using language that the general public understands. Often times as meteorologists, we speak from a scientific background, but we really need to give information to the general public that they understand and information that will allow them to make decisions that will be good for them. Rather than messaging outlooks and categories, convective outlooks are good, but we try to speak directly to what the impacts are and what the general public can expect. So when we talk about impact-based messaging, it's about what is the message that matters most to the people. And Patrick Burke kind of talked about this. First, they want to know, what are they expecting? When is it most likely to happen? and where is it most likely to happen. So those things are very, very important. We find out to the people that we serve on a daily basis. So when we talk about, which is more impactful, let's look at this. Let's say a high chance of marginal severe storms or a slight chance of significant severe storms. The slight chance of significant severe storms is probably going to be more impactful in this case. Because the marginal severe storms may not produce a whole lot of damage, whereas we know that in this case, a significant severe storm can, if you only have one, it can produce some significant damage across an area. What's more impactful here? A fast-moving Category 2 hurricane with a small wind field, or a slow-moving tropical storm that produces 2 to 3 feet of rain. In this case, it's not the category of the tropical storm. I mean, of the cyclone. It's the size of the cyclone. And so the tropical storm, even though it's a lower category than the Category 2 hurricane, it's more impactful. And I want to use a recent event just to have you think about Hurricane Beryl. Hurricane Beryl, as it moved through the Caribbean and then moved into Texas, it reached Category 5. But as it reached Texas, it weakened down to Category 1 before it made landfall in Texas. Along with that hurricane, there were, I think, 64 fatalities in all. 28 of those fatalities were in the Caribbean. 36 of them were in Texas, when the storm was approaching Texas as a Category 1 and weakening to a tropical storm. And but a majority of those deaths in Texas happened after the storm pretty much cleared out. A third of them happened, just from the heat, because people lost power. They couldn't. And in Texas in July, you're reaching temperatures around 90 degrees. So a lot of people died from heat-related deaths and not directly impacted by the storm itself. So those are things that we talk about. When we're talking about impacts, how will the storm impact individuals? How would it impact the citizens that we're called to serve? Next slide. Here's another example. EF2 tornado that has a narrow path. May not hit much, it could hit something, or a destructive severe thunderstorm that impacts a much larger area that does not produce a tornado, but it knocks down trees everywhere. So again, impacts are important. Next slide. So things that we use is we do use ensembles when we're trying to give decision makings and give decision makers enough head time. The more ensembles that are in line, that's what we try to use. So as we use variant runs, the ones that are more in agreement are typically what we typically will go with, provides possible outcomes, and then it also demonstrates the likelihood of what may be coming our way. So next slide. We try to use machine learning analogs, and with machine learning analogs, it helps us to compare past weather patterns to forecasted weather patterns. We really like in the National Weather Service offices to look back at past events and especially events on special days and similar atmospheric conditions to try to predict what may be coming around. So it highlights signals for us to take a look at, and it derives, probabilities of where an event may occur, and even can give us some clues into the magnitude, the intensity of what that storm may produce. So here's one of the things that we sent out to our partners, mainly to our emergency management partners. This is what we call our week 2 hazard assessment. So we basically have different categories that we forecast. This was actually the one for this week. And so it's based from uncertain to -1, well, to -2 to +2. And so if it's a +2, that means we have a very high confidence that this particular weather will be seen in the next 2 weeks. If we have a -2, it means that we're pretty confident that it's not going to occur. And so since it's summer, we just blank out freezing temperatures, winter precip, dangerous cold. We're not going to get that in August in Mississippi. But notice we have a fair confidence that we're going to see some dangerous heat. We have fair confidence that we'll see fire weather. If we were, ensemble showed us something of maybe a tropical system coming in, then we may bump that up on the positive side, but probably not seeing anything. And so that's why they have a -1. And so this is something that our partners really, really like to see. This tool was created to give our partners at least some look into at least the 14-day period on our confidence of any particular weather that could cause them problems within a 2-week period. And the reason why we did it is because we talked about this yesterday. We had a lot of emergency managers that was looking at social media, and they were looking at things that weren't necessarily true. People were predicting stuff that wasn't true. And so we started doing this so that we can kind of debunk a lot of that false predictions that sometimes will show up in social media. So next slide. So again, probabilistic forecast, this is basically just high and low temperatures. Again, ensemble models help us with this in forecasting temperatures out in the long-term period. So as we move into near term, things that we'll look at, that we often look at, is we do mesoanalysis, the HER, high resolution guidance, and then I'm not going to beat up WAFs because Patrick pretty much did a whole talk on that. We'll just kind of slide through that slide. So in the forecast office, mesoanalysis is key to a lot of things that we do. Forecasters have to analyze actually what's going on in the atmosphere to really understand how to communicate what they're thinking, what they're seeing, as it relates to any significant weather that's going to show up. And so we do a lot of analysis in the office. It's not as the way it was a lot of times. Now we've got a lot of computers that do the analysis for us, but we still have some forecasters in our office that do hand analysis. And so it helps us to anticipate, the low probability or high probability of events that we think are going to be impactful. And it allows warning forecasters to anticipate what is coming and helps us to, provide as much lead time as we can possible. And then high resolution modeling, the HER, is tremendously used by National Weather Service forecast, especially in our office. Trying to see storms and how they're going to develop ahead of time, where they will be is so important. And so we run high resolutions modeling often in our office just to see what is generating. Again, this helps us anticipate, timing. It helps us anticipate where they will form, the location. All of those things are important as we communicate when storms will develop to our partners. And again, we use 1.0 forecast. It's again, Patrick talked about, it really helps us in that 0 to 6 hour time frame. It's that time taking a look at it, between watches and warnings and helping us to get some of those things out. And so this was an event where we had a large hail event, and 1.0 forecast did a really, really good job in helping us get information to our partners in time to let them know about these developing cluster of storms that will produce hail. And then the radar is probably the primary tool, especially in the near term, that we use. Again, you know, for us, it's a lot of severe local storms that we're looking at. But you know, we're not too far from the coast where we don't deal with hurricanes and such. And then the radar is also beneficial to us even in the wintertime. Our office in Jackson is called Action Jackson. So we really deal with weather all throughout the year. I don't think we ever get a break. At least my forecasters don't think we get a break. And so primary tool is that we utilize is the NextRad WSR 88D. It helps us, especially with those local severe storms that we get in our area. And then, you know, just the various tools, like I'm sure you guys are familiar with this, the tools that we use for warning and aiding and confirming tornadoes. Paul talked about, you know, the SRM, storm relative velocity picture, but also what's important for us in making sure that we confirm and predict tornadoes is CC. And CC is that box in the lower right. And basically what CC is it looks at the uniformity. So if everything that it sees, let's see, raindrops all the same size is going to be one, but when there's variation, and with tornadoes pick up debris and throw it in the air, and so the sizes of that debris is different. And so the correlation coefficient begins to drop out. When we see dropping out the correlation coefficient in line with what we see in reflectivity with maybe a hook echo and then gate-to-gate velocities, that lets us know that we have a tornado on the ground. And we utilize that quite often. And it's not just to detect, but also sometimes from this, the deeper that CC gets, the more intense that tornado may be. And so, you know, we may have a tornado warning, and often in our office, we'll have to upgrade sometimes to what we call a tornado emergency. And so radar helps us to make those decisions. And then we use satellite for different things in our office, especially with fire weather. We use, you know, lightning tools that are in the latest satellite series of GOES. That helps us out quite a bit. We can see, you know, cleared on some days. It may not be a lightning generated. A lot of times, especially in Mississippi, it's not lightning generated fires that start, you know, somebody who threw a cigarette butt out the car on a clear, dry day, and now we got smoke. And so we can inform our partners areas where we see fires based on satellite. Next slide. Same thing. This is more, again, using satellite-derived tools to, you know, predict certain things. Severe probabilistic guidance is utilized, especially with hail, wind, and tornadoes, and then lightning cast. That's all I have on that. Any questions?
Do you ever use the lightning products for, like, so you put out a severe thunderstorm warning? Do you actually use any of the lightning products from satellites to say vivid, or are you using ground-based? Like some of those ground-based products using low frequency?
Yeah, well, yeah, doing some, especially when we're doing severe storm warnings, and we're using lightning products from satellite because, you know, usually the more lightning strikes that you see, the more intense that storm likely is and is becoming. And so, yeah, there are times where we use lightning. And I remember exactly the Rolling Fork tornado that we had a couple of years ago. The lightning on that storm was tremendous. And it was, the field of it was really, really large. And so when we're using, when we're in severe weather mode, we're really looking at every tool that we can that will give us some information on this storm so that we can put out the right information to the public.
How does the topography there interfere or influence the assessment of potential hazards? Like,
I didn't hear the first.
Topography, the mountains.
Oh, topography. So in Mississippi, it's not a whole lot of topography, not like here in Pennsylvania. Okay. It's pretty flat. Now we have hills that we call bluffs, you know, but it has very, very little impact on you know, storms in our area. But matter of fact, we was talking to Ashley Evans, who's the MIC here at State College, and he was, you know, just talking about how the topography here and tornadoes here in Pennsylvania, things that we see in the deep south, you know, is totally different from tornado formation, what we see, to tornado formation, what you guys see. It doesn't take as much storm relative velocity here to get a tornado, whereas down there, we want to see it amp up, you know, definitely be above 30 knots or so.
You?
I had a quick question. I know you said you all use a lot of analog data, but do you guys have a researcher in office, and/or is anyone kind of studying Mississippi's weather over like across like the 30 years? And how do you all kind of use that? And also the forecasting that you guys apply. And also, too, another part of that question is like, what is something that sticks out for your weather that you guys are commonly known for?
Well, I'm going to answer the last question first, because it's
okay.
We're really known for tornadic activity that we see. Now, we get everything down in Mississippi, but our office is really known for the tornadic activity that we get, and especially from the standpoint of long track supercell tornadoes. It's nothing. I've been in this agency 30 years working for the National Weather Service, and I was in Shreveport, Louisiana, just the office to my west. And in that office, in the 22 years I spent there, I've seen one EF4. I've been in Jackson 8 years, and I've seen 3 EF4s. And I've never in Shreveport saw an 80-mile track tornado. In Jackson, I've seen over 50 miles several times, tracks. So that's what we're known for in the Jackson area. Now, on the other side, and I like to say, especially to students, the really thing that I really like about the Weather Forecast Office and its operations is, if you're interested in research, even though you're coming in and you're doing operational forecasting, you can still do research. And yes, we have people in our office who still do a lot of research, who focus in on our area, and trying to help us get an edge in understanding the storms that impact our area so that we can better inform the people that's in our office. So in the forecast office, there's research, there's, you know, operations. I mean, we got to have people who can communicate and don't mind communicating to the public. That's the great part, I think, about the National Weather Service. You get a taste of everything.
I have a question, actually. Something you touched a lot about the socio-economic part. Would that be another talk or what?
That's a little bit later.
That's the last talk. We asked him to specifically do that.
Yes, sir. We're going to talk about that a little bit later.
I think now we'll have a 5-minute break. And
yeah.
We'll reconvene at
2:40.
2:40.
And we'll
4 minutes.
Hello, Lisa.
Hi.
How are you?
Good. How are you?
Good. We're gonna go again, and I just want to give a short intro on you, and then we'll let you get to this important work. Given that we have a tropical storm right now.
We do, yes.
your presence is welcome. So, Doctor, can you tell me how you say your last name?
Bucci, like Gucci, but with a B.
Bucci?
Bucci.
Okay, so Dr. Lisa Bucci is a hurricane specialist at the National Hurricane Center in Miami, Florida. She holds a bachelor's degree from my alma mater, University of Michigan, Go Blue. And a master's from meteorology at Florida State and her doctorate from the University of Miami. And her research, she's looked at, she used airborne and space-based technology, basically Doppler wind LiDAR in tropical cyclones, tropical cyclone analysis and prediction. And today she's going to give us her talk that we really appreciate.
Thank you so much for that introduction. Are you able to see my screen and my slides?
Yes.
Great. Okay. So today I was asked to talk a little bit about the challenges in predicting tropical cyclones and messaging their hazards. You heard from my friend and colleague, Dr. Philippe Papin, yesterday, giving you some of the basics about forecasting tropical cyclones. So today, in terms of the challenges we have predicting tropical cyclones, I thought I'd go over 3 key areas. The first being the genesis, or the beginnings of the tropical cyclone, and the challenges we face there. Next, the intensity changes, especially the rapid changes that we can face, and the challenges predicting that. And then some of the track forecasts, especially the sensitive ones that we have difficulties. So in terms of genesis forecasts, what we typically do is that we look at a disturbance and we split it up into a time frame of 48 hours or 7 days. And we give that disturbance a probability of forming within those time frames. And those probabilities fall within a low category of forming all the way up to a high, so low, medium, and high. And you'll see on this graphic, we have a depiction of various genesis areas over a period of 7 days. And the yellow is the low, orange is that medium, and red is the high. And you're looking at the 7-day outlook. So this is an example of a genesis forecast that worked well. It was in 2023, last year, and it was the disturbance that eventually became Hurricane Hillary, which ended up impacting the southwest United States and California. We put this disturbance into the forecast almost 7 days before formation, which is a really long time when you think about forecasting these days. We raised our probabilities to the high category 4.5 days before formation. So all in all, we consider this a good forecast. But forecasting in the Eastern Pacific, genesis is relatively easy. When we start looking at areas where we have difficulty predicting genesis of tropical cyclones, we look at our example of Idalia. Idalia actually came out of a disturbance that can often form over Central America. We call it, sometimes you'll hear it called the Central American Gyre. And in it, we identified a disturbance, but only 60 hours before genesis. And we weren't quite sure if it was going to form. It actually ended up forming much sooner than we were expecting. So we only raised it to the high category a day and a half beforehand. And those are for the 7-day probabilities. For the short-term probabilities, we only made it into the medium category. So we have these areas where it's difficult to predict genesis. The Central American Gyre is one of them. Another example is oftentimes when you get fronts and the tail end of that front could spin up into a tropical cyclone. We are not quite sure if it's going to do that. We base a lot of our genesis forecasts on multi-model products that provide objective guidance. This is models from all over the world that have been reliable models from all over the world that give us an idea of whether or not a tropical cyclone is going to form or not. And from that, it forms objective, statistics, and we put that into our genesis forecast. We also will use ensembles and the formation of lows within various ensembles like the GFS ensemble or the ECNWF ensemble, and look at that to help influence our prediction. But we don't have a ton of guidance for this. And so, in terms of areas of active research, this is definitely one of them. So challenges forecasting the genesis of tropical cyclones is part 1. Once you have a tropical cyclone, you have to build a forecast, which means you have to say where it's going, how strong is it going to be, and how big is it going to be. So today I'm going to talk about the challenges that we can have with track and intensity, but just know that we are, in terms of the 3 of these, really bad at predicting how big a storm is going to be. This is probably the area in which we can make the most improvements in the coming years of predicting the sizes of storms. So if you're looking for areas of research, this is definitely one to consider. But for today, we'll just be talking about track and intensity challenges that forecasters face these days. So first talking about intensity, one of the biggest challenges that we face in terms of forecasting the intensity of a storm is usually rapid intensification. In 2023, we had 9 storms rapidly intensifying, 5 of which impacted land. The ones that I've highlighted in green are the ones that we predicted correctly rapid intensification before they occurred. And that was Hillary and Idalia. But there were 3 storms in the East Pacific that ended up making landfall in Mexico, in which we did not do a good job predicting rapid intensification. And the most glaring one is Hurricane Otis, which rapidly intensified tremendously within a 24-hour period. And it unfortunately ended up hitting a major metropolitan area. It hit Acapulco and caused quite a bit of devastation there. So let's take a closer look at what happened with Hurricane Otis. So Hurricane Otis, you know, it was a short-lived tropical cyclone that lifted up out of that monsoon trough. And then from there, it intensified, and it did not stop intensifying until it made landfall. It made landfall as a Category 5 storm, again, in Acapulco. In terms of our forecast, this is an example, or this is what our forecast looked like over those days in blue, with the best track, or what actually happened, in black, and those different categories shaded. And what you can see is that we were predicting it to be maybe a tropical storm. Eventually, we were predicting it to get up to a Category 1 storm. We were not expecting it to make it to a Category 5 storm. And why didn't we expect it to make it to a Category 5 storm? Well, all of our guidance did not indicate that it would make it to a Category 5 storm. So if we look at the forecast from, these are the GFS forecasts overlaid with what actually happened, the GFS and all of the global models, I'm picking on the GFS, but all the global models did not predict it to intensify. If we take a look at some of our regional models, or some of the models that actually specialize, dynamic models that actually specialize in the prediction of tropical cyclones. So these are the Hurricane Worth and the HAVs. None of them predicted it to intensify into a Category 5 storm. They maybe made it up to a Category 2, but most of them, all of them, did not expect it to make it to a Category 5. We even have statistical models, and these have often been some of our best models predicting intensity, and none of them were expecting it to make it into a Category 5 storm. Even on top of that, we have additional statistical models that specialize in rapid intensification. And typically you'd see this grid, and some of the warmer colors are, that it is definitely going to go through that, 30% or 30 knot increase in 24 hours, which would be rapid intensification. And most of our specialized statistical models did not even predict that this was going to happen. So, we still have a lot of work to do catching these extreme outliers and being able to identify them, because there's a possibility that this, could happen, within the United States, as it did to Acapulco. And actually, we can look at some of the Category 5 storms that have made landfall in the United States. And those have been the Labor Day hurricane of 1935, Camille in 1969, Andrew and Michael in recent history. And we can look at where these storms were 5 days before landfall. And what you can see is that of those storms, only Andrew existed as a tropical storm 5 days before landfall. But, so we can ask, okay, 5 days, I only need a few days to make plans for myself as an individual. Where were they 3 days ahead of time? Well, 3 days ahead of time, we had the Labor Day hurricane, which was only a tropical storm at that time and only 40 miles an hour approaching the Bahamas. You can see that it rapidly intensified closer to land. You had Camille, again, approaching the tip of Cuba as a tropical storm 3 days before landfall. You had Andrew, still a tropical storm. And Michael, one of those disturbances coming out of Central America as a tropical storm before making it into the Gulf. So all of these cases were only tropical storms only 3 days before landfall. So, you know, studying this and understanding it and being able to predict it is utterly important and an active area of research for the forecasters and the general forecasting community in tropical cyclones. We are getting better at this. If you only look about a decade ago, in 2005 to 2017, we had a median error in terms of predicting RI of 22 miles an hour, versus within the past couple of years, we're down to a low bias of 13 miles an hour. But still, we have work to do, and we have work to do, especially catching some of those extreme outliers. So let's talk a little bit about track forecasting. I think, it's pretty well known that our track forecasting has been getting better over the years. You can see that over the decades, as this colorful graph shows, the cooler colors being from the 60s and 70s. As you get closer towards the zero on the y-axis, that's a better forecast. And the lines have been moving towards that zero over the decades, with even some possibility of the 2020s being quite similar to the 2010s. So, there's some discussion going on over whether or not we're plateauing in terms of our ability to improve track forecast with our current track forecasting technologies. But we've been improving. That being said, we still have challenges. So here are a few examples of some of the recent challenges we've had. One of them from last year was actually Tropical Storm Philippe. So as you can see on the left-hand side, where all the red is, that's actually where Tropical Storm Philippe went. And in the blue is all the official forecasts that were made for Tropical Cyclone Philippe, which do not lie close to where the storm actually went. So what was going wrong? Well, it was a slow-moving storm. It was likely that intensity played a role in the large track errors. There would be times when they would be forecasting it to strengthen and grow within the atmosphere and catch different steering layers, or weaken and catch some of the lower lying steering flow. And it kind of just stayed in the middle. And we had a tough time forecasting it. And if you look at some of our track guidance, the track guidance had quite a bit of difficulty forecasting it. So we had a lot of model spread. Oftentimes the storm would even move outside of where any of the models had it, which is never a place that you want to be as a forecaster. And so the number of times that we were communicating how we're uncertain about this forecast, or this forecast had a low confidence within our forecast discussions, which were published every 4 times a day, every 6 hours, was 58 times. And how this affected some of our watches and warnings were that, if you switch back to this slide, you can see that Tropical Storm Philippe started to approach the Lesser Antilles. We had a call scheduled to put up tropical storm watches, and then it looked like the storm stalled out and was possibly going to turn away before reaching it. So we canceled those calls, only to a few days later have to call them back and say, no, actually it's going towards you. We're gonna have to put these watches and eventually warnings up for your countries. So yeah, it can impact how you're warning the public to prepare for possible hazards coming their way. Another example of issues that we can have with track forecasting are tracks that parallel a coast. So here is an example of Hurricane Ian as it was in the Caribbean, making its way towards southwestern Florida. Initially on the 23rd, we had a pretty good forecast, and our model guidance was where it ended up making landfall. But as you can see, as the time went on, our models started to swing northward. up towards the Tampa Bay area and then up towards the Panhandle area. And then finally, they started to come back south, back towards where it eventually actually made landfall. So this made it so that our track forecast ended up having a northward bias, as you can see here. But we have products that convey some of our uncertainty. And one of those products is the cone that you've seen likely in our website or even through traditional media or social media. But the thing about the cone that people don't understand is that the center of it only tells you where the center of the tropical cyclone is, and it only tells you or where it could be 2 out of 3 times. So it's just giving you a measure of uncertainty. Thankfully, with Ian, it fell within the cone every single forecast, which means that this forecast was actually a pretty average forecast. And every single time it fell within the cone, even though the cone is designed that 1 out of those 3 times it's supposed to fall outside of it. So we had a pretty average forecast with Ian, but the problem was that it was paralleling the coast of Florida. And this is an image courtesy of Brian Lamar from the Tampa Bay office, but he can show you here in this graphic that as with any tropical cyclone paralleling a coast, even a small wobble or a small shift of 20 miles, which tropical cyclones can do, if you ever watch them on radar, they wobble back and forth all the time. But those wobbles can end up making huge differences in the location of the landfall. And so that is why we'll often be asking people to be to have large areas of watches and warnings, because a wobble could mean that you have a major hurricane moving into your town or city. So one of the things that we've highlighted on our graphic are that the wind field, which you can see in this orange, and the tropical storm force wind field and the hurricane force wind field fall outside of the cone. A lot of people have mistaken that the cone is somehow related to the size of the storm. You'll also notice that we have highlighted the watches and warnings based on the hazards of the hurricane. And so you can see here in the reds, the blues, and the yellows, those are our tropical storm and hurricane watches and warnings. So that kind of brings me more into the messaging part of my talk. And so when we're talking about messaging hurricanes, I really agree with the previous speaker. You don't want to be talking about what the category of the storm is or where the center of it's going. You want to be talking about the hazards that the hurricane is bringing. And so when we're thinking about the hazards of the hurricane, you can break it down into 5 different hazards. The water tends to be the ones that kill the most people. So we'll often hit those first. So if there's storm surge, that's one of the hazards. The wind field, but not just the category, the extent of the wind field plays a particularly important role in the hazards that are brought to different communities. The rainfall, flooding, again, that water that we're asking people to flee from. And then wind gusts and tornadoes. This often gets it's messaged in our products. People don't seem to realize that hurricanes can also bring tornadoes with them. And then the hidden hazard that often gets overlooked is the rip currents that even distant hurricanes can bring to local communities and rough surf. So being aware of, even though the hurricane is nowhere near you, it is still possible that it is sending hazards your way when you're just having a lovely day at the beach. In terms of our key messaging that we're putting out to the public, we have a key message graphic where we're putting out what the most dangerous hazards of the storm will likely be and identifying a larger region, the region that it's threatening. We also are providing quick look graphics through this key message, and we're distributing it through our website, social media, and using it in our briefings. We have a variety of graphical products that we use to help message some of the hazards. They can be something like the earliest reasonable arrival of the tropical storm force winds with times and days of the week, so you can help prepare your property or make your plans before the arrival of the hazard, of that particular hazard. And storm surge graphics showing what the peak possible potential storm surge could be in different locality along the coastlines. These are examples from Hurricane Beryl several weeks ago. We also work with our partners within NOAA. So those are graphics that we make within the National Hurricane Center, but we'll work with other partners within NOAA, like the Weather Prediction Center and the Storm Prediction Center, to work to give us graphics about, say, the excessive rainfall outlook for a region, or the possibility of tornadoes, where they'll give us, the 5 to 2% that you can see that Hurricane Beryl brought to Texas. And finally, we're then taking that information and providing impact-based decisions, support services like what was discussed in the previous presentation, and giving media interviews to our partners, and then giving that information and working with the local WFOs, which are taking our forecasts and downscaling it for particular communities, and working with the regional emergency managers. So, I've talked about some of the prediction challenges, the messaging challenges, basically that we're trying to shift that focus from the category and the center of the storm towards those hazards, that hurricanes and tropical cyclones bring multiple hazards. And so having the public understand that they should really be thinking about it holistically, not just the winds. And then, we've been actively working with social science to communicate these effectively. A lot of times we're communicating in terms of numbers and probabilities, and people don't necessarily think that way. We do, because we're meteorologists and scientists, but it's important to remember that not everybody understands numbers the way that we do. And so we've been working a lot more with the social science community to help communicate effectively. If you ever want to check out our latest forecasts, they're on hurricanes.gov. And if you have any questions, please feel free to email me. Thank you.
Lisa, there's a question online which says, how do you differentiate prediction of intensification, hurricane intensification, from rapid intensification? And what is the lead time? So what's the criteria?
So in order for something to be rapidly intensifying, it needs to intensify by at least 30 knots within 24 hours. In terms of lead time for rapid intensification, we don't get a ton of lead time. Sometimes you get a day or two. A lot of times there have been times, and oftentimes we'll be chasing it. It'll be rapidly intensifying. We'll have to shift our forecast up to keep up with it. So sometimes they're good, but sometimes they're not so good. But we've been building tools and getting better. So at least there used to be a time where forecasters would not explicitly forecast rapid intensification. These days, they're willing to forecast the outlier. So it's getting better.
I have a question about, and maybe Chris is going to show this, but things like inundation maps. Like the average person is trying to figure out what's going to happen to them. I know you have the surge piece, and in addition to that, in your products, do you have like layering, kind of a GIS layering, where you can see like within a city where you have like higher levels of poverty, or higher levels like people of color, or access to cars? I'm sure emergency management may know this, but is there any tools like that that have been developed, that when a person can click and be like, oh yeah, that part of the city or where it's going is like very vulnerable?
Yeah, so we don't have an active tool on our website. We did just have an intern this past summer, so it's funny that you bring this up, who did a project looking at that particular thing, where he looked at the forecast and all the hazards associated with the forecast, and then layered on vulnerability indices of whether it ranged from poverty, access to transportation, because a lot of times we'll be telling people they need to evacuate, but they don't have access to the transportation to do so. Looking at communication. Do they speak? Now they are starting to become more available in Spanish. And we have we're using AI to help automatically translate some of them. We're looking into expanding that within the National Weather Service to more languages, but that being a particular vulnerability is if you don't understand the language, then how can you know what's happening? That being said, yes, he looked at all of these things and looked at the possibility of developing like a vulnerability index and saying, okay, based on the hazards, say flooding, I have an area that has a lot of mobile homes and we need to be telling them that they need to evacuate, or we need to be hitting that point of you have a lot of mobile homes and there is going to be a lot of flooding. And we need to tell our emergency managers this so that they can decide whether or not they need to arrange evacuations.
Another question I had is about, Joseph is here.
Yes. This time I raise my hand. No, thank you so much, Lisa. Fantastic presentation. As a social scientist, like what would you, I know you kind of just answered this too, but if there's anything else, what else do you think would you consider like a hot topic where you believe social scientists could really fill the gap in the current operations within the Hurricane Service, out of curiosity?
I mean, there are so many options. The communicating is a huge one. The numeracy part, like effectively translating what meteorologists are saying and putting it into a version that people can understand. I think, translating some of our products, the previous presentation gave the like what, who, what, when, or where, what, and when is this going to happen, like making sure that that message is strong and in front of everybody's eyes. And then finally, I think a lot of people, we focus a lot on emergency managers in the Weather Service, right? So the ones that have the connection to the community, but a lot of people are trying to downscale stuff to an individual level, and it's like breaking down at that level. So using social scientists to help us design tools to help them make individual attention is another area that I see kind of coming up in the future.
Thank you so much.
Yeah, a couple more questions.
What forecast changes do you think that you guys could have made better preparing for Hurricane Otis? I seen you mention it in your presentation. And also, what new considerations have you guys developed in assessing rapid intensification and alerting the public for cases like Hurricane Otis? Because that was a bit extreme.
I'm so sorry. I got about half of that. I think the audio was cutting in and out. Maybe on that one.
Sent it in the group chat.
I don't even hear you at all now. Oh no.
The chat.
Yeah, I'll check the chat. Okay. What forecast changes could NOAA have made to better prepare for Hurricane Otis? I mean, looking at all the guidance that we had, there wasn't a lot that we could have done differently with the tools that we have right now. I think part of the problem is a lack of observations. We fly, planes into hurricanes, right? And that's one of the best ways that we can get an intensity and location estimate. So we only had one flight into this storm because it's really hard to get to that part of the world. So having different technologies to be able to observe hurricanes, either flying like remotely controlled aircraft or unmanned aircraft into the storms is a possibility. Having radar, because it was near the coast, having better observations would have helped. That's the general consensus. There are ongoing studies of how we could have changed some of our modeling techniques to improve the modeling, the prediction side, but again, like a lot of that might be based on the data assimilation that you have or the data that you have available, and being able to model those like really small storms, which is just hard to do. So yeah, it's a troubling case, but one that has research actively investigating it so it doesn't happen again.
So I know you guys don't have an app, right? But given the situation,
We aren't allowed to have an app.
Well, given the situation as currently evolving, where so many people are using their cell phones, it seems to me that a case is going to have to be made to somebody to get you an app, even though you're not allowed to have an app. And then the other question I had was, do you use Facebook Live when you're talking, when things are happening like near the coastline?
So, you know, the case has to be made to Congress in order for us to be allowed to have an app. So that you know, I think has to come from a pretty large community to get them to consider it. But I am all for it since, you know, more people are living, like you said, on their phone and with apps. We do Facebook Live events whenever there is something threatening the landmass, but especially the United States. And that is usually done by our director, Dr. Michael Brennan, or our deputy director, Jean Rome. And then, you know, we have like a whole media stage set up on our ops floor so that they can literally get the forecast from the forecaster sitting right next to them, and then go right to, you know, live streaming or live media. So yeah, it's a pretty dynamic ops floor, and it's unique too, because you don't see that happen a lot where you have the forecasters and, you know, basically a broadcast occurring at the same time.
What I asked Philip, what keeps him up at night? What keeps you up at night as it relates to these threats from tropical cyclones?
I think the one that keeps me up at night is the idea that an Otis occurs, especially to like a place like Miami, Florida, where it, you know, the threats just compound upon each other, like the Cat 5 winds, the storm surge, the heavy rainfall, and just a huge population on the coast with not a lot of options for evacuation. Like Joseph said, you know, vulnerable populations, like a lot of different types of vulnerable populations. So that's the one that keeps me up at night. But the other one is the one that Ken always brought up, which is a slow moving, like a tropical storm or a Category 1 storm that goes right into like Tampa Bay. And it's a huge surge event, but everybody attaches to the tropical storm or Category 1 title and doesn't take the threat seriously, and they don't evacuate because, again, the water is what kills the most people directly. So yeah, those are the ones that keep us up.
Well, I'd like to thank you again for this presentation. And, you know, we're all depending on you guys at Hurricane Center to keep us safe in the next 2 months. We are always hitting up your web pages, all these folks. They don't know. There's some anxiety, you know, given that there's supposed to be, you know, very active season. And that, I don't think that can be understated, that you're the source of relieving our anxiety or getting us to evacuate.
We appreciate it, and I appreciate the invitation to talk today. And I'm thankful that Chris is following me up because he's an excellent presenter as well.
All right. Well, that reduces my anxiety too, because Chris Chris just came on 20 minutes ago. I was like, "Where's Chris?" And then I see him. So thanks a lot, Lisa. And I'm hoping that I don't know if you or Chris are able to join tomorrow, but I'm hoping that there's a discussion period, and clearly these hazards in the U.S. that's like a top line issue that's happening across. And I know there's like always some politics around it, but truthfully, average people are just like, what the heck is happening? And how do I get out of the way of the thing? And who can help me get there fastest? I think that's really what's happening to the average person.
Yeah, we all are thinking that, especially in the midst of an event.
I'm getting your picture, so I see the three of you there. I can do this anyway, but I just want to do it because I see HRD and the NHC together. Okay, well, thanks a lot, Lisa. And Chris,
thank you.
And let me see, I have a bio for you. So good thing about Chris is his shirts. Like, no, you're always gonna see him. It makes the day a little bit better, even if it's probably like the middle of winter. So Dr. Chris Lancey is the branch chief of the Tropical Analysis and Forecasting Branch at the National Hurricane Center. He has his degree from Colorado State, right? Colorado State University, and his branch generates wind and wave forecasts for the Caribbean Sea, Gulf of Mexico, tropical North Atlantic, and the tropical Northeast Pacific Ocean. And I know Chris from a long time ago because of the work that he and Bill Gray were doing around rainfall in Dakar, Senegal, and the connections to hurricanes and hurricane days and all. So there was a very interesting work, even though it's a long time ago. You know, students don't do any references if it's, you know, before 2000. So you probably don't even exist, even though the work is super important and still relevant today, because we still look at Dakar and we still look at the rainfall in Senegal and be like, that's kind of a guide for us to know how bad things are going to be in terms of those waves. So, Chris, you can take it away, and really glad to see you and also to have you here.
All right. Well, thanks, Greg. Appreciate it, and happy to be part of this workshop today, and I should be able to join in tomorrow as well. So, can you see my title slide?
Yes.
Okay, great. All right. So again, my name is Chris Lancey, and I'm the branch chief of our Tropical Analysis and Forecast branch. It's kind of a mouthful, but it's our marine branch. And to paraphrase this mission statement, we do wind and wave forecasts and issue wind-based warnings over the Caribbean, the Gulf of Mexico, the Atlantic, and the East Pacific. We have 10 million square nautical miles, and that's for the protection of life and property for the mariners that are out there. And it's just so you know, kind of context of where we're at here. TAF B is the largest part of the National Hurricane Center, and you just heard from Lisa, who's one of the hurricane specialists. We're one of 9 national centers for environmental prediction. Another one is the Storm Prediction Center that does tornado forecasts in the United States. We're all part of the National Weather Service, and the Weather Service is the biggest part of NOAA, the National Oceanic and Atmospheric Administration. Put all that together, we're in the Department of Commerce, which is one of the executive branches. And it's curious, looking at the logo for Department of Commerce, there's a lighthouse on there, and there's a sailing ship. And it might be curious to folks, why is NOAA, a science-based service organization, why are we in commerce? And the answer is it's because what we do affects the whole economy. It's both for well-being and making sure that you stay stay safe, but also to provide more efficient economy. So as an example is for ships to avoiding the worst of the storms, but at the same time getting from port A to port B in an efficient manner. So I always thought that was curious that the Department of Commerce has the lighthouse and the sailing ship on there. So when we're doing marine forecasting, it's not only the auspices of the National Weather Service, but it's also the International Maritime Organization. So the IMO is part of the United Nations, and it was actually founded after the sinking of the Titanic, which was a big cruise ship that went down because of an iceberg in the North Atlantic over 100 years ago. And so after that, the world's countries realized that every vessel over the open ocean needed to have a country that provides free forecasts and warnings. So for example, if you're transiting in the Southern Oceans just south of South Africa, the South Africa Weather Service provides those marine forecasts in the Southern Ocean down there. So a little closer to our home, the marine forecasting of winds and waves over the ocean, it really is broken down by responsibility by geography. So within 60 miles of the coast, that's 110 kilometers, it's the local weather forecast offices. So that little pink ribbon along the coast, that's the coastal waters. And there's 122 local forecast offices that really focus on the city and the county and the neighborhood level. Further from shore, it's the national centers. So the Ocean Prediction Center does the high latitudes of the Pacific and the Atlantic. And the green area shows our geographic area for the Western Atlantic, the Gulf of Mexico, the Caribbean Sea, and the East Pacific. And I did want to talk to you a little bit about some of the tools we have access to, because as forecasters, we start with the observations. And we're very fortunate we live in the era we do, where there's lots of both in situ measurements as well as remote sensed information. And so, for example, ships over the open ocean using two-way radio have for decades provided measurements of winds and waves and barometric pressure reading over the open ocean. We also have drifting buoys now, and there's moored buoys that NOAA operates that provide us continuous wind, pressure, and wave information. To supplement that, we have remote sensed information. So there's two kinds of radars in space that help us with marine forecasting, one of which is called a scatterometer. Right now, the US, we don't have any scatterometers, but the European Space Agency has two, and we get to see those wind, speed, and direction twice a day from both satellites as they circle the Earth several times a day. There's another radar in space called an altimeter, and that gives wave heights that are accurate to the nearest 1 foot, or about 1/3 of a meter. So it's a nice mix of both local information and information remote. One of the biggest tools for us as tropical marine forecasters is the satellite, though. So the geostationary satellites and the polar orbiting satellites both provide imagery that we use, and also observations or data points that get into the computer models to make for better predictions. And as we use the satellite, for example, this is an example from last winter when there was a cold front marching across the Atlantic all the way down to Hispaniola. And so this allows us to identify features that may be more difficult to do without the imagery that's being available. And then a last set of tools are the computer models. So because the domain that we use is very large, we don't do regional models. We use global weather models. And the two that we use the most are the Global Forecast System from the US Weather Service, but also the European Center for Medium Range Weather Forecasting, or ECMWF. So that gives us global surface winds, and we combine those together. And we also add in any observations that are going on now to have a gridded database of winds going over time. This database goes out through 6 days, and it's a resolution of 6 miles or 10 kilometers. To supplement that, we have the wave models. So getting wind waves and swell from the global models themselves. We do run one model locally. It's the only model we run at the National Hurricane Center, and it's a wave model. And we use our wind grids to run this wave model. And that gives us a consistent set of waves that match the forcing by the winds. And so it's real important as a weather service to make sure that we're providing consistent information from across office to another. And then probably the best way that we're able to incorporate information from across the hall, where Lisa and the other hurricane specialists, this is an example from Hurricane Ida from a couple years ago. And she presented some of the cone graphics that are used to represent the forecast. And so it turns out an hour before the forecast goes to the public, it's sent internally. And everybody else in the Weather Service is busy trying to flesh out the details. And so as an example, that pink star is about a day in advance. That's where we're filling out the winds over the whole Gulf of Mexico and the appropriate waves. So in this case, the yellow indicates waves of about 12 feet or about 4 meters, and blue gets all the way to about 10 meters or about 33 feet. And so those kind of details, we're doing that every 6 hours, and we do a forecast out through 5 days of the event. And we need to make sure it's consistent, because it wouldn't make sense that if Lisa's forecasting a category 4, but we're only saying 2 meter waves. That's not sensical. And so it's logical that you want it consistent, but to have the tools in place and the communications to make it happen is really, it's an amazing thing. And we do it every storm, every 6 hours, the whole hurricane season. So those are some of the tools that we use. And when we're making marine forecasts, and our main users are oil tankers, cargo ships, cruise liners, the U.S. Navy, the U.S. Coast Guard, anyone that's out over the open ocean beyond 60 miles or 110 kilometers from the coast. So we provide our forecasts in 3 different ways: traditional text forecasts, graphics that are provided by radio fax as well as on the website, and the grids themselves. So if one has a grid reader, one can bring in the grids and take a look at them themselves. What we're finding out, though, is the mariners, like a lot of folks today, they don't want to read. They want to be spoon-fed. They want the information as easy as possible. So they want graphics, and more than that, they want video. And so we're moving to a higher technology solution. Part of the issue, though, was just a few years ago, if you were out over the open ocean, there's no internet. And so you had to use radio technology to either have voice broadcasts or graphics broadcasts or text broadcasts. That's changing. And I'll get to that at the end. So let me show an example of one of our products. So each one of these little shapes is an area where we're providing a 5-day prediction, stratified by day and night. And we provide the wind speed, direction, wave height, and significant waves, as well as if there's a swell component where it's large waves being generated far away, we put that in as well. And this time of year, if we have any tropical storms or hurricanes, we put those warnings in as well. So let's just take a look. So let me bring up, if I can bring it up. There we go. So this is the GUI that we have, where someone can take a look at what's going on. And so let's look just north of the Greater Antilles. So this forecast shows hurricane warning. This was just issued a few minutes ago by our forecaster, Jorge Aguirre. And you can see it's got nice conditions now, east winds 15 to 20 knots, but by Wednesday, tropical storm conditions expected, hurricane expected. This is all automated. He doesn't have to type this. We have a database with a text formatter. It spits it out automatically. And it's taken into account those wind speed probabilities so that there's uncertainty information put in there, especially on these headlines. And so to me, it's a really sophisticated thing that doesn't take a lot of manual typing for the forecaster to accomplish. So another way that we're providing the forecast is just to show our gridded information directly to the mariner. So this is an example from a hurricane a couple years ago. Hurricane Earl, as it left the Antilles and started heading toward Bermuda. It's kind of like Ernesto, pretty close to what's happening over the next few days. On the left side is a graphical representation of a text product, the high seas, that nobody reads anymore. But blue shows where it's at least 8-foot seas, 2.5 meters. The orange where it's 23 knots, that's a strong breeze in mariner terminology. The medium blue is tropical storm winds, and then the gray is hurricane winds. Or you just look at the winds and waves directly. On the right side, it's the forecaster drawn features and the isobars, as well as every 12 hours, the forecast of Earl as it's moving across. So if I was transiting in a ship from, say, Bermuda down to Haiti, I would wait. I would wait for that hurricane to pass and then make a nice, safe voyage. And that would take about 15 seconds by looking at this graphic that, yeah, you don't want to get on a vessel going toward Haiti if you're in Bermuda at the beginning of this loop. You should wait. So that's really quick. I could go into a lot of details about our marine forecasts and the products that we have. I did want to talk about service, though, and decision support and some of the bad decisions that mariners have made and some good decisions. Because if you work for a National Weather Service in Africa or elsewhere, it's really about providing the public and your governmental partners with service they need to make good decisions. And unfortunately, there have been some ship captains and crews that have made bad decisions and gotten themselves into trouble. The most infamous was the El Faro, which is a cargo ship that's almost 400 meters long. It had 33 men and women on board, and the captain took this ship right in the middle of Hurricane Joaquin when it was a Category 4, instead of turning around and going a different way. And it was really sad when that happened. The captain essentially anchored his decision-making based on the first forecast, which was not a very good forecast, but they improved subsequently. And the company was not paying attention to where this vessel was either. So no one questioned the captain about, why are you taking this ship and 33 people into the middle of a hurricane? And unfortunately, the ship took on water. They called for Mayday for the Coast Guard, but within 25 minutes, they sank to the ocean floor, and all were perished. And there's been other examples of ships with very bad conclusions. Just 5 years ago, the Bourbon Road, when it was just west of the Cape Verde Islands, sank in the middle of Hurricane Lorenzo. Very similar thing. They weren't paying attention to the forecast. They went right into the hurricane. Good news is, though, that's pretty rare. Nowadays, most mariners are paying attention and altering their course to do hazardous weather avoidance. And there's a website called marinetraffic.com, because by global standards through the International Maritime Organization, if you're a giant vessel, you're supposed to have a transponder that if you get in trouble, you push the button and the local Coast Guard comes and helps you out. And they actually color-coded on this website, where orange are fishing boats, red are oil tankers, green are cargo ships, dark blue are cruise ships. And as Hurricane Delta emerged from the Yucatan of Mexico and was starting to head northward into Louisiana that year, you could see that the ships were getting out of the way. So they were recognizing the issue and they were moving to a safer place. And so that was gratifying. We don't know for sure if they're using the forecast from the National Weather Service or private sector or a ship routing company. We don't know. But in general, 99% of all these hundreds and hundreds of ships did the right thing. Now, if I was on an oil tanker, I think it would have been a little further away. But regardless, they were taking action to try to stay safe. And after the hurricane made landfall, then there's a lot of actions that are taken by the U.S. Army Corps of Engineers, by NOAA, and the U.S. Coast Guard to check the ports and harbors, to make sure the aids to navigation and buoys are in place, to make sure there's no sunken ships, so that the ports can reopen and commerce can go again. I didn't point out earlier, I should have, 80% of global commerce today is on ships. It's not airplanes, it's not trains, it's not cars, it's ships. And so these ports are huge economic engines that we have to keep safe and operating effectively. And it's our job as forecasters to help the Coast Guard make those decisions. So I've mentioned the Coast Guard a couple times. So they help us out by also providing the transmitters, these radio transmitters for text and graphics and voice. And so it's a good partnership. And it turns out the Coast Guard has no forecasters. So we provide, as Weather Service, all the forecasting needs to the U.S. Coast Guard, or we're supposed to be. And so this is by design going back many decades. And so we've really tried to embrace this mission and help out the Coast Guard as much as we can. And because we work with the districts, which is kind of a big chunk of the U.S. Coast Guard, it's kind of regional, we asked them, what do you need? And I think you need to do that. If you're working for a weather service, ask what your local Marine patrol or your local Coast Guard, what do they need for helping them? Because they're in the winds and waves all the time. The first thing they said is, we need a website. We need a website with all the things we want on it. And so we said, yes, sir, yes, ma'am. And we set up a website. It's public. We don't advertise it except for the Coast Guard. But if you go to hurricanes.gov/USCG, you'll find a special website that we made for the Coast Guard districts, where it's got everything they need, from briefings to websites to spot forecast requests. We also do training for them, because these Coast Guard folks, they're pilots, they're navigators, they're rescue swimmers. They're not weathermen, not weatherwomen. So we do training with them to make sure they know about our products. How can they use them to stay safe when they're rescuing people? And we do hurricane exercises. And so that allows us in the winter or spring to stay sharp and to do good briefings by getting some extra practice. And so every year we work with one of the Coast Guard districts to do a hurricane simulation, where we're looking at a simulated possible hurricane, and we make the forecast, and the Coast Guard decides, well, what actions would they do? So when the real thing happens, they'll at least have a good head start on dealing with a real event. So this kind of training is important. And in the United States, the Coast Guard officers, they move around a lot. Every 2 to 3 years, they move to a different location. So somebody that may be at Air Station Miami and flying one of these helicopters today, they may have been on, coast of Oregon, where it's super cold and they never get hurricanes. So different meteorology for them. Another aspect that we do is we issue spot weather forecasts. And so this is for special needs, again, for the U.S. Coast Guard. They say they need a forecast, and we get it to them within 30 minutes. It could be for a man overboard. It could be for an oil spill. It could be for a disabled ship. It could be an aircraft that's ditched. Or it could be law enforcement where they're chasing the bad guys. They don't even have to tell us why they want a forecast. They just say, we want it right here. Please give us a forecast. And we get it to them right away. And so that's a real critical part that we help assist with, are these special forecasts. Another thing we have been providing are live briefings. And so when the Coast Guard is dealing with a hurricane that's starting to threaten the United States, they have a few really important decisions they have to make. First of which is for their offices, and the Coast Guard, most of their offices are on the coast. Do they board up and evacuate their own Coast Guard office, or do they stay and keep providing services? And they need to get their ships, so their cutters, their fast boats, and their aircraft out of the way of the hurricane, because if a hurricane goes over them, the ships or the aircraft could get beat up, but not too far away, because they may need to go rescue people. And after Hurricane Ian, the Coast Guard rescued 1,007 people from rooftops, from boats, from flooded areas. It was amazing. And the last thing they do is more economic, is the captain of the port has to decide which ports to close and when. And so that's a huge thing, is restricting or closing a port. It's a big decision, a big economic decision, but you don't want a hurricane to hit a port like Port of Miami, and it's open because ships will batter the piers and the harbors. Ships may sink, and so. But on the other side, you don't want to close it too early because every day you close a port, it could be millions of dollars of commerce that's being lost. So that's a big thing. Is we don't do any of those decisions. That's done by the Coast Guard, but we're providing them the meteorology for them to help make decisions. So it's an important aspect, I think, for weather services to reach out to your core governmental partners. What do you need? What do you need to do your job better? And then provide that information. To supplement that, we have marine workshops where we bring in reps from cruise lines, cargo ships, oil tankers, fisheries, the U.S. Coast Guard, the Navy, even some of the maritime academies. And so we bring them in and say, hey, this is what we're providing, and what do you need? So that can help inform us in the future for new products and services going forward. So it's reaching out to customers, not just other government agencies, but on the private sector too. One thing we're trying to do is be more relevant. And as folks are getting more internet over the open ocean, we want to make sure that we're reaching them faster. And so as an example, a few years ago, we started tweeting out anytime we have a warning. And we have a lot of warnings this time of year. We have a lot of warnings during the wintertime. And so that's a way they can get the warning within 5 seconds of it being issued. Another aspect is videos. So our forecasters now are doing a video twice a week, Sunday afternoon and Thursday afternoon. And we host it on our YouTube site and we tweet it out, and it's sent out by Gov Delivery as an email. And that's another way to get the forecast out. It's not a new forecast, same forecast. It's a new way to provide it. People love videos. It's real easy. So I hope that gives you a little bit of who we are. We've got 16 forecasters in our TAFB Marine branch. And for if you're interested in seeing what we have, it's just hurricanes.gov/marine. So on behalf of our men and women working 24 hours a day, 365 days a year, I hope that is a little bit informative of what we do on a day-to-day basis there. So Greg, are there a chance for questions?
Is Nelsie Ramos in your section?
Nelsie Ramos is one of our marine forecasters. She does a great job. And yeah, she's been with us for several years now. And she was just on shift a couple days ago.
Okay. She's a Howard grad.
Well, I'll tell her howdy for you. Yes.
So what's unclear to me is, like, you're forecasting 60 miles out, right?
Yes.
Is that what so how does who does within 60 miles? Is that the local weather service?
Yeah, let me show you. But first I'm going to show you a picture of Nelsie. So there's Nelsie right there. That picture was last week, so it's really up to date. Do you still see my slides?
Yes.
Okay, so this is the slide that shows how we divvy up the responsibility. So the national centers have kind of a bigger scope, kind of a big picture point of view. So we do over the open ocean. Same thing with the Ocean Prediction Center, open ocean, but within 60 miles of the coast, it's the local forecast office. So for example, in Florida, there's a Key West office, there's a Miami office, there's a Melbourne office, there's a Jacksonville office, there's a Tampa office, and there's a Tallahassee office. So all of them do coastal marine forecasts out to 60 miles or 110 kilometers from the coast.
So when a tropical cyclone is threatening a coastline, who's doing the surge forecast? That's coming from Hurricane Center?
Yes. So that's still relatively new over the last decade. So that is the Storm Surge Unit. Right now, the leader of that is Cody Fritz. And the forecasts are provided probabilistically, and warnings are issued. And so to me, that's been a great advance that the National Hurricane Center has been providing for the last few years.
Do you have any other questions?
I have a question.
Question.
I kind of have two. One being, what do you do? What do you all do during your winter months? And then another one is about social media. But I mean, either or, how do you want to answer? You want me to say both, or you want to do what you all study during the winter time?
Sure. So we're busy as forecasters all year round, because during the winter time we can get strong cold fronts or extratropical cyclones coming across the Gulf of Mexico or on the East Pacific, and so we have forecast responsibilities 24 hours a day. The hurricane specialists, they I'm going to say this because Lisa's still on the line. They forecast for 6 months and then they play golf for 6 months, right, Lisa? I don't know if she heard that. No, they're really busy in the off season. Like they're super busy. I think there's sometimes the hurricane forecasters are busier in the off season because of training. They're doing reports about what happened to the storms. They're developing new products. They're super busy in the off season. We're busy all year with forecasting. They're busy 6 months forecasting and 6 months other stuff. Yeah. And so, yes, social media. Yes. So one thing we do, and I'll show an example. We have a Facebook component that the Hurricane Center runs, and there's also Twitter. So the Facebook is done kind of Hurricane Center wide, but TAFB, we have our own Twitter account. And so, for example, this would be the marine key messages that were issued this morning as part of a briefing that Amanda Reinhardt gave to Coast Guard District 7 in Miami. And so we are talking about the winds and seas near the U.S. Virgin Islands and Puerto Rico, and the impacts that could occur there. So we do a lot on Twitter or X, and Facebook is Hurricane Center wide. We're doing Facebook Live, as Lisa mentioned, with Mike Brennan's live briefings. And I've heard we're going to start getting into Instagram, but I've not seen any of that yet.
That was my question. If you guys, I know TikTok may be an issue with the government in that whole scandal, but I was going to ask for Instagram. And then two, how do you connect to the non-science community with people who may not be able to even, I guess, they know how to read the graphics that you have. They're pretty straightforward and clear. However, the people who don't even think to follow you all, how do you find that niche on Instagram, X, and YouTube? How do they come across your page?
Right. So again, we're forecasting for mariners, folks that are on vessels over the open ocean. And one thing that we're going to be doing to help with some of the underserved folks in the Caribbean, Central America, Northern South America, is that right now all of our forecasts are in English, but most of the folks that live around here don't read English. So we're hoping in 2025 to start providing Spanish language versions of this. And there's also folk that speak Dutch, and there's folks that speak Creole. And so with a AI version of our forecast, we should be able to provide forecasts in almost any language. And so to me, that's exciting to provide that, because if we provide these forecasts over the open ocean in Spanish and Dutch and Creole, we're going to have hundreds of thousands more users, because every day there's fishermen, there's folks that run medium to small cargo boats that go from island to island. And so to me, I'm excited about this possibility of reaching out to a community that really we've been kind of one-sided in only serving the English-speaking folks.
Tomorrow, if you can join a conversation, there are a lot of issues that colleagues in Africa have to face with the coastal zones and the marine environment and the tools that are available. I mean, at least in the past, people used to use a www wave model to kind of figure things out, but there are a lot of fishing communities out there, and they're small fishermen, and I'm not sure how far they go out, but I know Cape Verde, for example, is a little bit complicated because you have fishermen going between islands, and that is the open sea in a sense. And I don't know what tools can be used to help. And even in the worst case scenarios, when people are taking these small boats and trying to get to Europe, I mean, those boats don't make it in certain conditions. And so I don't know, that's kind of a separate topic, but it is that matters. Talking about human life. They don't fit easily into the box of the big companies or the big ships out there.
Right, right. Yeah, there's a really big role for local weather services to provide marine predictions to the populace. And so you mentioned Cape, the Cape Verde Islands and going from island to island as fishermen. That's a great example because most of the time the weather there is great, but occasionally you can get gales or tropical storms, and then that becomes life-threatening. So that's why I would encourage, folks that do work in weather services in different parts of Africa to engage the marine community, try to provide services for them, and reach out to how are they going to get the information. And as hopefully accessibility by cell phones seems to be the way that people are getting information. To be able to provide information that way, warnings as well as the information. But you're right, there's a lot of folks that are going out over the open ocean in vessels that may not be very seaworthy, and you want to make sure that they stay safe. If it's not seaworthy enough, then they should not go.
Yeah. Well, yeah, I was talking to fishermen in Cape Verde, and they're like, our biggest problem is we go out beyond a certain point and we don't have any signals for phones. And also they're trying to chase the fish. So sometimes the fish aren't where it could be related to ocean dynamics, or it could be to ocean warming. Fish aren't where they think they are. They have to go out further. Those seas, even if there's no storm, those waves can be just makes you sick. I mean, they make you seasick because they're rough and the boats aren't big.
Right, yeah, and especially in the wintertime, you can get some massive swell that hit the Cape Verde Islands from storms up further north and northwest. And so yeah, that's a dilemma. On the larger scale, there is more high-speed internet becoming available through SpaceX and their launching of Starlink. They've got like 350 mini satellites, but there's a cost associated with that. It's a couple grand, to get it installed, and a couple $100 a month, which may be cost prohibitive for a lot of fishermen. So, but that's that. My guess is that internet's going to become more reliable and cheaper going forward in time. So hopefully there'd be accessibility for folks that need it, like you mentioned.
I guess we can go to the last tropical talk, and then tomorrow, if you guys can come in for discussion, we'd appreciate it.
I'd be happy to. Thanks for having me join in. I appreciate it.
All right, good seeing you again, Chris. All right, UNG, we don't need to say who you are again. You are the moderator. But we have, you're up next, and you're going to be talking about the improvement of hurricane intensity forecasts with data simulations.
Apparently I cannot finish this talk in 3 minutes.
In 3 minutes?
Yeah, in 3 minutes we're starting the next session, but I'll just go this time.
Go, man. This is the research side.
Yes.
And Bill is the last talk, so he might go over and not be mad at us. Maybe the folks online will all go off, but we want to hear his talk.
Anyway, today I'll be talking about some of the research that has been happening at Penn State's what we call Penn Center for Advanced Data Simulation and Predictability Techniques, or ADAPT, for the past 15 to 16 years already, in terms of how we can improve hurricane intensity forecast using remote sensing observations and data simulation techniques. So we have already been seeing these two figures several times yesterday and today already. And the left-hand side showing the average track forecast errors from the National Hurricane Center and the forecast error with respect to time, an average every 10 years. And we see some substantial improvements in track forecasts, basically from every decades going forward. But on the other hand, if we're looking at the right-hand side, we see that there is practically very little improvements in terms of intensity forecasts, or at least until 2010. And we see some of improvements after 2010. And there is a reason that I'll talk very briefly later. And yesterday in Philip Pappin's talk, he also mentioned several of the reasons that why there is no significant improvements in intensity forecasts in this very long time until about 2010. Because first, the intensity forecast or intensity change of hurricanes is a multi-scale process. And the most important part that controls the intensity change in the core region, or basically the eye wall and surrounding region of the hurricanes, is typically poorly observed. And for a very long time, we are using global models to basically do the intensity forecasts as a surrogate for the intensity change of hurricanes. And the model resolution is just too big. The grid spacing is too big to properly resolve many of the critical processes that are actually happening in the inner core region, which controls the intensity change of the hurricanes. But if we can combine some of these these discrepancies that we mentioned above, we can probably have a better intensity forecast of hurricanes. And the first success with the data simulation with the inner core observations happened happened when late Professor Fuqing Zhang, who Paul Markowski also mentioned 1 hour or 2 hours ago, when he was still at Texas A&M. And he did an experiment with Hurricane Humberto, which made landfall in Texas back in 2007. And the observation he used was the surface-based next-threat radars in the landfalling region. This one is the Houston, Texas radar, and the Corpus Christi radar, and the Lake Charles radar in Louisiana. And these observations, you can see, provide very critical inner core, or basically where the very fine resolution of how the hurricane evolves when it made landfall. In addition, he also uses a very high resolution numerical model. He uses the WRF model with a 1.5 kilometer grid spacing. As a comparison, the operational GFS model back then has a grid spacing about 35 kilometers, which is not able to properly resolve many of the convective processes happening in the core or the high region of the hurricanes. So he basically only used the wind information that is retrieved from the radars, because as you already know, the hurricane is a very strongly dynamically constrained system that the wind field basically drives everything from the dynamical side. And he has in this slide here, the first two panels on the left-hand side are the observations of wind, the radial wind from radar from 2 different times. The center panels here are how the model do if we put this information into the model through data simulations. And on the right-hand side is the results if we do not put the observations into the model. So you can see that will we actually successfully assimilate these observations into the model, and they had a very good match between the model model analyzed wind field compared with observations, which is very different from the experiments that do not have data simulation at all. And with this vast amount of radar observations of the hurricane wind into the model can actually predict very decently how the intensity change of the Hurricane Humberto will look like, although there is slightly discrepancy in terms of time of how the intensity will look like. We can still see that the red line here, which is the forecast from ensemble common filter analysis and forecast, will look like compared with the post-storm analysis of the intensity of Hurricane Humberto. On the other hand, the blue line here represents the then operational data simulation algorithm, the 3D VAR techniques. And we can see that even with 3D VAR techniques with all the observations, it cannot predict how the rapid intensification of Hurricane Humberto happens before it made landfall. So here we see that the techniques that we use to simulate observations also plays a very important role in addition to a high resolution model as well as observations that can actually see what is happening in the eye region of the hurricanes. And of course, the ground-based radars are still too far away for most of the times of hurricanes because they can only sense about 200 to 300 kilometers away from the radar sites. So the focus next, we switch to the aircraft, the NOAA P3 Hurricane Reconnaissance Aircraft, which we have the tail Doppler radars, which we can probably see here at the rear end of this P3 aircraft. And it can scan in the forward and backward direction and provide wind information when he fly across different parts of the hurricanes. And just the very similar stories, after we are able to put the aircraft's tail Doppler radar wings into the models, we see a notable improvement in terms of both track on the upper panels and intensity in the lower panels in the forecast represented by this red line here, compared with the National Hurricane Center's official forecast, which is represented by these cyan lines here. And the basic idea is that the red lines are always closer to the black lines, which is the best track observation, compared with the cyan lines. And we have this system running in real time for 5 years between 2008 and 2012. And when we evaluate all the forecasts what we have across these 5 years, when we have simulated aircraft observations, we see that first, we have very comparable track forecast errors compared with National Hurricane Center's official forecast. And secondly, we see that there is a vast reduction in terms of wind forecast errors when we compare the forecast from numerical model with National Hurricane Center's official forecast. And this is probably a very rare time that a numerical weather model actually becomes much better or considerably better or more accurate than National Hurricane Center's official forecasts, or over hundreds of forecasts. So of course, because we have shown that these techniques have very significant improvements in terms of hurricane intensity forecast, the operational H4 models also implemented the data simulation technique in 2013 to assimilate the aircraft observations. And also there are a lot of other improvements in terms of, for example, if we have better track forecast, it will also translate to potentially better intensity forecast. And we also have been improving the model resolutions and parameterization schemes that we use to describe interactions between the hurricanes and the underlying surface. And we also have better data simulation techniques. Back then, back in 20 years ago, the majority are using 3D VAR, and it's been using hybrid ensemble variational techniques after about 2010. And also we have advancements in the consensus of models. So we have better technique to select the best performing models to combine them together. And eventually after 2010, we now see a quite notable trend in terms of a decreasing trend in terms of hurricanes intensity forecast, at least for the North Atlantic basin hurricanes in the past 10 to 15 years. And this is also the time when the dynamic models actually outperforms the traditional statistical models. When back in the 2000s or 1990s, the statistical models actually performs better. So this is a lot of improvements that we can gain from improving the hurricane forecast models and improving the observations that is being used for the data simulation. But of course, the problem is hurricane reconnaissance aircraft is not available for a lot of the basins worldwide. So the next step is, of course, try to figure out what we can use, no matter where you are, we can use to improve potentially the hurricane forecast. And of course, the tool we'll be using is the new generation of geostationary satellites, because it now has a very high spatial temporal resolution that is capable of observing the development of severe convection and tropical cyclones. And more importantly, these observations are not fully utilized in all the operational models because all of them only use the clear sky part, while the cloudy observations are basically thrown away. And our research during the past 5 to 10 years has been focusing on how to fully utilize all these observations of the clouds into the numerical models. So we did 2 experiments at the beginning for the Western North Pacific and Atlantic basins using Super Typhoon Cellular and Hurricane Harvey as 2 examples. And the left-hand side one, we used the Japanese Himawari 8, the satellite, and the right-hand side one, we used Ghost 16. And here is an example of how the data simulation looks like. The left-hand side is observation from Ghost 16's infrared imagery. And right-hand side is how the model has been able to construct how the cloud might look like for Hurricane Harvey. And we can see that after several cycles, the model is basically capable to reproduce what exactly the observations looks like for Hurricane Harvey. And not to surprise, after that, we see that assimilating satellite observations from geostationary satellite actually also improves the intensity forecast of both Super Typhoon Cellular and Hurricane Harvey. So here, these black thin lines are the post-storm backtrack from 2 different agencies, and the red and brown ones are the forecast with the simulation of satellite observations, and right-hand side here one is the same. This black line is the best track, and the red one is the forecast after we assimilate satellite observations. And the other lines are actually the operational forecast from other operational models, including this one is the GFS model, and this one is from the European Centers model. And these 2 are the high-resolution hurricane models from National Hurricane Center. But the problem is clouds sometimes blocks the eyes for the infrared sensors among the geostationary satellites. So for example, if you're looking at the Doppler weather radars, it can basically see how the hydrometeors distributions looks like and how they move. So that's why the reason that Doppler radars has been one of the most useful tools, most powerful tools when we try to monitor development of hurricanes and severe storms. But for infrared sensors, the observations cannot see anything underneath the cloud tops. So it can only see the cloud top features. So in this way, we probably need to have something else. And in the scenario here for hurricanes, we're considering the microwave sensors. And under certain circumstances, the microwave sensors can actually see how within the entire column, how many hydrometeors, the rain, the snow, and hail, and graupel are there. That is integrated through the entire column of the atmosphere. So if we can combine that with infrared, we can probably see an even better forecast. But first, let's see how does infrared and microwave see things differently. So this is for Hurricane Harvey as well. The first panel here are it shows the infrared radiance. We can see basically where the cloud top is. So this is Hurricane Harvey, and this is one of the rainstorms that is developed from its outer rain band and hit Houston and produced a huge rainstorm flash flood. And for different channels of the microwave sensors, we can see things very differently. This one, a relatively low frequency microwave channel, we can see how the liquid particles looks like. And we can also see the land-sea contrast in these observations. Well, if we go into a high frequency channel, it's more sensitive to ice particles, or basically ice cloud and snow and hail and graupel. So we can see if we can combine different sensors and as well as different frequencies from the microwave sensor, we can probably have a more complete depiction of how the hydrometeors and clouds looks like in hurricanes. And as a matter of fact, after we implement microwave observations, we indeed have a better forecast of intensity of Hurricane Harvey. So the first two panel here is the track, and this is the minimum sea level pressure and maximum surface wind. And the upper panels here are the results. If we only assimilate infrared and lower one, we add additional microwave. So you can see that originally the infrared experiment actually struggles a little bit for the rapid intensification of Harvey, but after we implement or add microwave observations, all the forecasts at least show some degree of rapid intensification, even for the earliest ones, that is starting when Harvey was still over the peninsula of Yucatan in Mexico. So we see that there are tremendous values in these observations which are not yet operationally assimilated in the numerical models. So to conclude, the inner core observations are probably very critical for accurate intensity forecast in current numerical models, in addition to a higher resolution of the model itself. We found that radar can provide very critical information, although the distributions and coverage of the radars are limited. On the other hand, the satellite can provide cloud information, which is sometimes more difficult to use by the models, but it has more complete coverage or more global coverage that you don't need to have a surface radar network or a fleet of aircraft to observe these hurricanes. And in my opinion, satellite observations are probably our best opportunity to improve tropical cyclone forecasts in underdeveloped countries, although there are still a lot more research needed to fully utilize and understand what's going on when we try to put these observations into the models. And that's all for my talk. Thank you very much.
All right. Yunji, tomorrow you're in the discussions session for both talks, for Africa and the United States, because we have to think about this last point that you've made, because there's no radars, there's nothing really.
Yes. So I see there is a question in chat. I wonder how to include satellite observations to initial conditions for WRF model. Is it through intermediate file? So we use the technique called data assimilation. So basically it combines observation with the model fields, and it will adjust the model fields according to how much differences are there between the model predictions and the observations. If there are large discrepancies, and it basically weights how much you would like to change model fields to match the observations better. And there is a whole lot of algorithms and programs that can do that. And then it will generate adjusted initial conditions that is matched better with the observations. Then if you launch forecast from that, it can potentially bring you a better forecast.
Yeah.
So is this similar to using the old sky gradient?
Yes.
Similar to the Xinjiao's.
Yes.
Yeah. All right. Well, let's jump quickly because next we jump to river forecast, and we have Sean Reed, who is a hydrologist from the National Weather Service Mid-Atlantic River Forecast Center here with us. And Nikita, you're going to advance the slides, and Sean, you're going to come on up because you can sit. You can, if you want to sit right here, the camera will zoom in on you.
I like a face. I don't know.
Well, how do you face people online? So if you face us, then you'll be like Miles Davis. Your back will be against them.
I'll do it this way. That works.
Okay, let me. Can we get Sean's slides up, and let me just introduce him quickly. So, Sean Reed is the development and operational hydrologist for the Mid-Atlantic River Forecast Center here in State College since 2012. Prior to that, he worked at the NWS Office of Hydrologic Development, where he served as a research meteorologist for 9 years for the hydraulics and the hydraulics group for 5 years. He has a PhD in environmental and water resource engineering from the University of Texas at Austin. His areas of interest are for developmental work include hydrologic and hydraulic model calibration, probabilistic hydrologic forecasting, verification, and flood forecast mapping. So thank you, Sean, and we'll have your talk.
Okay, thanks a lot. Yeah, so I think some of this has already been said, but I just wanted to talk just briefly about the difference between my work at Silver Spring and what I do in State College. So State College is an operational office, and it's a great opportunity to do a combination of things. You can, you have the responsibility to do the forecasting at the River Center when there's not a lot of rainfall or the risk of flooding going on. We do have time to work on projects, and we'll look at what partners need, and we'll look at improving our models and working with other groups. So I have some information about that in my talk. And go on to the next one. So just at a high level, I just wanted to, some of you probably already know a lot of this, but there are 13 river forecast centers in the United States. We're just the one that covers, Pennsylvania, New York, New Jersey, Maryland, et cetera. We work closely with not only the weather forecast offices, which I'll talk about a little bit more, but we also work with the Weather Prediction Center, particularly on the precipitation forecasts. And then the National Water Center is a relatively new center in Tuscaloosa, Alabama. And they have, we work closely with them on development projects, and they also support us during operations in terms of, providing us with new technology and those types of things. So yeah, for our local office, we cover the river watersheds that are shown here. So Susquehanna, Delaware, Potomac, James, and a couple of the other smaller basins that drain to the Chesapeake Bay. And so just to distinguish what we do at the RFC, the River Forecast Center, from what the weather offices do, as far as the river forecasting goes, we run models. We analyze meteorological data. Before we run the models, we pass that to our hydrologic models. We generate products where what we think the river levels are going to be, and then we share that with the weather forecast offices. The WFOs then review that information, and they make the decision about whether there's going to be a flood advisory, a flood watch, or flood warning in discussion with us. And then, yeah, you can go on to the next slide, I guess. So that just gives you the context. And so I guess what I wanted to talk about today is what I perceive in my work, both in the development down in Silver Spring and locally here, as what are the biggest challenges we face as far as the river forecasting and also the flash flood forecasting. So I'll talk just briefly about each of these topics: observed precipitation, forecast precipitation, the river hydraulics, the fact that the flood characteristics of basins are not stationary, and then the extreme flash floods kind of combines all the challenges from the other categories together. My particular expertise is not on the communication side, but I know we have tremendous challenges there, so I'll give a few examples on that side as well. So the first challenge that I wanted to mention is just getting the observations right, getting the rainfall field right. The way we generate the rainfall field, we look at radar and we look at precipitation gauges throughout the region. We have thousands of rainfall gauges in the Mid-Atlantic region. And then we blend that with the radar to try to get the best hourly intensity of the rainfall across the region. And then we add those up and we run them through hydrologic river models. But it turns out there's no perfect way to blend that information together, to do the quality control on the gauges, to blend it with the radar. You can generate different fields depending on what your algorithm is. And so this is just one example of a basin in New Jersey. And this was actually from the remnants of tropical Hurricane Ida. And it's just showing that if you have 3 different types of ways to generate that rainfall field, one is called MPEBE, MLQ Mosaic, MRMSGC. You can get a range of simulations for that particular basin. It can be plus or minus 2 feet at the top. It can be a record flood or below record flood. So it can make a pretty big difference just to have the observations right. And then if we go on, another, of course, even bigger source of uncertainty is the forecast. Forecast of the precipitation and the temperature and other variables that affect the amount of rain or the melt of the snowpack in the wintertime. So I wanted to show an example of just how much impact that uncertainty might have on the river forecasts. So the left-hand diagram here is a forecast generated by running the NAIFS ensembles of precipitation and temperature through our hydrologic forecast models. And the NAIFS, if you're not familiar with that, is a combination of the GFS and then a Canadian model. As currently has 52 members, I believe. And so what that is showing is that 3 to 4 days ahead of when Ida really hit, we were predicting the Susquehanna would have quite a few moderate floods, or at least a decent chance of moderate flooding, the red circles, and a few locations in Delaware, but it was definitely going to be a widespread flooding event. We were pretty confident about that. But what actually happened on the right, 4 days later, it was even much more severe, and it was shifted a little bit more to the east as far as the worst flooding that was predicted. So this is just to give you a general flavor of the uncertainty we might have 3 to 4 days in advance. Of course, when we get closer to the flood itself, like 2 days, 1 day, then our forecasts would be much more precise as far as the locations. But this is just, the challenge, I think, is to extend the lead time and to reduce the uncertainty. So another challenge is once you get the rainfall and the runoff calculated, you route it into the river reaches. And then for very extreme events, we can often be challenged by the hydraulics of the river itself. So in our upstream watersheds, we don't necessarily run detailed hydraulic models that do the physics of how the water flows through the channels. We just do simple relationships between the distance and the velocity, and then route the water downstream and see how it accumulates through time. But in some areas, the dynamics of the flooding are much more complicated. There's a backwater effect. And here I'm just showing an example in Philadelphia where there's the combination of tides and freshwater really impacts the water level right along the Schuylkill River in downtown Philadelphia. And you can see on the right that there's a tidal fluctuation, and then you get the freshwater surge, and then you get that jump up. But it's not like a normal river hydrograph. It has a combined effect of both the tidal signal and the river itself. So in this area, we're running this more complex hydraulic model. You can see the cross sections that are drawn all across the river. And that's an engineering analysis you do to get the amount of area that the water can flow through, so you can get conveyance of the river and really model the dynamics of what's happening during the flood. Unfortunately, it's a challenge because we don't have the capability to do this everywhere, and so we have to select the places where it's most important to run this type of model. Okay, next challenge is not all of our basin, or the behavior and characteristics of flooding in basins varies over time. It's changed over the years, the non-stationary flood characteristics. This is something we're still learning about. These graphics actually, we had a student volunteer work in our office this summer, about 20 hours a week. Her name was Sarah Mounier. She was from the meteorology department. And she put together this analysis. And so what this involves, we have a database of all the floods that we know about that have occurred. It goes actually back to the 1800s. So all the floods we know about in the Mid-Atlantic region. But for this analysis, she selected only gauges where we had a complete record from 1920 to 2020. So 100 years. It turned out there were 67 locations in the Mid-Atlantic region where we had then a complete set of information. And so then what she could do is tally the number of floods in each decade and then just make a simple plot to show, visually you can see there's an increasing trend over time. 1970, of course, is kind of the exception. But there is statistically a trend. She did a really simple trend test, the Mann-Kendall test, that showed we have 98% confidence there's a non-zero trend in this data. And the other thing, not only the number of floods increasing, but on the right, we broke it up into two chunks where you have a chunk 1970 to 2020, the most recent 50 years, 1920 to 1970, earlier 50-year chunks. And this is the CFS per area. This is the magnitude of the flood. So CFS is just cubic feet per second. So the amount of flow per area at the peak of the flood You can see from 1970 to 2020, there are many more samples in the higher range. And you can also see the interquartile range is larger. So that just indicates that not only have the number of floods increased, but the intensity of floods in the region has increased. Okay, next challenge. Kind of combining really all the other issues together. So we have a challenge with estimating observed precipitation, estimating forecast precip, doing the hydraulics of the modeling, and then understanding, are the models we have adequate because of the non-stationarity of the system. So I pulled this. This is recent. Last week we had Debbie come up the East Coast. Really huge impacts in the Carolinas. We weren't expecting as much impact in our area, but it turned out we did have some pretty devastating issues in kind of northern Pennsylvania and southern New York. So you look at the total precip for the event on the left-hand side, and you might think, just looking at the precipitation, Central Virginia really had the highest totals, especially along the Blue Ridge, where the convective enhancement was much larger. But I'm not showing our river flood forecasts here, but on the right, these are the storm reports that the WFO collects. And in Virginia, there are some points, but those are all light green points. Those are flood points where we had some lead time. We knew that the flood was coming along the river. The darker green points and the more concentrated areas, like the area circled in blue up in northern Pennsylvania, that's in the Chemung Basin, part of the Susquehanna. There are a lot more severe reports. So when you click on these points, you can see the description. It says, there was home damage, roads closed, water rescues, people trapped in their homes. It was really catastrophic in some of these, in a couple of the smaller towns up there. And so you look at the rainfall map and you say, well, why is that particular area worse? Because the total rainfall was either comparable or less than places that didn't have any flooding. So let's think about that a little bit. And I've got on the next slide just some possible reasons. This is a little bit preliminary. We haven't done a detailed analysis of the flooding in this recent event, but the graph on the left, or the map, excuse me, it shows a measure of the wetness prior to the event, the antecedent conditions. And you can definitely see in Virginia, Maryland, and the coastal areas, a much higher, what we call flash flood guidance. So that's a much higher amount of water that the soil can absorb before it starts flooding. And then you can see in Pennsylvania, and especially along the Pennsylvania-New York border, some white and blue numbers. That just means the soil is wetter there, can't absorb as much rain. So that's part of the reason the impacts were higher. Another thing that I looked at, and this is a little bit, again, preliminary, but for some of the watersheds that we modeled in the southern area in Virginia, et cetera, they had more rain total, but it occurred over a longer period of time. Once the storm started moving quickly and hit the rainfall in some of the upstate New York areas, it had more intensity in a 6-hour period. So it was just more likely to cause those local intense flooding. And of course, some of the areas that really got the catastrophic flooding, there was local topography that influenced, what was going to happen there. And then the fourth thing that I was thinking about, and again, I don't have, a particular study to show that this was the case. I don't know the infrastructure design requirements for these communities, but if you look at the precipitation frequency analysis done by NOAA, this is NOAA Atlas 14, climatologically, those areas that were hit harder by the impacts of this flood, they don't experience those magnitudes of flood as often. So the 100-year 6-hour precipitation totals are much less than down in DC, where you can get like 5 inches in 6 hours. And up in the northern areas, you might only get 3.8 inches. So the infrastructure might not be designed to account for as much rainfall in those areas. So those are just some of the reasons we think about, and it helps us to forecast next time. When we know the antecedent conditions, we know that we can, that the models that are not showing flooding in Virginia still might show flooding in the wetter areas. Okay, so now I'm going to talk a little bit about the uncertainty or sorry, the communication aspect of flooding. I didn't really show the ensemble hydrographs when I talked about our ensemble forecast, but this is a hydrograph that shows the possible range of river levels for a specific location. And it's fairly actually complicated to explain, but what we've had done in the past is we have had some work done by the Nurture Nature Center. It's actually a neat place in Eastern Pennsylvania. It's an educational center. And our early versions of this graphic is on the left, and then the improved version after kind of discussing with them, terminology, color schemes, other types of information that people might want. There's definitely been an improvement, and I think there's some more room for improvement, but we definitely, as I think a couple other speakers have talked about, trying to incorporate social science understanding into our products to make them easier to understand is a big goal of ours. Next. Another aspect of communication is not only these hydrographs where we say, okay, this is how high we think the water's gonna be at a specific point, but translating that into maps and showing neighborhoods or homes or roads that we expect to be flooded. The big challenge with that is not just the mapping technology itself. That's actually been around for years and it's pretty mature. But what is your forecast flow, and how does that, how much uncertainty is there in that? Because you start going out, like I said, more than a day or two in the future, you're not gonna know the flow necessarily, so that's not gonna translate properly into the right map. So we have the mapping capabilities are designed so that you can look up the map associated with different flow levels, and then so because there is uncertainty, you can see like a range of possibilities that might hit a particular area. And then another aspect of communication, which I think other speakers have touched on as well, is how do we learn from our partners and provide the best service to them? And in the water community, we have a kind of unique set of partners that's maybe not the same as what you might have in the weather community. Of course, we have the Army Corps of Engineers because of all the reservoirs and levees and things like that. We have river basin commissions that work with the communities. They understand the community needs for not only high flow warnings, but also for water supply information. New York City Department of Environmental Protection, they have a huge interest in our forecast because they have to manage the water supply for the city as well as other stakeholders downstream of their reservoirs. And with the partners, we try to do pre-event work. We build relationships when it's not flooding. We understand their needs. During the event, we have mechanisms to interact, two-way interactions, scheduled meetings. We started using Slack just recently. And then post-event, we always want to talk to people afterwards and understand whether the products will be provided are useful and how can we make improvements. So I'm kind of circling back to what I started off with. I just had a list of challenges in both the modeling and the communications. And I don't plan to go into every single square in this table or rectangle, but just some of the improvements that I've kind of touched on here in the last 10 to 15 years for for example, the hydraulics challenges. I don't know if people are familiar with the HEC-RAS. It's a hydraulics model built by the Corps of Engineers, but we can implement more of those and improve the accuracy of our river routing, for example. In the next 10 years, we've started leveraging these already. There's something called the National Water Model that's being run at the National Water Center. They have a capability to run that model everywhere on smaller rivers, and then along the coast, they'll do more integration with the tidal models than what we can do right now. So there's a lot of opportunity in a lot of these areas to leverage new technology. Extreme flash flooding, Patrick Burke's presentation on World Forecasts really hits home on that and offers the future capability to kind of have this higher resolution, more accurate lead times for the smaller scale convective systems that are going to cause these flash floods. And the machine learning you can see in the ongoing next 10 years problems, or next 10-year enhancements. Machine learning is certainly out there. There's in the flash flooding arena, we already have a product coming in from the NASA group. They call it SPORT. I think that's an acronym for some sort of like research to operations technology, but they're running a machine learning model in some of the smaller watersheds across the country and then providing them to the RFCs so we can look at them. So we run our own models, but we also try to look at, models that are being run as prototypes or in the research community to learn as much as we can about what's happening. And then lastly, I talked about some of the communication challenges, communicating uncertainty, the ensemble graphics. Certainly we can continue to work with social scientists on those. For inundation mapping, we need to improve the accuracy of those. Those are kind of, the technology has been here for a while, but the ability to produce accurate maps for all different types of terrain and different types of flooding is the challenge. Understanding partner needs, there's plenty of opportunity to continue with that. And then I didn't talk about this, I don't have a lot of expertise, but we issue these products, we issue watches of warning, and a huge aspect of getting the right response and making people safe is how do people understand the products? How do they respond? And there are a lot of people in the Weather Service that are starting to work more on that as well. So hopefully that was timely, and be happy to answer any questions.
Will you be around tomorrow at all? Can you join online?
I can join up until like 11.
Okay, there's a question. I think this is tying into the social sciences and really like the communicating part, like the products, especially like inundation maps. I guess people, when they're thinking about future floods, I don't know if there's a such thing as a future inundation map, but that would certainly help people prepare for if they need to just go. I can't, I won't make it. Or if I need to just go get some sandbags from Lowe's and just see if I can just get my way through this. But it seems like that is important. The other thing, which is leading to the next talk, is around language. And like when people look at your maps, you look at your site, and if they're not speaking the language, is there something there? Because that's like, you hear, Hurricane Center, Weather Service, but then you start thinking about like river forecasts and flash flooding, and you start saying, well, is everything aligned, or is everybody moving? Like they're talking about AI at Hurricane Center but is everybody in, phase?
Yeah. No, you've hit on really a lot of points with that question. I think, one of the things with the inundation maps is, like I said, we've had some inundation maps for some locations for a while now, but now we're rolling out for many, many more locations where we actually provide inundation maps. But the question, is it a future map? Is it a current map? Is it for now? We have something we call map libraries where we just have a map associated with each river level. So you can go look, well, what if the river level got to this point? Then I can look at the map. But then now the new technology is generating a real-time dynamic maps that says sometime in the next 5 days, what's the highest level of map that you're going to see? Of course, my feeling on those is there's still a lot of uncertainty. So how do we communicate that? And then also with the maps, there's the challenge of, you can see blue on the map covering, say, a road or something, but you don't know how deep it is. Like, well, the current maps don't provide how deep it is or how quickly the water is moving. So those are things that we technically, you can model that, but we're not doing it yet. Computing power, accuracy, those are limitations right now. But ultimately, you want to know the depth, the velocity, and the extent of the flood. Right now, we're just producing basically the extent of the flood. And so that's another part of the challenge.
Okay.
Is anyone storing the data of the observed like river height, so that you guys could move forward to the next step? And you could actually develop the model so that it can feed on the information you guys see?
Yeah, so you're asking about like observed river heights?
Yeah, so when you do get flooding over the years, does anybody kind of storing that data? Where how does that tie to the model? I have to take a look at it.
Sure.
How does that tie to those projections?
Yeah, absolutely. So I didn't focus so much on individual locations in my presentation, but for individual locations, there's a lot of partnership with the U.S. Geological Survey in the United States, and they collect observations of river stage for thousands of locations around the country. And those are the places where we actually issue our specific point forecasts. So we have a lot of data on those locations. There's still a challenge though with, well, what happens where there's no gauge, right? So we need to know, and if there's a big flood and it makes a lot of damage. So in those cases, what we'll often have is post-event assessments where people will go out and collect high water marks, for example, to see how high the water rose, not at predefined locations, but maybe just based on where the flooding actually occurred. And so there are archives of that type of information as well.
That's all right.
Well, some of it is. Again, I think the U.S. Geological Survey has a collection of that data for different events, like big tropical storms, for example. And then there's a lot of data in the research community also with trying to use airplane surveys or satellite information to really get an image of where the water is. And there, those types of data sets, like NASA has some stored in other agencies as well. So there's a large collection about that data.
Thank you.
So a good question about, I think you mentioned already. So the dynamic hydraulic model, which is driven by the precip, right? So in other words, that also including your uncertainty in terms of any extreme events happening because the focus of precip is not necessarily accurate.
Yeah, so the way we handle the uncertainty in the precip is basically just run different ensembles through the hydrologic model. So we take 20, 30 different precip scenarios and we run the hydrologic model that many times and produce different, like a spaghetti plot. And the same thing with the hydraulic model, but the problem is once you start getting the more complex hydraulics, computationally becomes more, you have to run more ensembles. Then it starts becoming, it's actually a computing problem, not a hydraulic problem.
So on the second question, one of the slides shows 4 different factors actually, right? I think number 2 talk about number 3 is the topography.
Yeah, number 2 is intensity. Just in that.
So
yeah,
I would feel like the number 2 and number 3 are related because you have a complex terrain which reduce the extra vertical velocity, then enhance the precip.
Yeah. In this case, what I found kind of really unique or challenging about the remnants of this tropical system were, you look at the rainfall totals and over a large area it seems about the same, about 4 inches total. But locally, the topography.
That's actually what we are facing right now over the West Coast in terms of the AI events. Then if you simply looking in the watershed and looking at the amount, you don't actually see that much of the difference. But then you look individual, the rain shadow or anything detail. The topography actually play a big role.
Yeah, I mean on the East Coast it's less. You can see the enhancement from the Blue Ridge in that event in Virginia. But up in the areas that really got hit in upstate New York, they're hills, but they're not topographically enhancing the rain so much. I think once the rain falls, then those hills really affect the speed of erosion and those types of things.
Well, we're gonna try to get you on tomorrow. There is probably gonna be some questions about the models and and the communication part. I think that's still a kind of a blind spot. People don't think about, unless they live near rivers, they tend not to think about it. And you have some basin-wide stuff that we never think about either. Like, oh, where's all that stuff draining to? So it really needs a little more discussion. I mean, just some basic questions that people may have about that.
Sure. I mean, I can try to come on to the second session.
Yeah, and I'll send you an email to be like, can you come in between these time slots?
Yeah, up until 11.
Yeah. All right. Thanks so much.
Thank you.
Okay, we next have Joseph, Dr. Joseph Trujillo. He's a distinguished postdoc research associate at University of Illinois, and he's going to be coming on as a faculty member. Before joining U of Illinois, he was conducting interdisciplinary research at the Cooperative Institute for Severe and High Impact Weather Research and Operations at, this seems like at NSSL and at the NWS Storm Prediction Center. And we're gonna hear his presentation, which again is very, very important actually in terms of communication. So could we get his talk, or can you share your screen? Either or.
I'll share my screen. I'll share my screen. It's all good. I just before pulling it up, I just wanted to thank you so much for the kind invitation and just say hello to everyone. Yeah, it's truly I just started this new position just as of 2 weeks ago, and it's been an exciting journey so far. It's a postdoc to faculty role where really we're trying it out for the first time. And with all of these talks with, social science and the importance of it in our operations and how we conduct research in the weather and climate space, this position was very timely in that I have a joint appointment in the Department of Climate, Meteorology, and Atmospheric Sciences and the Department of Communication. My bachelor's is in meteorology, where I got it at Texas A&M University, and I have been a weather communicator ever since then. I do freelance work for digital platforms and continue to actively be involved in that space and through NSSL and SPC in the past. But I also see this really important place in where communication and atmospheric science can come together to improve the way we communicate to the public, our practitioners, and really our entire country. But today, what I wanted to share a little bit with you about are the nuances of multilingual communication, because a lot of what we've been talking about today is how do we go about communicating extreme weather hazards in English? Well, you toss it to a complete new language and you get a new level of challenges that you must address. And so in this talk, I'm going to be showcasing some of these and also some solutions, including the artificial intelligence project that we've been involved in to help advance and create a more systemic way to communicate this in the future. And so before showing you any research study or anything of that sort, I first just wanted to start off with a narrative. I think it's so important to highlight the perspectives of the people that we serve on a daily basis. In the aftermath of the December 10th to 11th, 2021 tornado outbreak, the deadliest tornado outbreak in U.S. history there in December 10th to 11th, affected areas in the Midwest, and particularly affected a lot of multilingual communities. In Bowling Green, Kentucky, for example, only the tornado victims alone, I'm not saying the entire county, just the people that were directly impacted by the tornado spoke 12 different languages. And to even help conceptualize that, when an incoming tornado heads your way, you don't necessarily know what to do, especially if you've never experienced one before. Here in the United States, where we grew up with Twister and recently Twisters, and, there's a whole culture around it, especially in the areas that are prone to it. But even in areas like California, they don't experience those kinds of hazards. A multilingual speaker that moves from Latin America, Africa, Europe, and anywhere else across the world faces these dire challenges. And so we interviewed people in this event in the aftermath that received the most direct impacts from the storm. And let this quote be representative of what it really feels like to not understand warnings in your native language. This Guatemalan immigrant in Mayfield and a tornado survivor mentioned that their phone was going off, and initially they were only receiving notifications in English. And that's what you see there on your screen. They're a tornado emergency out of all things. But since they didn't know what that meant, they simply ignored it. If it wasn't for an adjacent Spanish language alert that also said the same thing, they would have never went to go seek shelter in the first floor of their home. When we went to go interview this family, the second floor was completely wiped out. It is so important to state that communicating in a language that you are most familiar with is a difference between life and death. And multilingual communities across the United States continue to amplify in number. As right now, nearly 1 in 5 Americans, or 69 million Americans, speak a language other than English at home. This can be Spanish, this can be Arabic, this can be French. And when we go about communicating it in the National Weather Service and across our agencies here in this country, we undergo a lot of particular challenges because before we've begun automation efforts, a lot of it traditionally has just been grassroots. San Juan, Puerto Rico began this even decades ago in the 1960s when they issued the first ever Spanish language translation for their National Weather Service office. But even to this day, we don't have a systemic way of addressing it. A lot of it has been volunteer-based. So if you're bilingual, you go about translating something and you just hope it goes okay. But recent research that we've conducted in this space have shown that because we're leaving it to the individual to translate, and there's no systemic way of doing it, no collective dictionaries or ways to define this for our field, we go about communicating and translating it in completely different ways. Just take a look at our most leading agencies for weather and climate communication, the National Weather Service, FEMA, the World Meteorological Organization. You check their dictionaries, you check their web pages, and the most fundamental definitions of watch and warning are translating it in different fashions. And I'm not putting the blame on the translators themselves. They have underwent an admirable amount of effort to try to create bilingual resources. This is actually more something that our whole enterprise should address as a whole. It shouldn't be on a grassroots level. Yes, there should be grassroots efforts undergoing to advance this, but it should be hand in hand with government agencies that have established this terminology so that we don't run into this issue that even as of last year, when we conducted a national survey, only 38% of Spanish speakers were able to correctly identify what a tornado watch is. And that's after decades of education across bilingual television platforms, digital platforms, and of course, educational resources across government agencies. So it just goes to show that the lack of standardization does create challenges in the way we go about translating. And today I wanted to show you just how hard it can be to translate because a lot goes into it. It's not just changing from one word to another. You have to take into consideration culture, someone's background, and everything of that sort, and especially their language dialect when you go about doing it. And the best way to go about describing this is nothing other than a McDonald's caramel sundae. I promise this will make sense in a second. Essentially, in English, there's really just one way of saying the word caramel sundae. It could be, maybe the big argument that we have is caramel versus caramel and how you pronounce it. But when you go about translating this into Spanish, you can do it in completely different ways. For example, in Mexico, you would call it a sundae de cajeta. Whereas in Peru, where I'm from, we would call it a sundae de manjar blanco. Colombia, sundae de arequipe. In Argentina, you would say a sundae de dulce de leche. This is what we consider regional dialects or the regional varieties of a given language that are influenced by your upbringings, where you grew up, your culture, the way your family speaks, and, people end up creating their own cultural identities based on language and everything of that sort. And as fascinating and beautiful that diversity can be, we also have to consider it in a risk communication concept. Because if we have now 5 different ways of saying the same word, well, now you have to stop back and say disculpa, excuse me, it creates a lot of challenges in translating weather and climate risk information into other languages, because now, depending on where you're from or how you're raised, you go about translating it in a different fashion. For example, the words rip current can be translated to the word resaca in Spanish, but that can also mean hangover for in different areas in Latin America. So you're suddenly not communicating a rip current risk anymore, but rather a ton of drinking alcohol, which is very complete different hazards. And so we went to go about doing this to really showcase this using Storm Prediction Center risk categories. I'm sure you're familiar with the ones communicated in English: marginal, slight, enhanced, moderate, and high. but they were recently translated to Spanish back in 2014 into the categories you see there below: mínimo, leve, elevado, moderado, and alto. These are used, of course, by broadcast stations nationwide to communicate incoming risk of severe weather in the coming days and whether people should be prepared or not. But quickly, we found that due to regional varieties, or these dialects that I was explaining, broadcast stations across the country started to translate the English terminologies in different ways. Anything you see in red there is different than the official SPC translation, to where you could tune in to the Good Morning America equivalent of Univision in the morning on April 16, 2019. And then you want to probably get an update, right, of the severe weather happening in your area. If you live there in San Antonio in the afternoon, you would get completely different risk categories. Say you wanted to tune into the competitor station, Telemundo, they would have a different set of risk categories airing at the same time. Again, this is not the fault of the broadcasters themselves. It's just that we don't have a systemic way to communicate this. And a lot of people at the time also thought that the initial translations provided by the SPC did not make sense. And so we wanted to get a deeper understanding of this phenomena. And this is where social science research really kicks in. We worked hand in hand with the Institute for Public Policy Research and Analysis at the University of Oklahoma, where they conduct annual surveys of the United States public to get a better understanding of how they receive, understand, and respond to weather and climate threats. And think about it, right now in the presidential elections, there's a lot of public polling. Those very similar methods can be also done to get a sense of how people respond to weather events. And so they do it every year in English, but most recently we started also hand in hand releasing Spanish language surveys to be able to compare the two groups. And so in this specific type of survey, we match up the most recent US Census data of Spanish speakers so that we can have a representative sample of the country and add survey weights too to make sure it's completely representative so that we can make recommendations for government agencies. And the survey is completely in Spanish so we can get a good understanding of how these communities respond. And so what we ended up doing for these SPC risk categories, for example, were providing the original translation provided by the SPC. But then we worked with actually linguistic experts at Penn State University. There, Dr. John Lipsky is a great friend of mine, and he helped us, since he knows all the different varieties of Spanish, helped us create a dialect neutral risk category scale where, depending on where you're from or how you're raised, you are able to understand all the given terminologies. For example, he was able to identify that the word leve, the translation for slight, that word is often only practiced in Spain and not really in Latin America. And that could explain that confusion, but we could only really find out after analyzing data from the people themselves. And so we split it half and half. Half of them received the SPC translation. The other half received the suggested one that we developed with the linguistic experts. And we asked them to rank them from 1 to 5 in terms of risk to go about describing the imminent threat of severe weather. And sure enough, the confusion is now illustrated by data, through a representative sample of Spanish speakers. When we asked them to rank them in terms of level 1 to 5, the original SPC translations were being translated 3 and 5, communicating the same level of risk, which is why broadcasters were changing it in their station to not create, if you're saying there's an enhanced risk, you're now suddenly saying it's a high risk. And so a lot of broadcasters noticed that and went against the SPC recommendation and created their own translations. Makes a lot of more sense now. But with the dialect neutral translation, our participants went to go find that, levels 1, 2, 3, 4, and 5, they were able to categorize correctly depending on risk. And it's not just the overall sample, but when we look at the different dialect groups that I was speaking, whether you come from Mexico, Puerto Rico, Cuba, or other origins across Latin America, they tended to as well be able to correctly categorize from 1 to 5 without any educational campaigns or without any bilingual broadcaster telling you so. And so we presented this information to the Storm Prediction Center, and sure enough, we were able to pass a new risk category scale in Spanish that is now available in the SPC website that goes from mínimo, bajo, moderado, alto, and extremo, or it can be translated to minimum, low, moderate, high, and extreme. Hey, it could also provide some good insights for the English language too, as we consider that in the future. And it was the very first time NOAA passed the research to operations effort into Spanish, which was a huge, huge accomplishment from our team, because not only were we finally able to create a pathway forward for multilingualism, but we created something across the different broadcast stations to where we can now consistently, and not just consistently, but effectively communicate weather risk in Spanish. And it created a translation framework where we're developing that we're not translating the word, we're translating the meaning. Because as previously, we're so focused on just translating the word itself, and as a lot of multilingual speakers know, sometimes context can get lost in this translation. So you sometimes have to resort to a different word to provide that same level of context and meaning. But that begs the question. We've done a lot of great work in Spanish, but there's a whole lot of other languages that we have to address. As a matter of fact, according to the most recent census data, here are the top 6 US non-English languages spoken here in this country: Spanish, Chinese, French, Slavic, and among others there. And of course, as we're considering our effects to Africa, there's also a ton of languages that are already increasing in numbers. They're actually ranked around 7, 8, and 9 there. And so there's like Yoruba, for example, Arabic as well as a big language in Africa too. And we have to consider all of these other languages in the future. And as our colleagues in the National Hurricane Center have so previously been able to introduce the concept, we're now working on using social science insights together with operations to create effective solutions in the future. And because as of right now, when it comes to the National Weather Service, as I mentioned before, we only have things based on local translation teams. We have begun to automate things like Spanish WIAs, for example, are now automated across the country, and also automated tweets as well. But we figured there's a better way to go about doing that. And that, my friends, is artificial intelligence. It's something that we have been looking forward to advancing here to optimize the accuracy of translations, being able to use machine learning to better train a specific model to be able to create better translations given the context of weather and climate. Also to reduce forecast burden, since as I mentioned, a lot of this is grassroots. Operational forecasters right now not only have to do their everyday responsibilities, but they also have to translate, which can be a lot for somebody that is bilingual. And so hopefully this helps them reduce time in translation. And then, of course, address under-resourced languages beyond Spanish to create a more systemic way of communicating this in the future. And so the way we go about doing this is by this given model. We work with Lilt, and they go about, they're a machine learning company specializing in large language models focused on multilingual customer experiences. So what you see here is an adaptive neural machine translation, and it takes the context of the entire document along with learning from corrections made by human translators. And so they were contracted by the National Weather Service, and the Weather Service gives them a domain-specific insight into some of the terminologies and translations that have already been given. And so what the AI machine does then is give you a first guess translation, like, oh, okay, that I think that rain is lluvia. And so then our volunteers in the National Weather Service evaluate it and they say that's correct or maybe not. One of my favorite examples actually most recently in Mandarin is they were trying to translate the term trough, but it ended up translating as trough where pigs eat, not the atmospheric phenomena, completely two different things. And so in that case, they said, no, that's the trough that pigs eat. We need to think about the atmospheric trough. So then you tell the machine that, they're like, okay, I get it. And so then it learns from that feedback. And as of most recently, we've continued to do that for the last 2 to 3 years and have accomplished 99% accuracy, at least in the Spanish language component, in a pilot that they have done with the National Weather Service San Juan office, to where tropical outlooks used to take around 30 minutes to translate and now only take 2 to 5 minutes. TCP, the tropical products, 45 minutes to an hour to translate beforehand. Now through this new machine, that they only take 10 to 15 minutes. And so, for the majority of the part, this San Juan pilot, where we just tried hurricane outlooks in Spanish, instead of translating an entire document now, really they just get the automated thing, and the forecasters only have to fix 1% of the words. It's truly a huge accomplishment, and it goes to show how AI can help address some of these issues. Of course, we still have yet a lot to cover in this space. And so but it does show a promising first result to see how this could look like, not just in hurricane contexts, but future in tornadoes and other hazards as well. And of course, other languages. And so I invite you. Recently, the National Weather Service Director, Ken Graham, recently released this, and there's a QR code in case you ever wanted to learn more about it. You can go visit right now, weather.gov/translate, and you will have access to a beta version of what the future of the National Weather Service will look like. Whereas you could see there on your screen on the top right-hand side there, we have automatic, outlooks and everything of that sort, and that get instantly translated into Spanish. And anything you see there highlighted in blue, there's actually dialectical differences that where us social scientists have come to find, and it gives you alternatives. Here's what the different dialects have this word as meaning, so you can provide even more context to the message you are trying to do. Other things that have been automated are educational graphics. So for example, on the bottom left there, you see a hurricane message in Vietnamese. And then of course, translating some of the products there so we can have better visualizations in the future. Again, this is all in beta format. So if you speak another language other than English and want to give feedback, there are surveys available there, and we'd appreciate your feedback in this developmental phase as we continue to move forward. These efforts are led by Monica Bozeman, by the way. She is our head leader in the artificial intelligence space. So I'm always happy to get you in touch with her as we continue to create a better future. But we're implementing social science along the way because, as we're developing all these AI tools, where my team comes in here at the University of Illinois, I have a lab here with the name of Alertas, Advancing Language Equity and Resilience in the Atmospheric Sciences. And our main focus is the social science component. We're going to be conducting surveys for the first time this year in Mandarin just to give it a shot and see, how Mandarin speakers respond to different weather events. We're also using a geographic information systems, or GIS, to now use census data to locate where these multilingual communities are. Because as we're developing this AI tool, we now have to know where these multilingual communities are located in the United States so that we're not just releasing information, in Vietnamese to a community that only speaks Spanish. It wouldn't make any sense. And so we recently created a dashboard where you can click on a National Weather Service weather forecast office region, and it gives you the composition of limited English proficient, so people that do not speak English very well, those speakers in different languages, anywhere from Arabic, Chinese, French, really what the census has to offer. And we hope that in the future, we can also put this side by side with survey data so that a forecaster can click on their forecast region and say, okay, this is the top 5 language groups in my community, and here's what social science research shows about this. Mexicans that speak Spanish experience hurricanes sometimes. They don't really experience winter weather. We should focus on that. Here's some recommendations for doing that. So we're currently submitting an article to AIES, the AI journal, and the AMS to really overview how we look forward to continuing this great research area. All in all, though, that is all that I have to present for today. When we say that we want to create a National Weather Service, a weather-ready nation, that involves all language groups, no matter the background we come from, no matter what language we speak. Because, ladies and gentlemen, I'll tell you one thing. The United States does not have an official language. English is not the official language of the United States. And what our team argues is if there's no official language in the United States, why should our emergency systems have an official language? Let's strive to create a more inclusive future so that we can ensure that all language groups are considered in emergency preparedness. If you're ever interested in learning about some of the work that we do here, and we have a language department here, so also looking forward to recruiting graduate students that can speak these other languages and have them take the lead in looking at how these language groups communicate this information. So there's my information. I'd love to get in touch in this new Illinois place. And yeah, that is all that I have. Thank you so much.
Are you available tomorrow at all, or no?
I will be, yes.
Yeah, because I mean, we didn't talk about the social media component of this, but I have other questions, and then we just out of time. But really, questions about platforms that people from different languages are using and how that plays out in real time when you're dealing with extremes.
Right. To answer that question really quickly, actually, we're currently doing some research on digital meteorology platforms just because the way we communicate is definitely evolving. And we're now entering a decentralized communication landscape where, nowadays you can get information from really anybody. And recently what we've been doing here is I've been actually doing some freelance work on digital platforms. And I've been able to get a hold of a lot of Spanish speakers through that because there's many areas in the United States that don't have access to Univision or Telemundo. Like here in Illinois in Urbana-Champaign, we don't, the Chicago station is the closest Spanish language station we have. And that's miles away. That's 2 hours away from us. So a lot of people are actually heading to social media, especially multilingual speakers. And we've come to find that increased numbers among these populations are starting to reveal themselves. And even the most recent Pew Research Center data show that 86% of Americans have relied on at least one social media post or social media platform to receive news. And so therefore weather is also trailing right behind. And so we definitely need to consider how we go about communicating this in other platforms in the future and challenging scientists too to get more involved in this space, just because it could now in a decentralized information landscape, you can have people that will intentionally sue misinformation, disinformation. I mean, you probably ran into a TikTok that shows a NAM model that reveals that the world is exploding, gets 1 million likes, where that's not true, but people can technically do that. And we as scientists have to be brave enough to also confront it with facts,
Okay, so I'm going to reach out to you today because really this is a very important point about being brave enough because I think there's a tendency to pull back because we haven't been trained that way. And so actually hearing your point of view would be super important.
I appreciate it. Yeah, no, I think it's important, to get more scientists involved in communication. And, there's a lot of great things, even here at the Department of Communication that we learn, things that we borrow from health communication, because we face similar challenges. They have to communicate diseases that are unknown to us and encourage us to take medications and make healthy decisions. They've learned so much in how to encourage people to promote safety behaviors. And I've learned a lot from them. It's actually how I got into this multilingual space. I borrowed a bilingual health communication framework and applied it in the weather space. So yeah, the world of communication is vast and we can learn so much from it.
And this was a great presentation, eye-opening.
Thank you.
All right, our last speaker is Bill Parker, and he's going to be talking in another kind of parallel track that we don't think about. So I want him to come up and do what do whatever you do.
I know this is the end of the day, and so I'm not going to be long. I'll be quick with this presentation. Joseph just talked about that there are challenges in communication, and the National Weather Service in Jackson, Mississippi, we definitely deal with communication challenges. And it's not always language. Sometimes it's just, can people get the information that we are pushing out? Is there a method for them to get that information? So you go ahead and go to the next slide. And so in our area, we deal with what we call social vulnerable areas in Mississippi. And what I like to say is you can close your eyes and throw a dart at a map of Mississippi, and I guarantee you're going to probably hit a social vulnerable community. There are communication barriers within the acronym there stands for historically underserved social vulnerable communities. And so the National Weather Service in Jackson, we have multiple efforts that we're doing to reach the vulnerable communities in our area. So that's what we'll wrap up with. So just a background on Mississippi. Mississippi has the highest poverty rate of any state in the United States. We are considered the poorest state in the United States of America. 6 of the 12 county parishes in our area have the lowest median household income in the United States. And so Mississippi has the lowest percentage of population with access to just broadband internet communication of all the states in the United States. So it's a very poor state, but I love the state, I'll be honest, just say that. Next slide. So what is social vulnerability? There's several factors that we include when we talk about social vulnerability, factors that weaken community ability to prevent human suffering and financial loss in a disaster. So poverty is one of those things that you take a look at, lack of access to transportation, low quality housing. And the Social Vulnerability Index was created by the CDC. There are maps across the entire US that they've created that shows different communities and their social vulnerability risk. So here's the SVI map for Mississippi. And again, like I said, you close your eyes, throw a dart at the map, 9 times out of 10, you're gonna hit a social vulnerable community. The area that we're gonna focus on today is that big blob of dark blue that you see. And so the darker the color, the more vulnerable the community is. And that area where you see most of the darker blue kind of collected together is what we call the Mississippi Delta region. Right along the Mississippi River is a flat land, and they see all types of impacts as it relates to weather. And usually it's those communities that struggle and have a harder time in our county warning area to recover from significant weather impacts. So many of our most socially and economically vulnerable communities are also most at risk for, again, natural disasters. And so CDC came up with a social vulnerability index, but FEMA created a national risk index to illustrate communities at risk based on 18 natural hazard types. And their map looks kind of similar. Go to the next slide. Their maps look similar. The brighter colors, reds, orange, yellows, means that you have a pretty high risk of seeing some type of natural disaster, some type of weather-related disaster, a natural disaster. Notice along the coast is all bright red, and that's basically induced because of the risk of hurricanes. But you know, as you move inland, you still have some risks that are very, very high. And again, notice the area kind of in the center, but where you see the reds just northeast of Jackson. Again, that's the Delta region of Mississippi. And so we circled it, and you see that area for us is really one of our most vulnerable areas in our county warning area. There's a lot of people out there that, and you'll see in the next couple of slides, they don't really have ways of getting communication. They don't have internet service. I've driven out there, a lot of spots, the cell phone service is very, very poor. And then, believe it or not, there's some areas in our county warning area that don't get local news. So here's the broadband availability in Mississippi. And we don't have spots that is just zero, no data. But on this, according to this map, and this based on the county, portions of counties that they did, yellows mean that there's only about 25%, 0 to 25% of the people have broadband internet access. The green areas are less than 50%. And then once you get into the blues, that means, you know, it's greater than 50% area. So the big dark blue area in the center, that's the Jackson metro area, of course. That's the largest city in the area. And then you have along the coast of Mississippi, they have good areas. But as you move into the central part of the state, it gets less and less across our area. So that's a big communication issue that we have to deal with, that most of the people just don't even have broadband availability in the state. So what are some of the things that we're doing to bridge the gap, to work on the communication barriers that we have in the state because of the social vulnerabilities? Well, one of the projects we're working with, we collaborate with the C-STAR project, basically exploring messages and barriers in vulnerable communities. Mainly, we're focusing on the Mississippi Delta region. The image, the map to the left, that's the area we're focused on, the area in the red and the yellows. And we're doing focus groups with some of the communities. We're talking to them. We're finding out what methods can they receive information on. We're taking surveys. We're talking to the people about do they have an understanding of the different natural hazards that will impact their area, and also do they understand how they can protect themselves when those natural disasters or hazards impact their area. So we've been doing a lot of things like that, but that's worked through the Sea Star project. One of the things that we're doing is working with our emergency managers. Recently, again, the Rolling Fork tornado, many of the people didn't have no weather radio. And so we worked with the local emergency manager to help him purchase some weather radios to distribute in his county. And we had a very, very high turnout with people. But again, when a tornado goes through an area, if you're gonna start giving out weather radios, you're gonna have a high turnout. People become very, very interested at that point in time. But Sharkey County is where Rolling Fork is located, and again, the citizens came out to receive those radios to make sure that they can get the warnings that way. We do several town halls. We go around our entire CWA, and again, one of the best ways for us to understand how we can better communicate is really just going out and listening to the citizens that we serve. And so we will target different areas, local partners, emergency managers, work with local businesses to host these town halls. This one here in Forest County, we kind of tried to make it a family event. We had, giveaways. We had food. We had things for kids to do, just so that we can engage citizens in a fun way, but also be able to talk to them about the dangers of severe weather. And so we're constantly trying to bridge the gaps. We're constantly trying to get out into the community, let them know that we're concerned and that we want to make sure that the services that we provide and the communication that we do provide when it comes to hazardous weather, that they are able to receive it. We work with Jackson State University. Jackson State University has two programs that we work with. They have what is called Center for Community Resilience Project. It's actually something that I really was a part of to help them get it started. And so they have this program called CREATE. It's Community Resilient Engaging Advanced Training Project. And what it's doing is we're trying to recruit and educate local students from historically underserved and socially vulnerable communities, educate them about the opportunities in this field, in the science field, in the communication fields, so that they can go back, get educated and go back and be the people who can really, really connect with the folks in their hometowns and their home areas. And so the more we educate people from those areas, the more we get people exposed to the work that we do, I think the better off it's going to be in us really, really meeting our mission and us really also understanding the needs of those communities. So that's one of the things that we're doing with Jackson State University. So I'm not going to show any videos. Dr. Jenkins wanted me to show some videos, but those are links up there, 2 good videos, I think, that you can look at that really deal with and talk about the impacts on social vulnerable communities. The first video is Rolling Fork tornado video, and it really talks about it. And you'll see, sometimes, in that video, you hear people say that they didn't get the warning. Well, if you talk to a meteorologist, he's going to say, oh, well, we gave them 13, 14 minutes of lead time for a tornado. But just because we may issue a warning and we think we're giving people lead time, it doesn't mean that they received it. And then the next video is called Muted. It was produced by the Institute for Diversity and Inclusion and Emergency Management. It's another video that I work with some people on. But they cover a wide range of things. So they cover the rolling fork tornado. They cover risk for hurricanes on the coast. They work with our Native Americans and talk about some of their vulnerabilities. So it's the muted video is like 1.5 hours long, whereas the rolling fork video is only about 26 minutes long. But I think they're really, really good videos if you would like to go and take a look at and see how, weather impacts vulnerable communities. And then the last slide that I have here is the victims from my rolling fork storm. And the reason why I show it is because a lot of times in science, we just focus on numbers and we don't put faces with numbers. These are real people who are often impacted by the storms that roll through our area. It could be a flood event. It could be a tornadic event, whatever. But storms don't care, and they impact young people. They impact old people. And I often, when I go out and survey and find out that I had a fatality, I often want to try to get to know the person that was impacted, but also want to know what happened and if there was a way that we could have saved a life. And so, again, I often want to, with my forecasters in my office, I want them to always know that fatalities aren't just numbers. They're faces that go with those numbers. So that's it.
Wow. Okay, we gotta take some questions because he's leaving and we won't see him again. So any questions we should ask?
I came across a study a while ago saying that the tornado fatalities in recent years increased a little bit due to the larger spread of mobile homes being hit than before. And I'm wondering how that is or is not a problem in Mississippi.
It's a huge problem in Mississippi. 60% of people who buy their first home in the state of Mississippi buy a mobile home. And, tornadoes are one of the biggest risks in Mississippi. And so it doesn't take a strong tornado to do damage. A very weak tornado can cause major damage to a tornado. I'm talking about EF1. And so to a mobile home. And so that's one of the things that we have to deal with. There are not many community shelters in Mississippi. And the very few community shelters that we have in Mississippi are in more affluent areas. They're not in the areas where we have those social vulnerabilities. So for instance, Rolling Fork didn't have a community shelter. It's one of the things that I'm working with them on to try to get one, make sure that they get one. And they understand they got a lot of focus with that tornado that came through. And so the emergency manager has been talking to me. He's like, man, if we get one, I'm not trying to get one just to house the people in Rolling Fork. I want to make sure that I house people in our neighboring counties who also will need a place to go. And so, yeah, when it comes to mobile homes, that's something that we really, really have to deal with. Here's another thing. Even if they can't purchase it, 70% of Rolling Fork were renters. And guess what they were renting? Mobile homes. Yeah. The majority were renting mobile homes. And so if you're a renter, you don't get the FEMA help. You have to be a homeowner to get the FEMA help.
Wow.
How would we use, which by the way, I love the method of just how you're running, you're connecting to the community and not kind of just sticking a Band-Aid on it. I mean, like you said, you go talk to the families and when you go to the site, you come with like a caring mind. I have 2 questions. One, how do we kind of get that to other National Weather Service and like the other offices that they have? How do we continue to grow that method? And is that even possible? Does it only come from like a kind heart? One, I want to hear your thoughts on that. And then two, how do we, how would we go about, if we were to start making change in different offices, how do we go about that and making it actually legal, that people are caring about the people that are being lost and not trying to stick a Band-Aid over a severe storm, and actually making change, like I asked earlier. And I was like, hey, so you guys seen that Hurricane Otis, what it did. Now you can keep running models, do what you want to do. What changes are you guys getting ready to make? Have y'all even wanted to change anything, or do you want to just stick with the same old methods? What are your thoughts on that?
Yeah, so the first part of your question is asking if other weather service offices begin to do it. Yes, slowly but surely, weather service offices are beginning to pay more attention to the social vulnerable communities in their areas. They're beginning to reach out to their partners, and it comes down with leadership. For a while, you didn't have leadership that paid attention to that, but the Weather Service leadership now really does pay attention to it. King Ram, the Director of Weather Service, matter of fact, in October, the National Weather Service is coming to Jackson State. Jackson State is going to host the National Weather Service Equity Summit. And so when leadership at the top is showing that, yes, this is important, and we need to do a better job of connecting with our communities, understanding what they need, how we can overcome some of these barriers in communication, then it begins to trickle down to other forecast officers. So it's slowly beginning to happen. But again, it starts with leadership at the top saying, hey, this is important, and these are some of the things I want you guys to do. The National Weather Service in Indianapolis just hosted themselves their own local service equity workshop, just to learn more about their area and how they can do a better job of serving their community. So it's happening. Okay. Yeah. What's the other question?
It was asking, like, how could we implement and not make it, because the government is full of laws, and it feels like you have to tell somebody. Nowadays, you do have to tell somebody to be kind and caring. Majority of people are selfish and like, oh, just me, or I'm good, my house is good, who cares? I don't care about 2 miles up the street. But with thinking about that, how do you make it not necessary? I don't want to say protocol to check on people and to make sure that we're actually hitting these marks. You said it's growing, but how do we make sure that it's going to continue to grow? And just because you change the leadership and then you get, someone who's like, oh, I don't really want to put this in place, how do we get that to stay so that we can continue to progress forward with that?
That's a tough question. I mean, I think one person has to impact another person.
Okay.
In the interview today, I was talking to David, the communications guy here, and I was telling him how the African presentations really impact. We talk about fatalities in America, but man, the numbers that I was seeing this morning just was blowing me away. And he asked a good question. He says, well, how can, the US, how can we help those countries? And I said, again, you got to have people who have the mentality like the Good Samaritan. You got to have the Good Samaritan mentality, not just in the US, but around the world. If we're going to continue to be leaders around the world, we're going to have to begin to show people around the world, especially people who are suffering, that we care. Well, that starts at home first before we can even get around the world.
Thank you.
I think you make a really good point, but I also think that sometimes I'm going to ask this question that Lauren said first. Lauren said, occupancy of mobile homes can be difficult to track in rural areas, and consideration should also be given to seasonally occupied homes that house migrant agricultural workers. So it's like a flux.
Oh, yeah.
And that might not be captured in census data. No. But at the community level, it's probably known, right?
Yeah.
And so, digging in at the community level which to me says something else, which is like we putting the pressure on weather service, right? But I think you're doing it right. When you reach out to universities, when you're engaging young people, to me, you're building something that's more impactful because you're building local infrastructure. It's not just saying it's a weather service, it's everybody, right?
Yes.
Yeah, so that's amazing.
Now, we can't solve, the weather service can't solve the problem by themselves. And again, our job is to deliver the message, but there's so much more that comes with people receiving the message. And in one of those videos, you're gonna see, especially Rolling Fork video, one of my forecasters talked about when we were issuing that warning. And we knew that we were gonna have a high number of fatalities. And he says, even if I could have picked up the phone, or basically he was saying, even if we could have picked up the phone and called someone in Rolling Fork, the question will be, where would they have gone?
Yeah.
Okay. Same thing. I'll give you a perfect example. Personally, in New Orleans, you know, that's where I'm from originally. And when Katrina was coming, some people just couldn't leave.
Yeah.
I had 60 people in my house up in Shreveport myself, but you had people who just couldn't leave. They didn't have a way out. And so even if you get the warning, do I have the means to protect myself from what is coming?
Right.
And that's what we have to work on.
Yeah.
Because we already talk about the homeless.
Yeah.
That didn't even come up.
Spirit of that, for anybody who is going to the annual meeting this year to New Orleans, I highly recommend you to go to the city museum to see the Katrina exhibition.
Yeah.
It's extremely good.
Well, I often feel like now I'm talking to these university students that we're in a protected and privileged kind of position, right? And we don't really think we got to go out there. And I think we're being trained not to go out there. We're being told like you just stay in your zone. And whatever that zone is, you feel comfortable in it. But then when you show the pictures of the people who died, or if you did that for Puerto Rico with Maria or any of these places, it has a different impact on you, right? So I think we have to really go beyond our training. Our training is
focus on numbers.
Yeah. And so you're looking at like, oh, you're looking at 179 people died in Mozambique, right? But you're not really thinking about what that means.
What it means.
Yeah, and I think we have to really get away from some of this because it's kind of crazy in a climate crisis to be looking at numbers but not thinking about the people. Yeah, the people. I mean, that's really it. And so I feel like we have to do something different. I don't know what that is, but when I look at what you're doing, I think that can inspire people to think about how you work in these bigger structures that are just seems to be fixed, but they can also be impactful. So I think we're really appreciate that. All this is going to be available. I want to talk to Nikita. How we're going to do this? I don't know the technology myself. How are you going to put these presentations on, whether it's YouTube or we have all the recordings, but I think, you know, people have to sometimes, they need time to like absorb what's happening here, right? And that's what we can do. And so I think that will stay with us no matter what. And we're not thinking about stopping here. So, you know, I don't ever do anything without connecting dots. I just don't tell people where the popcorn trail is going. But trust me, there's a popcorn trail that's being built.
Yeah, and this is my, like you said, I have to get back tomorrow. But man, I just want to tell you, this was an awesome, awesome workshop. Man. You did a great job with the speakers that you guys had a part of this. I'm thankful that y'all allowed me to be a part of it. Because I've learned a lot. Like I told you, we got to go to Africa next year.
I keep telling him I'm going virtually, but I don't want to do no carbon footprint.
Okay, so you want to know why I came here? Why I really got on the plane to come here? Well, one, because I had never been, and one, I wanted to see you. But the real reason I came was because I could have participated virtually.
Yeah.
But if I would have tried to participate virtually, there would have been so many things that would have distracted me from these talks.
Yeah.
I probably would have just came on and presented, and even if I had it up, I wouldn't have been paying attention.
Yeah.
Like I am in the room. And so that's why I say we need to go to Africa for that first African Meteorological Society.
13-hour flight, 11-hour flight.
Yeah.
But let's see. Yeah. We have to do something.
Yeah.
But anyway, we'll all convene tomorrow again. And I hate to say that it's an early one, right? What time does it begin?
8.
Yeah, but we have to take into account our colleagues in Africa.
12 UTC.
Yeah, so we don't have a choice. I like to sleep personally, but I also realize the moment and the time. And, you know, not just the time in terms of like the wet season in West Africa is building up, but also the hurricane season that we're having here. All this is now. It's not like next year, or it's like we don't know how things will go. No one knows. And what we find for sure, my colleagues in West Africa, is that things happen. Just like, whoa. And people like Riyadh will send a video and you'll see like, whoa, this happened this morning? Yeah, it's happening now. This is amazing how this like extremes are playing out so fast and such a big impact on people. So anyway, thank you everyone for attending this today, and we'll see you tomorrow. Martella, I'm sorry it's so late. Get some sleep and see you. Bye.
You already started stretching because it's too late.